Part of the challenge that the amateur astronomy community is facing is to bring in more people into the hobby. So we've been actively trying to contact different people, science communicators, people with influence are also interested in astronomy, to help them help us popularize the hobby. I think it's very, very important for all of us to do that because as a hobby, we want to make sure that it's growing. And one way to do it is reach out to younger people, make sure that the next generation, the younger people, are actually getting into the hobby.
Basically, I look at it now and I think of astronomy as more of a really artistic. You look at all the beautiful pictures that they do, and I think that's going to bring more people in. It's like getting the big buck for the hunters. You want to get the most beautiful picture that you can get, and it's kind of a competition, really. Something that can be achieved, and you don't have to have physical strength. You don't have to have all these different things, but you can go in and just be able to have that creative spark and eye, and go out there and work with it.
I guess what I do is I have a small group of friends near my home. And if I have a night where I decide to take out the telescope, I'll invite them along. It's not really their hobby, but it's nice to branch that out. But I would like to do some outreach to some high schools or elementary and get the kids interested early so that it's not something you're starting when you're 20s or 30s. It's something you start early on and you just get that for your whole life.
Already we can see that the impact of social media has popularized astronomy a great deal amongst people who just have no real direct interest in astronomy, but they get excited about these things, like this eclipse that just occurred. Had one of the largest turnouts that have ever occurred for a solar eclipse. And I think it's 100% due to social media and the news coverage that it gets. So I think that is making it more important. In other words, you can reach people much easier now than you ever could before.
I think the general public is more into, the now results, So a lot of people like to share things. I find that people like sharing, they want to see results, they want to make things easy. So I see a expansion into just easy imaging and sharing.
There's a lot of people now doing science, not just astrophotography anymore. There's a lot of people doing science. There's a lot of citizen science, and there's schools that are doing science. The easier we make the telescopes, the more science that the schools can start doing. We get colleges doing science, and maybe even down to high schools doing some science projects with NFS grants and such. So because the capabilities of the telescopes today are so much more, I think the way to get the young people involved is to get them using them in schools.
On the scientific point of view, astronomy is trying to answer very fundamental questions, and most of them have to do with cosmology, meaning where does the universe come from? And there are still many questions. Most of them are unanswered. The other search, I think, in astronomy is searching for other planets, other intelligent civilizations, or even sign of life, simply sign of life on other planets. I think that's the second quest. The first, I believe, should be trying to find out, answering the big question of cosmology today.
I think there's a renewed interest in astronomy. It really peaked for our generation, or the generation slightly before us, with the moon landing and the Apollo program. And then we had the space shuttle, but with the cessation of flying the space shuttle, people predicted that there would be less interest in astronomy. But as Cassini and some of the other probes have demonstrated, a lot of interest is generated because we're getting looks at our solar system with the technology that has been put into these probes that we were never able to get before. And I know that the generation, my children's generation, has a lot of interest in these types of things, and I think that interest will continue. And those are the future astronomers and future amateur astronomers that are coming out of that.
I think what you're going to see, and what you're already seeing, is that amateur astronomy is making significant strides in the professional realm. You've got amateur astronomers finding comets and asteroids and near-Earth objects, and I think that's just going to continue to happen. I see a network of astronomers, maybe a network of satellite imagers. If you can turn households into a satellite spot, and suddenly you've got a satellite telescope that's the size of a hemisphere, just because amateur astronomers are working together. I see that happening. I see the entire community coming together and doing more.
In terms of making astronomy something that it can reach a much broader audience, we want to see more development of those accessibility options via the internet and ease of use, to try to make it a simple process. Using your iPhone is a pretty easy thing to do, and it'd be great if we can get to where people can access these high-end telescopes and take these terrific images and also do research. You think about the science projects we did when we were young, in some respects pretty primitive what kids can do today.
One of the most successful programs that I've seen for engaging younger students and younger kids in astronomy is the Sonoma County Astronomical Society has a program where they have students, little kids, write essays, and then they take the best essays on astronomy and they give them telescopes. And these kids, I've been surprised, it's mostly girls. These kids, they get these telescopes, they bring them to star parties, and they become little experts, little amateur astronomy experts, and they give public talks and presentations, and this is one of the most successful places. I'm a member of about 5 different astronomy clubs, and this is a great way to bring in a younger generation and help them maintain it, because we've seen over years now these kids come in and they stay in there, and this is a kind of program I think we need to scale it, we need to use it as an example and do it elsewhere. Just sort of one small example of one thing we can do.
We live in a fast age, right, where our movies and our music, our media, fast edits, instant gratification, loud and in-your-face kind of stuff is required to hold people's attention today for a half a second, which is sad. And so the subtle and the esoteric stuff suffers. I think it's very difficult to get a lot of younger people into this as a hobby. It seems like there's more younger folks, even women, who manage to get into the professional sciences, astronomy, cosmology, whatever it is, but in the amateur way, getting them to a telescope, getting them to a dark sky, inspiring that wonder in them is difficult, I think.
Giving someone the opportunity to not only see it for themselves, but do it for themselves, and say, here, have a look. For example, if they have the privilege of looking through a telescope and seeing the rings of Saturn, give someone that opportunity to do that and see it for themselves with their own eye. It has an incredibly powerful impact. And what I'll find, and for those who, like I say, there are many outlets where you have an opportunity, city star parties, outreach events. Once you see it for yourself, it's like a catalyst that the rest starts to take care of itself. The interest will be there.
One of the things that concerns me greatly is the fact that so many people are moving away from science and from facts. The fact of the matter is math, history, science, and facts matter. And so to advocate that and to advocate education, I believe that college education should be absolutely free. We should be investing in the brain trust of this country. And so to me, our job is to advocate science. Our job is to inspire people to really embrace what is right.
The stars are for everybody. And I would like that, if I could do that, if I could spread the interest out amongst everybody, that would be the biggest contribution I can make.
I'm Jen Winter, and I own Daystar Filters, and we're actually out of Warrensburg, Missouri, flyover country out there. We have lots of square footage, lots of acreage, and big blue sky. I've had a very strong math background, and I was studying mechanical engineering very early on, but I also was heavily into photography, scanning things. I worked in a newspaper, so I was in media with a math background, or math with a media background. The two came together when I met my late husband, Vic, who was an astrophotographer with a Kansas City Star. And I was instantly hooked on astrophotography because it was a marriage of that art and science both in together. And Vic really got me addicted pretty early. He pulled a 16-inch Dobsonian out and put it on Saturn, and the rest was history. That's one of the worst ways to get hooked, of course, Saturn. How many people hooked on Saturn? I always like to refer to a story when I was in school. We had a gentleman who was working in Kansas State University in Manhattan, Kansas, and I was going to school there, and a gentleman discovered there was, a grad student said, "What do you mean we have a planetarium and nobody goes to here?" So he went around to every school, everywhere, brought every student, every person in town went to the planetarium that year. And in my little group, as we were going up to the top floor, we passed a room in this physics building, and here were these guys in their little brown corduroy suits, just all excited because Voyager was going by Saturn, Jupiter, I don't even remember because I was so small. But here they are, they're showing video of a planetary pass and getting data live. They were coming out of their skins, jumping up and down in the chair, and I'm like, well, you know, this is really interesting. And I was fascinated at that moment, but I got dragged away to go to see the planetarium, which frankly, after seeing actual images of the planets, seeing the dots was a little bit less. Well, I think we need to get a little bit more hands-on and a little bit less hands-off. I'm finding that when we do outreach, in our area of the country, there's an awful lot of outreach, but I find that the youth are becoming so addicted to their screens, and there are so many good pictures of astronomical things out there that seeing something on the web is sufficient. They're satisfied by seeing these Hubble images. But when they have the chance to look through that telescope and see Saturn through the eyepiece, there's always a moment where they question, is this actually real? Am I actually seeing this? So that direct connection to the equipment, having a hands-on experience instead of a cyber experience, that makes more of an impact, I see, in getting them moved along further into astronomy. We found that schools have more difficulty getting, with budget issues, they're having difficulties getting people out to field trips for nighttime astronomy. But daytime astronomy, of course, you can go right to the school. We have outreach guys who can, and there are even a lot of outreach support groups where you can participate and even have access to materials to get out and visit the schools. And during the daytime, the teachers are much more likely to have activities and the hands-on opportunities daytime versus nighttime. It helps a lot. The most important thing with the sun is, because the sun is so bright, astronomy is usually about collecting light, and more light is better. But with solar observing, you're buying dark. The sun is already bright enough, so bright that it'll blind you. So with solar, we always have to reduce down the amount of light that's going to damage your eyes through infrared and ultraviolet radiation. But also, if you reduce the light from wavelengths that you don't really care to see, then you can start to pick out details that you wouldn't otherwise. And the hydrogen is all about, perhaps you remember in chemistry that you have these little emission lines that in a spectrum you see lights light up in different colors. So we're going to isolate the color of light that hydrogen emits. So then you can, and hydrogen and helium is what the sun is made of. So then you get to see what the sun is really doing instead of it just being a big circle. Hydrogen alpha will be the brightest line, and if we got more complicated, there are energy levels and how much energy it takes to make different wavelengths of light. Hydrogen also gives, the alpha line gives a more interesting view of the sun. So you have it's more interesting, it shows more contrast, it's brighter, and it represents an energy level that physicists are interested in the science from. A lot of times folks don't quite realize that the sun is a star. It's the most fundamental concept about astronomy and about actually solar physics. Everybody gets excited. There's even, what is this, the new TV show Rick and Morty is all about physics, all about the physics. Well, we happen to have a really cool physics experiment Einstein's theory of relativity references things like the sun in it, and so solar physics is astronomy, except up close in a way that we can watch it change hour to hour, day to day. We're still today, even Citizen Kate is learning more about. The Citizen Kate was the project where they were looking at the sun during the eclipse. We're still doing real science on the sun every single day to learn more about physics that we didn't know yesterday. So I like solar versus nighttime just for that interactive aha moment where it's not just black and white dots.
Good morning, guys. It's a beautiful day here in sunny Southern California. I don't know what it's going to be like for you over there, but I have Steve Ramsden from the Charlie Bates Solar Project, correct?
Charlie Bates Solar Astronomy Project, yes, sir.
Solar Astronomy Project, and he is going to be going crazy with all sorts of goodies. I mean, this guy has more stuff than I do when it comes down to solar. I've just got a handful of things. Because let's face it, I'm an amateur, hence why we call ourselves amateur astronomers. But we've got a pro here for you guys, and he is going to be rattling on and on and on, hopefully, because we've got 4 hours to kill. I've got to go set up a scope real fast, just in case we have more bad weather. And you guys are going to have some live views of the sun, and he's going to go through a presentation. So, Steve, the floor is yours. I am going to mute myself, so it's all you.
Thank you very much, Simon, and thank you for the opportunity to share what I love the most, and that is studying light. Solar spectroscopy, stellar spectroscopy is my thing, and light is a very, very fascinating thing. So while I've been waiting to go on, I've also been bird watching with these awesome Meade Rainforest Pro binoculars. They are incredibly clear, man. They're HD. They just came out with them, and I've seen cedar waxwings, 2 red-shouldered hawks, robins, a chipmunk, and my wife on the balcony. Because you see, I'm out in my driveway right now with all my gear set up, and of course it was overcast until about 3 minutes ago. So I'm going to start with a presentation first, and then we're going to go into some live solar, either with Simon or me. So it ought to be awesome. I've got my mask just in case somebody comes up, and my hand sanitizer, because I live in the #1 zip code in the Southeast for COVID. And I'm also old and high risk. So if you see the mask go on, it's because one of my neighbors is pulling in or whatever. But let's talk a little bit about the sun. And it's I've been planning on this live broadcast all morning. I get out here, set up all my gear, man. I have a massive array of telescopes in front of me, the Solar Max 3 double stack, calcium K scope, white light scope. And it was just totally overcast until right now. And you can see the shadow on my face, which is the first time I've seen the sun all morning. We're going to go through a quick presentation about what I love about solar astronomy. And I hope that you enjoy it, and I hope it's not too boring. I'll try to go fast. I think it's fascinating, but we will be here for probably 4 hours. So between Simon and I, we're both going to get some fantastic views of the sun and a little bit of information about astronomy. So thanks again, Farah and Simon and everybody over at Woodland Hills for allowing me to get on here and talk. We'll talk about a few products also. I got the Shellyak Hi-Res 3 behind me and a Coronado PST sold by Meade. And they're sitting on a Skywatcher USA Helio Find mount. It's called a Solar Quest mount. That thing is really cool, man. You just turn it on and it finds the sun. It is really, really sweet. Let's see if I can work this newfangled technology and get the screen share going. Alrighty. Share. And now we're going to talk. By the way, that's an aircraft flying overhead. I live in the middle of downtown Atlanta, and it's always something. Now the sun's actually getting so bright I can barely see my computer screen. I am outside in the driveway with a 27-inch iMac broadcasting over Zoom in case anybody cares. Solar astronomy. Charlie Bates Solar Astronomy Project. Yeah, that's a cool thing. So let's get talking. First, who am I? Well, I founded the Charlie Bates Solar Astronomy Project in 2008. Yes, that's a police helicopter flying over now. We'll just enjoy that noise for a second. And the sirens. Like I say, this is downtown Atlanta. Always something going on. All right, I founded the Charlie Bates Solar Astronomy Project in 2008 in memoriam for a dear friend who was in the military like me. I'm a retired Navy veteran. And he was also an air traffic controller with me. And he took his life over the demons that we all have. And I thought, this would be a really good way to remember this guy and also to do something good for my society by trying to spread science and reason. Okay, here comes the helicopter again. Hang on. By the way, the patriotic flyby of the Blue Angels and the Thunderbirds went directly over the spot I'm standing in a week or so ago. It was really cool, man. Okay, so what inspired me? Well, of course, Star Trek. I mean, same thing that inspires everybody. If you never watched Star Trek, I would just say, what's wrong with you? Carl Sagan, I think one of the greatest science, or maybe the greatest science communicator in history, in my opinion. Currently 54, no kids, married to an attorney who spends most of her time yelling at the laptop. And she is inside working right now. So in case she comes out and starts hollering, I may have to go do some tech support. Retired air traffic controller in Atlanta, the world's busiest air traffic facility. Some U.S. Navy nuclear propulsion. You can read. This picture, that's me over there with the hippie haircut in 1981. I went to the summer science training program at Georgia Southern College way down in South Georgia after winning a contest for making nylon of all things and writing a paper on it. And our instructor was Carl Sagan, 1981, the height of cosmos. This guy comes down to South Georgia and spends a week or two with a bunch of rednecks. So it was a fantastic thing, and I was very lucky to be involved. Since then, I've had a pretty ordinary life. There's a picture with Terry Legault. If you don't know who he is, he's the great ISS photographer. And I've done a lot of cool things. The coolest thing has been starting this nonprofit and sharing science with people. Let me tell you, I've been very, very successful in life thanks to some good teachers early on. It has been a lot more fun giving away the money than making the money. And I encourage the rest of you to do the same. What is the Charlie Bates Solar Astronomy Project? Well, it started as a telescope outside of a Starbucks in Atlanta. And then within a month or two, I was doing schools, setting up gear remotely all over the Southeast. I did something original with it, and that is, this is back in 2008. I put cameras with the solar telescopes and broadcast live solar images through cameras. So that was something nobody else was doing. And we took the kids through and told them about the sun, let them look through the visual scopes, and then took them over to the solar imaging scopes, which was something totally new. Now everybody's doing it, and I'm glad, but it's a great way to share some hands-on astronomy with these guys. And my video is a little choppy, sorry about that, but that's the way it is. Let's talk about where we came from. This is just fascinating to me, man. This Big Bang thing, where this just pure energy just explodes, 15, 16 billion years ago. And it cools down slowly as it's expanding into our four-dimensional universe that we live in from some other place. I'd like to say I know where, but I don't. And while cooling, the energy forms matter. First subatomic particles, then hydrogen, all controlled by gravity, expanding out at extraordinarily fast speeds. Time and space were created by this. yeah, it's mind-boggling to go into this. That's why I love physics so much and love cosmology and math. This explosion where we came from is absolutely fantastic, man. It's just like watching a sparkler. You know, I always try to do a sparkler on stage if I'm in need for something, and I say, look, man, every one of these little sparkles is pretty much the same as the Big Bang on a tiny scale. I mean, it's energy, it explodes, it cools off, it makes ash, and we are the ash. So let's keep going. This is the Orion Nebula, of course. I'm not sure why. Oh yeah, this is what happened after the cooling over many, many, many hundreds of millions of years. These awesome things called stars were formed by a gravitational collapse of this hydrogen, these first generation stars. And then all this gravity, you know, caused these stars to group together in these little clusters called galaxies. This is a view of the Orion Nebula and the star forming areas in it. It's not a real video, obviously. Hopefully we'll get there in my lifetime and we can take this real video. But this shows these stars forming by gravity, and as the star collapses, it heats up and heats up and heats up until it ignites and becomes a hydrogen burning generation 1 star. And of course, all the stuff expelled in that explosion, just like in the Big Bang, created these little hunks of rock and these things that we call us, you know, planets. After a few million years, or hundreds of millions of years, this ash turned into life, turned into me and you. You know, and when Carl Sagan said we're made of star stuff, I mean, he's not joking. It's not a clever pun. It's reality. I mean, these stars formed, exploded. The ash left over is me and you. Well, it's really noisy here, isn't it? Great time for my neighbor to start using a leaf blower. Let's move on to the next slide. So this, what are the mechanics of this star formation and ignition? Well, Einstein discovered this in the early 1900s. Before that, people thought the sun was made out of wood or coal or some other nonsense. E equals mc squared. Energy equals mass times a really big number. In this case, the square of the speed of light. So inside the sun, these hydrogen atoms forced together by gravity are so hot they get to these temperatures in the 27 million degrees or so, and they fuse together in this process called nucleosynthesis or nuclear fusion. That's what created life. That's what made me and you. These atoms come together, they go through a process called the proton-proton cycle. The results are more protons being expelled and a helium atom and some neutrinos and gamma rays. The sun emits this energy in the form of light, really in every wavelength of the electromagnetic spectrum. The visible light part is really important for us because that's what we've evolved to be sensitive to. It's a fascinating thing. Here's a star that is just ignited. And as you can see, there's things still orbiting around this star, also because of gravity. You know, gravity is the #1 source of everything. These little chunks of matter swirling around this star after it's ignited are left over from the original explosion. Thank goodness. I hope they don't turn that on again. These chunks of rock and dust and material form together also by gravity and create this protoplanetary disk. And while these planets are cooling off, they're forming into rocky surfaces. And on those surfaces, after a little bit of electricity is involved, carbon-based life forms are formed, as evidenced by Simon and I currently doing a live broadcast to you, who is also a carbon-based life form. And there you have this beautiful blue marble we call the Earth. You know, strangely enough, this actually is a photograph, a real photograph from a satellite orbiting the Earth of the moon in the foreground and the Earth in the background. There's Saudi Arabia over there. This is awesome. You know, in Star Trek, every time they come home or they get to Federation headquarters at San Francisco, they always show these shots of the Earth, and everyone's just calm and everyone's really feels good to be home. I really hope we all get to see that view from space at some point. I think I might be too old, but we'll see. Oh, and guess what? All this other life also is on this planet. This is a yellow-crowned night heron that I took a video of recently, eating a crawdad. It's a bit choppy because this is a 4K video on a 10-year-old iMac, but this yellow-crowned night heron and that crawdad and that grass in the background all came from this nuclear fusion in the sun's core. I think it's an amazing thing to study. You know, life, I mean, if you want to talk about where did life come from, just look up at the sun, man. That's where it came from. By the way, all the colors you see in this photograph are a direct reflection of nuclear fusion in the sun's core. So the yellows on the bird's head, the red on the crawdad, all this is a direct reflection of the sun's core. I'm gonna walk over here and see if I can yell at these people real quick. So hang on. All right, hang on. Got that? No, I don't know why somebody chooses to use this 20-year-old air blower right next to me while I'm doing an internet broadcast, but believe me, you don't want to poke the bear. So here we go. This is our sun. This is the view from the Savannah National Wildlife Reserve, and it's taken through a Canon camera of the sun setting behind a paper mill. You know, this thing rises and sets every day, and it is just the most beautiful thing. Here it is coming over a cloud bank. This is a giant ball of hydrogen fusion 93 million miles away. And I can't tell you how many people I know that have never even looked at it, never even noticed it, or they're walking around with their phones and don't look up and see this. Look at this sunrise over the ocean. Beauty cannot be better presented than that. And this is the source of all light on our planet. Everything you've ever seen outside, appreciated, looked at, every painting you've ever seen in natural light, all of it is a reflection of this light that's created from simple vibrating atoms or protons inside the sun's core. There's not a more fascinating subject out there. This is the science of it in a very simple chart. Basically, protons are shoved together by gravity. They heat up really big. They fuse together and explode. You get the gamma ray, the neutrino, the positrons, the protons and neutrons, and a helium atom. Fascinating, fascinating, fascinating. The math behind it is unreal, but we've only got an hour, so we can't talk about that. Let me turn that volume down. Oh my God, that guy's still going. Okay. So this is what it looks like when it's coming through. Jeez. I turned the volume all the way down, but it's still pretty loud. It's the creation of a photon of light in the sun's core traveling through the many layers of the sun. Let's go to the next slide. So what are these layers called? Well, we've got the core of the sun where all the actual fusion occurs. Simon, can you give me a thumbs up? Everything working okay on that end?
Oh, sorry, say that again.
Everything working okay on that end?
Yeah, I'm just fighting with my scope.
Yeah, well, you missed my running over and yelling at the leaf blower guy. But it's a lot of fun. This is how we do it down here in the South. Okay, so.
Right, hold on, I'm still trying to set up the scope.
All right, mute yourself. There you go. So this core is where all the nuclear fusion takes place, and that's where it's super hot. The hydrogen's turned into helium. Everything outside of the core of the sun is just different layers of it cooling off. So we've got this radiative zone, you know, the names are self-descriptive, the convective zone where heat is exchanged. You've got the tachyline line between those two. Then you get out into the photosphere and the chromosphere, and then the corona, of course. Why do they call it the photosphere? Well, because that's what looks like the surface of the sun. That's where the light emitted in the sun's core becomes transparent. It goes from opaque to transparent at that point, and that's called the photosphere. Above that is what we look at with hydrogen alpha and calcium K scopes, and that's called the chromosphere. Chroma meaning color, the sphere of color, you know. Observing the sun. Well, this light, like I say, is created by vibrating atoms that are super, super hot. Subatomic particles are vibrating. Neutrinos, gamma rays are all emitted from this vibration. It's a fascinating subject. When we say hydrogen alpha and calcium K in solar astronomy, we're talking about wavelengths, names of wavelengths. Hydrogen alpha is the alpha line in the Balmer series of the hydrogen atom. Calcium K is the K-labeled line discovered by Fraunhofer in the calcium spectrum. What is a spectrum? Well, any object that's emitting light has a spectrum of some sort. The sun has a continuous spectrum all the way through visible light. The way you see that spectrum is with a prism. And that's how Isaac Newton first discovered this. Yeah, that guy did a lot, didn't he? Here's a spectrum. I'm showing it here, just like Newton used. And he measured the temperature of the different wavelengths and found that the red was cooler than the blue, basically. He totally missed the whole absorption line thing because his prism was not high resolution enough to see it. But when we're talking about absorption lines and emission lines in a spectrum, there's some laws by a guy named Kirchhoff who showed that when you pass a hot solid or a liquid or any dense gas that's hot, that's heated, when you pass that energy through a cooler cloud of gas, i.e. the Earth's atmosphere, for instance, or the sun's chromosphere, you know, the chromosphere is cooler than the source of the energy. So you get these absorption lines. And what are they? An absorption line is a portion of the continuous spectrum that is absorbed by atoms in that gas. For instance, the sun is mostly made of hydrogen. The sun's chromosphere is also mostly made of hydrogen. When you pass energy through it, cooler hydrogen absorbs certain wavelengths of that energy and creates a black line in the spectrum. If you look, the dark lines up here on this graph, you can see there's really thousands of them in the sun spectrum. But each one of these lines is indicative of a certain atom and certain magnetic field strength and certain temperature. But these lines indicate what atoms are in the gas that the energy is going through. This is how drug tests are done. This is how medical tests are done. This is how gas chromatography is done. Absorption lines are fingerprints of the atoms that are in the gas. When you look through a hydrogen alpha scope, you're looking at the hydrogen alpha emission line that's inside the absorption line. So what's an emission line? Well, when the hydrogen atom in the sun's chromosphere absorbs that energy from the core, it likes it. It goes, yeah, man, I got some energy, I'm good. Then it immediately re-emits it, okay? Continuously. I like it, re-emit. I like it, re-emit. You get these black absorption lines, and inside those absorption lines is a very, very tiny re-emission line. Why is it so small? Well, the hydrogen atom absorbs all the light from the core going to your eyeballs at the absorption line. When it re-emits the energy, it re-emits it in every direction, so not just at your eyes. So you only get the portion of the light that's re-emitted directly into your eyepiece or your eyes. That's why the emission line is so much smaller than the absorption line. The hydrogen alpha emission line is what you're looking through when you're looking through a Coronado H alpha telescope. Fascinating subject. This is an actual image, and Claude Plymate later can give you more information on this. He specializes in this. These are images of absorption lines in the sun's spectrum. So people are always asking me, hey, what color is the sun, man? You know, there used to be this argument at astronomy clubs where they'd say, oh, the sun's yellow. No, the sun's white. No, the sun's, who cares, man? The sun is every color. The sun emits light in every wavelength of the electromagnetic spectrum to some degree. The sun emits about 85% of its light in the yellow and greens. And we're most sensitive to yellows and greens because we evolved on a planet orbiting this star. But the sun emits light in every color. So what color is the sun? The sun's every color. It looks a little bit yellowish to me from inside of our atmosphere. From outside of our atmosphere, it probably looks white because it's so bright. But this is a picture of the absorption lines in the sun spectrum. And let me tell you, there's more information about the sun in this photograph than every picture of the sun ever taken by mankind. A spectrum of a star is where all the data is. When astronomers are doing actual astronomy on the research level, they're using spectroscopes. They're not using visual telescopes for the most part because, you know, it's pretty to look at and it's really cool, but it doesn't really give you any data. The spectrum is where all the data is, and that's why spectroscopy is so important. So here's a close-up of the hydrogen alpha absorption and emission line. And this image was taken through this device right here, which you can buy at Woodland Hills, called the Shellyak L High-Res 3 spectrograph. This is an actual photograph taken with a camera that I just stuck in the eyepiece. And you can look directly in the eyepiece and see this emission line anytime you want to. This is the hydrogen alpha absorption line in the sun spectrum, okay? And that's what you're looking at through an H alpha telescope. When the hydrogen absorbs the light, the electron jumps from the second energy level to the third energy level. And when it re-emits the light, it falls back down to its previous state. And that's where you get this emission line at 656.28 nanometers that we look at through our telescopes. What does that look like? Even closer, like this. It's a lot smaller than that, so you're not going to be able to see the emission line directly through the spectroscope, but you can certainly see it through the telescope, you know, because these telescopes have 0.5 angstrom or less resolution. That's pretty small. I believe an angstrom is the diameter of a hydrogen nucleus. So you're seeing half that much in the resolution. So it's pretty awesome. Here's an image of the sun in hydrogen alpha to your right, and you know, again, the diagram of where it is on the sun spectrum. And this is a real image taken through my Coronado Solar Max. I believe this was the original Solar Max telescope, showing hot and cool areas on the sun. If you're new to astronomy, maybe you don't understand that any photograph of anything in astronomy or anything else, any photograph, brightness equals warmer temperature, darkness equals cooler temperature. So when you look at the sun, you see these action items, or these active regions, I'm sorry, they're hotter. The whiter areas in this photograph are 2 to 3 million degrees Celsius, while the cooler areas might be 5,500 or so degrees. This is the sun's chromosphere in hydrogen alpha. Here's another couple images of the sun's chromosphere in hydrogen alpha. What's that big black dot up there, man? Is there a dust mote on my, oh no, wait, that's Venus. That's the planet Venus transiting the sun's chromosphere. I took this photograph from 9,000 feet up on Mauna Kea back in June of 2012, and it was a sight to see, let me tell you. But this is Venus in front of the sun's chromosphere taken in hydrogen alpha. And again, Venus, the side we were looking at, it was a lot cooler than the sun, so it looks darker. How about calcium K? Everybody's heard of calcium K. If you're into solar astronomy, no, the K does not stand for potassium. The K is the label issued by Fraunhofer when he labeled these lines. Fraunhofer was a German spectroscopist who wanted to have some order and quantitative analysis of the spectrum. So he labeled all the big lines different names. Calcium K is the K line in the sun spectrum. What creates the calcium K wavelength? Well, again, this calcium in the sun's chromosphere, there's only a tiny fraction of a percentage of it, but it's enough to see through a calcium K telescope. So the calcium atom says, yeah, I like it, man. I got me some energy from the sun's core. And then it immediately re-emits it, just like the hydrogen. I like it. Re-emit. When it re-emits it, it ejects one of its electrons from its outer shell and becomes ionized calcium. It also ejects a photon at that same time at 393 nanometers. Most people can't see it. Some people can. It's outside of the standard visible light spectrum wavelengths, but it's created by the calcium atom absorbing the energy from the sun's core and then re-emitting the energy over and over again. And there's enough calcium in the sun's chromosphere for this to produce a really fantastic image of the sun. It looks like crackle paint, if anybody's ever looked at it. This is images of the same Venus transit from Mauna Kea that I took through a handheld 80 millimeter refractor, a cheapie, you know. It took no time. You don't have to be a super duper skilled astrophotographer to do solar imaging. Pretty much anybody can do solar imaging if they just take a little time to learn it. The best news is you don't have to use any complicated photo editing software, let's just say, so you don't have those headaches. You just take a few hundred pics, put them together, and there you go. So in this image, you're seeing 393 nanometer wavelength. Again, the bright areas in this image are called plage, which is French for beach, because it looks like a sandy beach. The dark areas are cooler areas. One of them is Venus. The others are sunspots, which you're not going to see today on the sun, but you will when we get back to solar maximum. How about visible light, or as a lot of astronomers call it, white light? White light is all wavelengths of visible light that make it through our atmosphere from the sun. And this is probably the most common way people view the sun because it's by far the cheapest way to do it. You can get objective covers for any telescope to view the sun in white light. You can view the sun in white light through a pair of Charlie Bates Solar Astronomy Project solar glasses, like I'm doing right now. Okay. You can also get a little more advanced item that was discovered by John Herschel, William Herschel's son, called the Herschel wedge. You can put that on the back of a refractor. Woodland Hills has all this stuff. The Herschel wedge is just a really, really crappy mirror. It only reflects a tiny percentage of the light that's coming into the telescope. The rest of it is sent out of the back of the wedge. So what you see is just a really, really dim image of the sun, which makes it dim enough where you can make out the photospheric granulation and sunspots. Hey, I wonder what this looks like. Oh yeah, check that out, man. That's a diffraction grating over my over my camera. We'll get back to that later. I'm getting distracted. So visible light images is all the visible light wavelengths that are allowed through our atmosphere from the sun. And strangely enough, since we evolved as life forms on this planet, we are sensitive to all of these wavelengths. If you had evolved on a planet orbiting, say, a radio source star, you'd have no need to be sensitive to visible light because there wouldn't be any visible light. It'd be radio waves. So if you find an alien somewhere, you think an alien has landed, go see what wavelengths of light they're sensitive to, and that'll tell you or narrow down what type of star their civilization evolved around. The other wavelength that's allowed through our atmosphere is radio waves. They're hard to see because we're not sensitive to them, but visible light is easy to see. So white light images of the sun look like this. This is the same Venus transit taken with actually the same little 80 millimeter cheapie from Mauna Kea, and that's what white light looks like. Now, these features on the sun, a lot of people are really interested in it, and you know they've got all these proprietary names given by certain astronomers. Some of them don't make much sense, but whenever I set up a H alpha telescope and somebody looks at it and they see the little prominence shooting off the side, they always think that's a solar flare. Well, I strive for accuracy. A solar flare is a surface feature. This image in the background is from NASA's Solar Dynamics Observatory, and the image in the foreground is from my CalCMK telescope. This is a solar flare. Solar flares are super, super bright. They come in different classes, and like I say, this is a whole nother lecture. We're just going to touch on it. But the flare is a bright, bright, bright white object seen in the sun's chromosphere, sometimes seen off the limb of the sun. Prominences are a different thing, and we'll talk about those in a minute. How about spicules? You ever heard that term? Spicules are cool, man. I like it. When you're looking at the sun through an H-alpha telescope, if you look at the limb of the sun, you will see these hair-like structures that are about 500 miles or so tall. Now, this graphic, the tall, big stuff is not spicules. Those are solar prominences. The small stuff around the very edge of the sun is the spicule layer, and that's sort of like the edge of the chromosphere. It's all over the sun all the time. They're always rising up and falling. And when you have your H-alpha scope tuned properly, you will see a grayish ring around the edge of the sun's chromosphere, and that is the spicules. Spicules are very cool. How about prominences? Okay, well, here's a solar prominence coming out of an active region that also has some flares. The dark curved thing that's ejecting right now, that is an ejecting solar prominence. That was a very cool day on the sun, and I filmed all this with my telescopes too, and we're going to look at the resulting amateur photo. This is what it looked like through a $2 billion NASA satellite program on August 13th, I believe 2012, was it? But a prominence is a cloud of hydrogen plasma that's tracing the outline of magnetic field lines. Back in high school, when you dumped magnetic filings, or you dumped iron filings on a magnet, it would create these curved things around the magnet indicating the magnetic field structure. Well, that's what a prominence is also, except the sun's magnetic field structure is extraordinarily complicated. So you get all kind of strange shapes. On the bottom left of this image is also a solar prominence that's coming off the limb of the sun. And this is an ejecting solar prominence in the center. I'm gonna turn off my video real quick because I got some people walking up. Let's see, how do I do that? All right.
It's all right. I've just hidden you so they can't see you now.
Okay, very good. Now, this image is the largest solar prominence ever photographed from the Earth. This image was taken by a 12-year-old science nerd girl operating my telescopes at DragonCon in 2012. I'm not sure if this is going over as well on the internet, but the prominence in this image is larger than the sun. I mean, it was over 900,000 miles, and it streamed off into two different streams. This image was taken in CalCMK, and I do these live solars at DragonCon all the time. And we have just people come up and they take their own images. And it just so happened that this gigantic prominence decided to come off the sun while this little kid was operating telescopes. I was absolutely ecstatic. This one, I don't enter contests, but this won some kind of award at the Astrophotographer of the Year thing back then, and was hanging in the observatory there in Greenwich, England for a while with this little kid's name on it. I thought that was awesome. This is a solar prominence viewed in CalCMK, taken by my amateur telescopes. Let's see here. How about a filament? You've heard that term filament a bunch of times. A filament is the same exact thing as a prominence. When you see the prominence on the edge of the sun, it looks bright because the background is space. When you see the prominence on the surface of the sun, it looks a lot darker because, again, it's a lot cooler than the background, which is the sun. So a filament, again, is a structure of plasma being held aloft by magnetic field lines emanating from the sun's core. And they come in all shapes and sizes because of the disarray of the sun's magnetic fields. It's a fascinating thing to look at. These are filaments. They are the same thing as prominences. How about sunspots? Sunspots, man, they are really cool. They look like drains. Everybody's got their idea what a sunspot is. A sunspot is a magnetically active region that is just cooler than the stuff around it. That's it. On the bottom left is a photo of a sunspot taken through a little cheap refractor and a white light wedge in my driveway. 2014 is when this sunspot occurred. And by the way, this sunspot region with its dark core called the umbra and its grayish surrounding area called the penumbra. This sunspot region is larger than every planet in the solar system and every moon and asteroid combined. That's how big these things get on the sun. You're not going to see those today unless Simon's really worked out something great, but you will see them in a couple of years. This is the prime time to get involved in solar astronomy because imaging now or observing now, you really have to pick out details so that when Solar Max comes around, you're going to be a pro, man. These sunspots are visible through the glasses. They're visible through very small telescopes with solar filters on them. Very easy things to learn. Sunspots cause all kind of weirdness in the Earth's atmosphere. They can interfere with radio waves. They cause ham radio transmissions to go further sometimes or go shorter sometimes. It's a whole nother field of study. But this is a sunspot, a cooler region in the sun's photosphere caused by magnetic field interactions. We're getting close, don't worry. Hey, how about facula and granules? You know, I'm an American, so I only speak one language, and I don't know where facula came from, but it's a cool word. Facula are the bright regions in between the granules, and the more active the sun is, the more facula and brighter they are. I did not take these images, by the way. This is from the 1 meter Swedish telescope. The little black and white inserts up there are close-ups of solar granules, which look strangely like epidermis cells in living creatures. You know, I don't know what the correlation is there. But the granules and facula are the features that cover the sun's photosphere. And this looks like it's moving really fast, but this is not sped up too much. This is 4x speed. The granules and facula last 5-6 minutes, and then they fall back down. It's like a boiling water, you know, like you're making some pasta or something. The water boils, comes up, falls, and that's what happens on the sun's photosphere. And these are easily observable through even a cheapy refractor telescope with a solar filter on the end of it, which you can get at Woodland Hills. Okay, so how about these granules? This is a pretty cool image by my friend Emil in the Netherlands, taken with a little bit nicer telescope. But this is the planet Mercury passing in front of granulation in the sun's photosphere. You know, I'd like to say that the grayish area around Mercury is the atmosphere or something cool like that. But, you know, Mercury doesn't have an atmosphere, so it's just camera aberrations. But this is a super cool image of granules. Solar wind, term that's been around for a long time, discovered by folks in Denmark and the Netherlands up in the Arctic zone. Solar wind is a stream of particles that are actually leaving the sun. The sun emits all sorts of subatomic particles, neutrinos, gamma rays, protons, electrons. Jump whale phone call.
Wow, was that your phone?
Yeah, it's the Let Your Soul Glow song from Coming to America with Eddie Murphy. But yeah, I'm old. So the solar wind is a stream of particles that come out of the sun continuously. We live in this solar wind. The solar wind passes our planet, goes on through the entire solar system and beyond. And the solar wind causes havoc. You know, I'm a retired air traffic controller, and we have had many harrowing days caused by excessive solar wind or coronal mass ejections coming from the sun and affecting navigation, radio waves, high frequency transmissions. When it hits the sun or the Earth's atmosphere, our magnetic field battles with the sun's solar wind, and all kind of strange things happen. You get the aurora borealis in the North Pole and the aurora australis in the South Pole, and you get all these cool lights in the sky. What do they look like? Sort of like this. This is a photo I took with an iPhone in Edmonton, Canada at a lecture I was giving. And this is like a 2-second exposure. It's amazing how bright these things were. I saw them in Australia and I saw them in northern Canada. I've never been to Iceland or Norway, but I'd like to go check that out. This is a little bit closer photo with a DSLR, and you can still see the sun or the stars in the background of these aurora, and they dance around like little veils in the sky. It's really awesome, and you get a bunch of different colors too. You get purples and greens, and all these different colors are caused by different atoms in our atmosphere interacting with the energy from the sun and the magnetic fields from the sun. So those are what aurora look like. This is an image I did not take from, I believe, Norway. And this is, of course, 5 to 10-second exposure of aurora. Speaking of the solar wind, this is a NASA-generated graphic of an event that occurred in July 2012. Notice that gigantic coronal mass ejection. Okay, let's watch it again. One of them came by the Earth on the right there, fairly common size CME. And then, boom, that one was sensed by Stereo A, which is a NASA satellite. It was a very powerful coronal mass ejection. And I'm not exaggerating when I say the only reason we're still here is because we happened to be on the other side of the sun at that time. And this event was well documented. The CME went out towards Jupiter and was very strong. Let's look at a little bit closer view of it. There's where the Earth was. So we got that CME, which was pretty strong and caused problems on the Earth. But this one, boom, that is a massive coronal mass ejection. And this is all mathematical data from NASA.
Just out of interest.
Yes, sir.
Do you know if that particular CME that hit in that direction also affected Stereo A? So that's why it's not working right now, I'm assuming, because they lost connection with it.
It damaged it beyond repair, and it lasted a little bit longer, but it was never the same after that. And this occurred on July 12th of 2013 or 12. I forget. The last slide had the date. But I show this to people, and they're like, "Oh, you're just making that up, man. You're exaggerating." No, I'm not. We are a tiny, tiny little pebble of nothing rotating around the sun, orbiting the sun. We haven't been destroyed yet by CMEs or by other things coming from the sun because of the fact that we're so insignificant and so far from the sun. We happen to be on the other side of the sun when this occurred, luckily, or things would be very different right now. Nobody would be worried about the COVID virus had that came to us. Solar maximum is coming again in 2 or 3 years, and I really encourage everybody to study this through the NASA SDO site, or even NASA SOHO still has a bunch of data. That's an older satellite that was retired. But these things really affect life. And as an air traffic controller, I saw the real effects all the time in my job, but they never made the news media, because nobody got killed immediately from these things. But, flying a commercial aircraft is probably the most radiation exposed job on Earth. And there's all sorts of protocols and things that you do as an international pilot to prevent yourself from being irradiated by solar wind. That's another lecture. Okay, so solar imaging, we've already talked about. These are solar telescopes in different wavelengths. These are the IMAX that I used with the students when they took their own solar videos. These are actual, screenshots of us imaging the sun in reality. That's a solar flare right there, by the way, that big white stuff emanating out of those 2 sunspots. There's the colorized version of it. These are all real videos that you can take with very little. It doesn't take years to do this. It might take a couple weeks just to get used to the equipment. But you can easily take these images from your driveway. It doesn't matter how light polluted your skies are because the sun's bright enough to overcome all that. This is an image of a white light photospheric shot through a GP telescope. It doesn't take much. Okay, and we'll colorize this one in just a second. Super cool, man. I think coming up is a calcium K image. And Simon and the gang at Woodland Hills will be happy to set you up on any budget, really. I mean, this isn't really about selling stuff on this video. I'm trying to make you aware that it is extraordinarily easy to become a world-class solar imager. And you can ask anybody who's referred to as a world-class solar imager how hard it is, and they'll say nothing. It doesn't take anything. Just a little practice and the right equipment. Solar imaging is very easy, and it's a great hobby to get into.
You know, the funny thing, I'm going to add to this.
Please.
Solar imaging to me is actually a lot easier than doing nighttime imaging, because it's literally instant results because you've got nothing but light.
I totally agree. And, you know, I'm kind of famous for the phrase sissy astronomy, referring to nighttime astronomers, but 90 seconds, you can capture all the data you need. And in 3 minutes after that, you can have a Facebook ready photograph that is world class of the sun. These guys at night will sit out for 6 weeks, maybe gathering data on something, you know, a deep sky object or whatever. And once they gather the data over 6 weeks, then they got to spend another 3 weeks processing the data. And listen, I got nothing but respect for these people, but I am a instant gratification kind of guy, man. I can walk out here, turn on my scopes, take images in 3 different wavelengths, have finished products within a half an hour, and then I'm off, man. I'm done. So if you like astronomy and you want to do something cool, and it's also in the daytime, by the way, so you're not freezing, you're not avoiding wild pigs in the woods, you know, you don't have 600 cables and 5 computers that are going to break. It's just a very, very cool, easy way to get some real astronomy, research grade astronomy in with you and your kids if you want to. It's a wonderful, wonderful way to get involved in astronomy. This image, by the way, is 3 separate images of the same exact active region on the sun in white light, calcium, and hydrogen alpha. So these are all taken at the same time of the same sunspot group. And these are the different features you see. So it's totally different in these different wavelengths, because the calcium wavelength, 393 nanometers, is much, much hotter than the hydrogen alpha wavelength, which is cooler than the photospheric wavelength. So it's a great, great hobby to get into. Here's some more cool photos of a solar flare in different wavelengths. This is the same active region in hydrogen alpha on the left and calcium on the right. Notice you don't see the filament at all in the calcium image because it's too cool. It's not emitting any energy at 393 nanometers, so you're not going to see it. On the left, you don't see the sunspots very much. Really, you're not seeing sunspots at all in hydrogen alpha. You're just seeing the absence of 656 nanometer light, because sunspots don't emit wavelengths at 656 nanometers. So you're seeing the absence of hydrogen alpha wavelengths in the area above the sunspot. This is another cool image. Me and a guy named Alan Friedman, back in the early 2000s, mostly Alan, developed this cool imaging technique where you image the disk and then you image the proms. You go through and you invert the disk, copy it, stick it on top of the prom image, and then you feather the edges so you don't get that nasty ring around the edge. But this kind of took off as the main way of imaging the sun. Alan's images are way better than mine because he spends more time on them. But this is an image that I can take. I can have this image done today in less than 3 minutes, from capture to Facebook. So people are always saying, oh man, that is a great image. In fact, I believe this image is used on the current Coronado banners. But there's nothing to this, man. If you can press a button and pick up a telescope, you can do this in 5 minutes or less. Hey, check it out, a drone flying over the sun. You would not believe how incredibly difficult it was to get a phantom drone to hover in front of the sun and both of them be in focus. I took this from the driveway also. This took about a half an hour. Here's an image of the sun in calcium K using the invert the surface technique and then copy the surface onto the prominence image. Prominences in calcium K are very, very difficult to capture, but they are there, and they're always different shapes than the hydrogen alpha prominence. If you look at the prominence in the H alpha scope, you're seeing only the 656 nanometer wavelengths emitted from the prominence. If you look at it in a calcium K scope, you're seeing the same structure, but the hotter parts of that structure. So there's always something different to see in different wavelengths. There's a white line image of the sun. I thought this sunspot group was kind of shaped like the Big Dipper, so it was cool. Here's the same exact region in hydrogen alpha. And here's the Venus transit. All right, so like I say, I was at Mauna Kea in front of the infrared telescope shooting all these photos in 2012. It was a very cool experience. This is a Venus transit compared to the Mercury transit on the right. Venus is easily visible in front of the sun because it's much larger and much closer to us. On the right, you really can't even see Mercury. I mean, unless you know exactly what you're looking for. It's in the lower third in the center of the image. It's not the sunspot. It's about 1/10 of the size of the sunspot. Largest prominence ever recorded from Earth. This is a video. I'll just let it play for a minute or two and you guys can walk around and get a drink or something. But these images were all recorded through my amateur telescopes of a solar prominence that occurred in 2013. That was almost 1.5 times the diameter of the sun. And this is what it looked like in real time through my telescopes.
I'm guessing you're getting close to the end. This thing's huge.
Yeah, man. I mean, the sun's not even in the image, if you haven't noticed that yet. That's
No,
how
I
big
know.
the prominence was. You know, it was over 1.5 million miles in length and just went on and on forever. And Simon, I'll tell you, because you're an experienced imager, imaging prominences in calcium light will give you much larger, much bigger prominences because
Oh, yeah.
they heat up as they go through the sun's corona, and the hydrogen alpha emissions just go away in short order in the chromosphere. But the calcium emissions continue for hundreds of thousands of miles out from the sun. So turn up that gamma and you'll see them.
By the way, just so you know, I've got the live scope up and running.
Very good. I'll let you control all the production, and we're just about done here. And while you're showing yours, I'll get mine going because I'm at a point where I can probably see something. So this is an International Space Station transit of the sun. No, the space station is not orbiting the sun; it's orbiting the Earth. And it's kind of hard to see that, but you can catch the silhouette of the space station going in front of the sun if you monitor CalSky or any of the other predictive websites. And here's a still image of the space station passing in front of an active region with sunspots in calcium K. This image was nothing to take. You just have to be there at the right time, shoot a video, pick out one of the frames, boom, you're on Sky and Telescope that month. How about that? This was taken in 2009, back when it was just Terry Legault and me doing these, and they're really easy to do. And that is, you would not believe the conspiracy theories that were generated by this image on social media, alien spacecraft, etc.
Well, trust me, I've heard it all. TIE fighters, you name it.
It does look kind of like a TIE fighter. This is me and Greg People, who's one of the early pioneers of solar astronomy, at the Space Shuttle Discovery dedication ceremony in Washington, D.C., where they took the Discovery in and put it in the same museum, Smithsonian, as the Enterprise. And they drove these shuttles out and parked them nose to nose on the runway there. And me and Greg had our telescopes set up and people were walking over looking at stuff. And I don't know, I just think this is a cool image. Of course, the calcium K image of the sun is superimposed. It's not real. But when they got done with this event and we were putting away our telescopes, you could have walked right over to the space station or the space shuttle and just climbed up into the cockpit if you wanted to. There was zero security. We were near it and walked over there, and you could still smell burned ceramic around the Discovery. Of course, the Enterprise never went to space, but the one that was in orbit, you could still smell burnt ceramic on it, which I thought was just an indelible memory that I'll never forget. I appreciate you guys listening to this. By the way, this is an image of the sunset in Australia from the Outback in 2014. And this is not enhanced or touched up in any way. This is just what it looks like in Australia. It's a wild place. But I'm going to let Simon do what he wants to do here for a couple of minutes while I see if I can get the sun in our telescopes. And listen, I'm really grateful that you guys paid attention to some of this presentation. If you want to join our Facebook group, it's Charlie Bates Solar Astronomy Project. We also have a group called Sunlit Earth, which is more the terrestrial visible light wavelengths in nature, like wildlife photography, birding, etc. And we are a nonprofit 501c3, and there is a donation link on there, yada, yada. But thanks, Woodland Hills, for the opportunity to give this. And I am going to set up my telescopes now, if that's okay with you, Simon.
Yeah, totally. So if you want to jump out of screen sharing, there we go. Oh my God, there's a great big picture of me.
Yeah.
That's a shocking image, isn't it?
I was shocked also.
All right, so what I'm going to do is, let's see if I can make this smaller. Oop. I'm going to try and get as many things on the screen as possible.
I'm going to mute my...
All right. Did not want to make that full screen. So right now you are looking at a prominence that is on the sun. Let me just try and get this as big as possible. And just to prove it's live, there's me adjusting the scope. And then I can play around with all these different settings to make it show more or less. If you guys actually want to see the surface details, we can actually just play around with the histogram. So right now we are actually in prominence mode, because I actually have a Quark Gemini, which is basically a 2-in-1 unit. Jen Winters, who's going to be coming on a little bit later, she will be going through how this actual thing works, so you guys can get a better understanding of it. She probably can explain it way better than I can. But right now we're in prominence, and this is a hydrogen alpha. And you can actually see there is a prominence today, which we were getting nervous because it was quite boring and dull when I was looking at the sun for the last couple of days. And I'm like, oh my God, I hope something's going to happen. And it just went blank. And I was like, uh-oh. So finally, there's something actually coming up. It's actually quite a big thing, which I will go through in my talk later on today. And I'm watching Steve's. Oh, look, there's an Amazon truck that showed up. I wonder if there's anything cool in there for us. Could be more solar goodies. All right, so let's go through a couple of questions if we still got questions going on. GeoAstroRV says, can you talk about software using to the quickest response for public solar imaging? I can answer that as well. Obviously, the program that I'm using is called SharpCap. It's the program that I prefer to use. You can use any other programs like Firecapture and things like that. I do not recommend any of the other software like MaximDL and stuff like that, because they tend to be more for nighttime imaging. So the best programs to use is something that gives you a live feed of some description. Ideally, you should really use CMOS cameras over CCD cameras when you're doing solar, primarily because CMOS cameras tend to have higher frame rates. Now, this particular camera that I'm using is actually the 174, and you'll notice that right here, I get around about 120 frames per second, but admittedly, I am actually limiting the field of view. Even on its full capture, I get around about 60 frames per second. So it's pretty, good and almost near real time to a certain extent. So yeah, the best programs that I've used is SharpCap or Firecapture. Oh my God, I'm watching this guy back up. Oh, I can see Steve. He knows what's going on. I'm sure you can see down in the corner. It's like down there. The Amazon truck is. Oh my God, that was close. But that's not what this is about. So anyway, unfortunately, I'm not very well polar aligned because I literally slapped this out onto the deck and just set it up in like lightning speeds. I can't show you where the scope is because it's outside. I'm completely somewhere else in the house. But right now, seeing it's actually pretty good. We're actually getting pretty good details on these problems. Let's see if we can get a closer look at it. So there you guys are. We're actually looking at the sun live. So let's have a look if there's any other questions. When was that transit? So obviously John's answer, that was November 11th, 2019. What filter were you using? I'm not sure what that reference is. It's probably something that Steve Ramsden was doing. And he's probably messing around setting up his scopes, because here's the great thing. He has multiple setups. He has white light, calcium K, and hydrogen alpha. You're looking at the prominence right now in hydrogen alpha. And I actually have this turned up to be able to see prominences right now. And I control that through the histogram. There's multiple ways you can do it. You can actually just reset the histogram and then just bump up the gain. I mean, there's multiple ways of doing the same thing. So the more gain you crank into it, the more apparent it becomes, but the more the surface of the sun starts to blow out. It depends on what you're doing. Usually when I'm doing a capture, I prefer to mess with a histogram, because here's one thing that you probably didn't know, and again, I will go through this later on today, is the histogram, when you're doing a live recording, is not affecting the final image, because this is just a preview. If I was to modify the gain in the middle of an imaging session as I'm recording, the gain actually also gets recorded. Is it also possible to see prominences depending on the bandwidth mode? So obviously with the Gemini, there's two parts to it. There's the chromosphere and the prominence mode. It's referencing the angstrom bandpass, so it's 0.7 versus 0.5. Oddly enough, even in 0.5, you can still see prominences. They're just not as obvious or not as bright. I think there is one other prom somewhere on the sun right now. Let's see if I can dig it out. Just gonna go check out a website real fast to see where the other one is. If you'll excuse me, I need to get a good image. Oh wow, there seems to be 4 of them. In fact, let me just show you this real fast. So this is actually a live view from Daystar. There's a bunch of telescopes set up all around the world that continuously image in hydrogen alpha. And the one that we're looking at is this one up here. So it's that one there, that's the one we're looking at. And you probably notice that it's probably facing the wrong way. It's only because I haven't done flip. You know what, just for your sake, I will. So what are we doing? We're gonna flip. There we go. So now it's facing the right direction. So you can see it's somewhat similar, but it's still in the wrong direction. But it's okay. We're all messing around. So now if you notice that there's a lot of wiggling going on, that's actually seeing conditions. It's not optimal seeing, unfortunately. I've got a 3 out of 5, give or take a little bit here and there. You know, oh, here we go. When you zoom in, when you zoom like that, is this just for display, or does it also change the zoom? When I'm zooming in like this, it's just for show only. It's just basically me limiting the window, that's all. So if I was to zoom back out at 50%, it doesn't affect the recording in any shape or form. So you can just keep on doing that. I'm just doing this so you guys can see a better view of the entire thing. Hopefully I don't have to run out and constantly refocus, because I don't have a motorized focuser attached to this particular scope, only because depending on seeing condition, it also determines which scope I'm also going to use. If the seeing conditions are nowhere near as good as they need to be, I tend to use a smaller aperture. So bad seeing, smaller aperture. If you've got good seeing, bigger aperture. So I can use a 150. So it looks like Steve's returned. All he has to do is unmute himself. There he is.
Sorry about that. As you can see, I had a Amazon package delivered. Oh, let me get my mouse here.
Looks like he was back into the scope at one point.
Yeah, I had to stand there and prevent that. You know, I live in a really tight in-town neighborhood in downtown Atlanta. And one of the reasons that I was only able to do live broadcasts during a certain time frame is because the buildings are so tall around me. So I get about a 3-hour window every day where I can do all my solar astronomy. And that's enough for about 10,000 photographs for you nighttime.
Much, yeah.
So I'm watching the YouTube feed, which is delayed a little bit, and I see you had a pretty good image of a prominence on the sun's chromosphere.
Oh yeah, it's kicking off a bit. There's more than one prom. This is just one of them. This is the one that's actually showing up the best, but seeing is just all over the place. So it's very, I mean, every now and then we'll get that moment of clarity. Like right now, it's actually pretty good, but it'll just drop off in a moment.
Are you still screen sharing? So they're seeing it still?
It's not, well, yeah, I mean, I'm still screen sharing it,
Yes.
but they can see us and I can see them, and well, actually,
And you
I can't see
notice
them.
this is a good example of, and you'll get into this when your solar imaging talk later, but you know, a lot of people when they're solar imaging, they begin by trying to make the preview image look like the finished product. And when you're doing that, you're really not capturing the majority of the data, because I'll see people try to darken the disk down to make it look super high contrast. And when you capture it in that manner, you're not capturing all the data. You've got your gamma turned up to a good point, but you're not saturated. It's way better to capture the data with higher sensitivity and then bring it down in your photo editing software. Boy, it really looks good now, even on my screen out in the sunlight. That is a fantastic image of a prominence.
So this is actually the image with the histogram as is. So from an exposure standpoint, this is set for good exposure. This is a common mistake. Again, I will go through this later on in my talk. This is actually a big common mistake that a lot of people have made in the past when they get into solar imaging, is they think that nothing is there. And if they can't see it, it's not being captured. But like I said, when I go through this, I'll explain where you can actually see everything, because in reality, I can actually modify the histogram.
Yeah, turn up the gamma, man. That's always my advice, you know.
There it is. Ooh, and it's running away.
Yeah, that's pretty cool. And I can't tell what software that is, but what kind of camera are you using there, Simon?
This is the 174 monochrome.
Right. And that's another point you'll touch on later. Imaging the sun with a color camera is a waste of your time, and you need to be using a monochrome camera because your telescope is only showing monochrome, one wavelength of light.
GeoAstro, again, I'm going to go through all of this in my talk later on today. Otherwise, I'll just burn through my content. I mean, I don't mind repeating myself, but I will answer that question for you guys. Does living near a large city also affect seeing and atmospheric stability? Oof.
It affects atmospheric stability for sure. Seeing, yeah. My point was that it's much easier to image the sun in an urban environment than it is night sky, because I've got a C14 that I can put in this same spot, and even with a hyperstar on the C14, I have to get 30-40 second exposures to see anything, whereas it would be a 5 or 6 second exposure out in the country. We do have a farm up in North Georgia that I can go to for nighttime SISI astronomy, nighttime astronomy. But imaging the sun from downtown Atlanta has produced every image I've ever put out on the internet, and people have been pretty satisfied with them. So I would say if you're stuck in the city, this is the way to go, which sort of leads me into something I was going to do also whenever you want to fit it in, is talk about some of the products for introduction to solar astronomy that you can get from telescopes.net if you're interested in that.
So do you have a live view of the sun right now?
No, because it clouded up again.
Oh, of course it did.
As soon as I got it, just a blurry view of it in the H-alpha scope, more clouds came in. So it looks like I'm not going to be able to provide that at least for the next hour. But I will stand by until the end of our time frame. Just in case.
We've got plenty of time.
Yeah,
so
man.
I just saw another question, and I just lost it. Oh, never mind. It was the same question. So here's another interesting thing.
Yes, I am married. That's usually the first question I get, being so handsome. Are you married? Are you available? Yes, I'm married. Okay, go ahead.
So here's an interesting thing that a friend of mine, his name is Stephen Pizzo. He is on Instagram as Long Tech Elsewhere or Long Tech Anywhere. He's the guy that does the 6K images of the sun. And if you go check out his Instagram, his stuff is like literally mind-boggling. It's unreal. I can show you guys his stuff later on. But more importantly is he discovered something very, very interesting. Now, he lives in the middle of Los Angeles, specifically the San Fernando Valley, in a place called Encino. So if you guys live here in LA, you probably know where Encino is. And he lives up on a hill. But the interesting discovery that he made was when you're doing any type of solar imaging, in order to keep a calm column of air, for a lack of a better description, is to actually image over a large body of water.
Right.
And this is like a phenomenon that he kind of discovered where he was out somewhere near Borrego Springs, I believe. And there is a lake there, or the Salton Sea, and they were imaging directly over it. And they had some of the best seeing that they've ever seen. But according to the charts, it was supposed to be bad. Now, he didn't know about this phenomenon at this time. So, they just carried on imaging. And then they set up in a different location where it said it was going to be good seeing, and it was dreadful. The heat was rippling off of the desert floor, and they couldn't explain it. And then till he actually did a test. So now, where he images is directly over his swimming pool in Encino. And this poor swimming pool does not get used as a swimming pool. He keeps it clean and everything, but he has his entire solar rig with his 300 millimeter or 230 millimeter solar scope that hangs right over the swimming pool on this great big jib arm,
right,
with a $20,000-$30,000 camera stuck on the back of it. But the images he gets is just unreal.
Well, solid color objects reflect more sunlight and create more heat waves, and water does not reflect much sunlight. So it only makes sense that if you're imaging over any cooler object, that it's not producing as many heat currents above you. And I have heard people talk about this before. Unfortunately, I don't have a body of water here.
To test that, right?
To test it.
Little kiddie pool.
But you can see that yourself by just looking, when it's colder, the skies are clearer and the seeing's usually better. So when you're standing over a body of water, it's not reflecting as much sunlight, and it's not heating up the air above that body of water. So that makes perfect sense to me. And I can't wait to see that in your presentation. I'm interested to see this guy's work.
Yeah, one of the other things that I've tested because of that phenomenon is putting everything on a huge sheet of carpet. And other than vibration dampening it, which works actually, believe it or not, does it make any difference? No, it doesn't. Zero. Absolutely squat.
Something interesting also that I've found I get these questions all the time, and people want to know. It's so easy to do this that it's really tough for me to stretch it out to a half an hour. But, people are used to taking 5,000 frames for a planet and stacking 20 or 30% of them, When I was in Australia, a single frame was always better than the stacked video. Here in Atlanta, I might stack 3% of 500 frames. Things on the sun are moving pretty rapidly. So if you take a 3-minute exposure with, 10,000 frames, you're going to get a blurry mess if you stack really any significant portion of it. So again, I don't want to cut into your thing, but with my point gray grasshopper cameras, they're 6 megapixel cameras. If I get 3 decent frames, that's plenty enough for me to stack out of 500 to get a fantastic image. You want your frames to be close together time-wise, because these convective cells in the photosphere don't last more than 3 or 4 minutes. So if you're stretching it out over 10 minutes, you're taking pictures and mixing together phenomena that weren't there at the beginning or the end of the video. But there you go. I might.
Sorry, I'm taking an allergy tablet because my nose is killing me.
What's your cat's name? Sunspot.
I should call her the black hole, actually, because she literally looks like a black hole when she's in front of a camera. In all honesty, and people are going to hate me for saying this, I don't actually name my cats because in reality, a cat does not understand what you're saying.
Right.
And even if you were to call the cat by its name constantly, it's not responding to the name, it's responding to your voice.
Intonation.
So, yeah, the cat knows when I'm referring to her. And it's the same thing with dogs. There's a guy with a great video where he screams niceties to the dog, and the dog is whimpering away. But then he does it in a very, very soft, calm voice. But he's absolutely insulting the dog, and the dog is wagging its tail and everything.
Yeah.
So people have to understand it's the tone of your voice that determines the response of majority of all animals.
Totally agree. And my Sunlit Earth, the American affiliate now, Sunlit Earth, really is all about wildlife and behavior and how wavelengths of light affect animals and plants. And I've really been happy that I've been able to take a lot of training in animal rescue and reptile and mammal and avian rescue, where I go out and I find these injured animals and go get them and treat them on site sometimes and take them to rehabbers and all that. But learning about these animals is a fascinating thing for me. Sunlight is all around us all the time, and this image you're showing your viewers is where the light is leaving the sun. But when you're looking at your cat outside, or you're looking at a bird or something, you're seeing that same light when it got to the earth. And to me, light is the fascinating thing about this, and how is it possible that if I'm riding a beam of light and another beam of light is heading the opposite direction and we pass, our relative speeds are still the speed of light? It's not twice the speed of light like logic would dictate. These kind of things go through my mind all the time, and I'm always wondering about light. So that's my
let's not get into that physics debate. This will open up a whole can of worms. I've had these conversations with multiple people at different levels of understanding, and the biggest problem here is trying to explain it to a layperson, as I call them. It gets lost real fast.
Yeah, I really enjoy the multiple dimensional aspect of this argument, and how it's it's that way in our known dimensions. But when you increase up to 10 or 12 dimensions, then it makes perfect sense mathematically after that. But you lose a lot of people with that conversation. And like later on this evening, I'm doing a presentation of a different program for a Brazilian astronomy club that I financed and started back in 2014. And they have to translate into Portuguese while I'm giving the presentation. And I don't speak Portuguese, but I'll say two sentences, and then the translator will translate those two sentences. It goes on and on, back and forth like that the whole time. So you can't give a lecture of any complicated information because, one, the translator doesn't know the terms usually, and one sentence at a time. You think it's boring just to listen to it in English. You should try to to break it up into one sentence at a time with a break in between each sentence. It's really mind-boggling how much you lose doing that. So it'll be a real simple presentation. I'll point up and say star, hot, sun, thank you, obrigado, and that's it.
I'm just literally scooting around the sun and trying to spot the other prominences. They're not nearly as good as the one that we currently are looking at right now, unfortunately.
Let me see if I can find
let's talk about products while we're at it.
Okay, seeing if I can find a movie that I've recorded of solar on this computer, but it wouldn't be live.
Oh, no, there you go. So, products. What have you got hiding in your collection of goodies?
Let's talk about the PST, shall we?
Yeah.
Anybody starting in solar astronomy, the Coronado PST is the way to go. If you don't have anything and you want to start out doing some cool solar astronomy, this scope is a hydrogen alpha etalon. It's about 20 millimeter etalon inside the body of this telescope. It's a 40 millimeter simple refractor. And I don't know if any of you have already figured this out, but Jesse Ramsden is was a famous British astronomer who invented the Ramsden eyepiece. And he is my 7th generation grandfather. So it's in our blood, but the Ramsden eyepiece is only good for monochrome viewing. This telescope is designed for monochrome viewing. So if you point it at anything else, you're going to get chromatic aberration. But for a single wavelength, it's superb. The Coronado PST contains a prism, a finder scope, obviously an eyepiece tube, and a focuser. And it's light enough that you can just throw it in your camera bag and stick it on a photo tripod anytime you want. And with this telescope, you point it at the sun and you can see the sun's chromosphere. And you can also image the sun's chromosphere. I've seen some of the best images I've ever seen taken through a PST. So if you want to give this a try and get going with solar astronomy, I strongly suggest the Coronado PST. Yeah, I think it's about $600. I don't know. It's under 1,000, which is cheap for this field. And I'm sure Jen will be on later with the quarks, which are also a fantastic option. But with a quark, you need a telescope and you need a plug. With the PST, you just stick it on a photo tripod and point it up, and there you go. The father or grandfather of the Coronado PST is, hang on a minute. Yeah, it's heavy. The Solar Max 3 90 millimeter. Whoa, I'm just kidding. I don't even know if I can stand back far enough to get this whole thing into view. But the Solar Max 3 is the absolute flagship of the Coronado line right now.
It's like a missile launcher on your shoulder there.
Yeah, it's funny because this is exactly the same size and color as a 5-inch Navy shell when I was in the Navy. And I've transported these all over the world. I've given away about 20 of these. And I always get the same looks in customs. You know, they're like, holy moly, what is that? The Coronado Solar Max 3 is the flagship. There is not a better scope on Earth for visual solar astronomy. It uses a tilt-tune system whereby the etalons, these are 2 etalons, on the exterior of a 90 millimeter doublet refractor, basically. The etalons are tiltable, and when you tilt an etalon, what you're doing is you're changing the angle of incidence of sunlight to the etalon, and you're changing the passband that is allowed through the etalon. There's also a rich view tuning on the etalons, and that changes the actual space between the 2 elements of the etalon. So when you have both of these etalons on this scope, you're getting about a 0.6 angstrom resolution, 0.5 angstrom resolution, and it is unbelievable to look at. And something about tilt-tune telescopes, they produce uneven illumination on the disc, which is not super advantageous for full disc imaging, but it really blows away the image for visual use because our eyes compensate for that, and it creates a very 3-dimensional view in the eyepiece. So if you put this next to one of the competitors that uses, say, pressure tuning or heat tuning like Daystar, you get a flatter image with those scopes for imaging, but it also looks flat. The Coronado line of Solar Max scopes was designed to be visual solar telescopes. You can image through them, of course, but you are not going to find a more pleasing 3-dimensional depth of field view than a tilt-tune solar telescope. So on the other side of this, I hope I don't drop this. I have dropped one in my driveway once, and it made a really alarming sound, a $10,000 alarm. But anyway, the blocking filter is another integral part of these telescopes, because once you get the sunlight through the etalons, you get a spike at 656.28 nanometers, but you also get a lot of spikes on either side of that also. And what the blocking filter does is it's basically a nighttime hydrogen alpha filter with about a 3 nanometer bandpass. It blocks all the additional spikes on each side of that center line, so that when you look through it, you're only getting the center line and a totally black background. That's the goal. And that's what a blocking filter is for. So when you're using these tilt-tune telescopes, you have to have the etalon and the blocking filter. You can't use either one of them individually to look at the sun, of course, because it's dangerous.
So I got to reiterate this because everybody always says this. Even with a white light filter, you still cannot use a hydrogen alpha filter. You have to understand that hydrogen alpha filter used for nighttime is not quite the same as the ones that you get in blocking filters. They're not remotely safe. So please, I'm getting fed up of answering that question, especially in the store when I have people arguing with me. Do not use these things, as in like your H alpha filter, and then go look at the sun. You will regret it.
Yes. Well, and you'll also explode the filter within about 30 seconds. Interesting thing about filters is when they heat up, they expand like everything else. So if you shine that focused sunlight beam on a nighttime filter of any kind, even a solar filter, which they used to sell for eyepieces back when I was a kid. Prolonged viewing through any filter with a focused sunbeam will cause the filter to explode. And that's how my first telescope went down the drain. And I strongly suggest not doing that. So the last cool thing about this Coronado scope is the solar finder on here. It's called the Soul Ranger or whatever. And, you know, people don't understand it's really difficult to aim your telescope at the sun, because when you look down the telescope, it's so bright, it blinds you, especially if you're using eyeglasses, which concentrate the light even more. This Soul Finder has a opaque back on it. Okay, and my neighbor's about to pull out, so we're going to get some noise. The light goes through the front of the Soul Finder through a little pinhole. It's just like a pinhole viewer for the solar eclipse, and it produces just a dot on the opaque image here. I'm going to mute me real quick while this guy backs up.
No problem.
So you don't have to struggle with that.
Sorry, I'm just going to make sure somebody didn't come through my front gate as well. I just heard the gate. Looks like I might have a delivery of something. Yeah, I'll worry about that later.
All right, so he's gone. Yeah, it's very busy here at the Ramsden household. Let me see if I can get this scope back in the box without dropping it. If you hear a really loud bell tolling,
that's you dropping the scope.
Yes. And,
I hope not.
I did that, like I say, one time when I was wheeling out a wheelie bar that had 2 of those on it on a Celestron mount, and I hit a rock in the driveway, and they both tumbled to the ground and broke the etalons, and it was a very unpleasant day. All right. There we go.
Yeah, I got to keep monitoring my scope from a temperature standpoint, because once my camera hits a certain temperature, it's usually time to stop for me.
What kind of setup is that? Come on, man.
Well, put it this way, the refractor that I'm using is also my nighttime refractor, so I don't want to ruin it.
This is a diffraction grating that Rainbow Symphony makes. Rainbow Symphony is the world's best solar glasses, which is they're a sponsor of the Charlie Bates Solar Astronomy Project. This diffraction grating, if you look at anything, will show you the sun's visible light spectrum. I've handed out over 1 million of these around the world, and you know, they're cool, man. They show you a first and sometimes second and third order spectrum of the sun. They also make that in a pair of glasses. This is a diffraction grating pair of solar glasses. Okay. And then you can get just your straight up eclipse glasses, they're called, but they're really for looking at the sun anytime. And I'm happy to send these to anybody who wants them for free. Just contact us through our Sunlit Earth Facebook group or Charlie Bates Solar Astronomy Project. Farrah and Woodland Hills are authorized resellers for Shellyak line of products, which Shellyak is I think it's the best product on the market. I love my Shellyak Hi-Res 3 spectroscope more than any other device I have, I think. This is a handheld version of that spectrograph, spectroscope, whatever you want to call it. And what this is a spectroscope. It's got a slit, just like a real spectroscope. You hold it in your hand and you just look through it. And I can't tell you how many times I've used this in the field. Right now, I'm looking at a 300 dots or 300 lines per inch visible light spectrum coming from the sun. I can see the hydrogen alpha absorption line. I can see the magnesium triplet. I can see the sodium doublet. It's absolutely, and it's cloudy outside. So I'm not looking, not getting sun. I'm just getting reflected sun. Anything you look at, it will show you the spectrum of that object, what it's reflecting from the sun. So if you look at something green, your spectrum is going to look a lot brighter in the green. If you look at something that's red, I always get a couple kids to stand next to each other. I'll get a kid or an adult with a red shirt and somebody with a blue shirt, and have everybody look at both of their shirts with this spectroscope. And what you're seeing is the reflected wavelengths from those shirts that originally came from the sun. And the reason something is blue, the reason Simon's shirt is red and my hat is green, It's not because the hat is emitting green light or anything. It's because that's the wavelengths that are reflected from the sun. So if you look at that object through a spectrograph or a spectroscope, you'll see the reflected portions of the sun's spectrum. Fascinating subject. This item is available through Woodland Hills. I'm not sure what the price is, but it's not enough, whatever the price is. And they
tell them that.
double the price immediately.
Yep.
Best money I've ever spent on solar equipment. This I had out earlier. This is a prism. This is old school solar right here. This is a great thing to have at home because you can shine a spectrum of the sun onto a piece of paper and just look at it, man. It's cool. Or you can hang it from your mirror in your car and drive around and, you know, look like a hippie. It's a cool item. These are cool. The Shellyak line of products also has an intermediate and an advanced spectroscope, which is what this is, the high-res 3. The L high-res 3 is, I can't get it much closer to the screen, but it's got a 2400 lines per millimeter grading in it. And you can put this device into the back of any telescope like a C14 or any other refractor you have, and you can get observatory quality as good as any observatory, spectral information from anything in the night sky. You can do research with this at your house. If you've ever taken a spectrum of a star, every bit of information about that star is in that spectral data. Tom Field has some spectroscopy software called RSpec, which translates the light coming through the spectroscope, translates it into a graph of the star and numerical data. And the little graph that's going up and easing around different wavelengths will have a couple of squiggles here and there. It might have a strange mark here or there. And those are indicative of things like rotational speed of the object. You can tell how fast a galaxy is rotating by taking a spectrum of it. You can tell how strong the magnetic field of a sunspot is. You can tell the red shift of the object very, very easily with this gear in a nighttime telescope.
So Tom actually covered that program that he has on previous talks. If you guys haven't seen the talk that we did last time around about 2 weeks ago, it's well worth watching Tom Field's presentation. And I believe you can download the software for free, if I remember correctly.
Yes, that's correct. And he sells a little filter, a screw-on filter for night scopes called the Star Analyzer that produces a spectrum that's usable for research. I mean, it's a fantastic product and it's cheap. Spectroscopy is my thing, and I try to push it on anybody who'll listen to me. But for some reason, people are just standoffish about it because they don't understand it. It takes a little bit of learning to know what you're doing. But the things that have been discovered through spectroscopy dwarf any other field of research. All astronomical information is gained through spectroscopy, not through visual telescopes. So the L high-res 3 is also available at Woodland Hills. It is a fantastic product. Comes with 3 optional grates, 300, 600, and 2400 lines per millimeter. You can stick an eyepiece in it and just point it at the sun and see the sun's visible spectrum and get a close-up view of the absorption lines that we spoke about earlier in my presentation. Man, it is an amazing subject to get, especially get your high school or college age student involved in, because spectroscopy is the basis of every applied science there is. Medicine, engineering, everything. That you have to know spectroscopy to understand fully nature. There's an intermediate spectroscope between the two that is used for outreach purposes, and it's kind of like this, but it's a little better than the handheld one. And you can also see that on the telescopes.net website. So
somebody's asking what mount is that you're using to mount all of that stuff?
Great question. And you can also find this mount on the telescopes.net. Let's watch what it does. I'm just going to turn it on. It's called a Solar Quest mount from Skywatcher USA. I just hit the power and check it out. It's going to take a minute or two. It'll hold this much weight, 2, 3 PSTs or a 60 millimeter solar scope. And it is leveling itself first And then it's got a camera sensor right here that is going to look for the sun. So while we're talking, this thing is going to rotate around and take images of the sky and everything around it to find out wherever the brightest part of the sky is. Then it's going to zero in on that quadrant, and it's going to continue moving up and down a little bit until it finds the brightest spot that's half a degree wide, which is the width of the sun, in the sky. And it's going to stick to that and give you a happy beep. And then you look in the telescope and you're centered on the sun. You do nothing. You have no input on this at all. And as soon as it finds the sun, it starts tracking the sun. So this is a Solar Quest solar mount from Skywatcher USA. A very inexpensive mount, perfect for a small solar telescope. Runs off a 9-volt battery, so you're not carrying around a bunch of crap with you. I take this out in the woods on my nature hikes all the time, set it up, and people get to look at the sun's spectrum through this device. So I strongly recommend this mount for a small solar telescope. I mean, you're not going to put a 90mm double stack on it, or a big 152 solar scope. But if you're just looking to have fun and haul something out in the woods and look at the sun, you can't beat this thing, man. No power needed, just a 9-volt battery. All right, so now it's turning, it's looking.
So just for you guys who are watching at home, if you're watching the live part of the sun, because obviously I still have that up right now, there's a smaller prominence to the lower side, or should I say towards the south in this particular case. If you've actually been paying attention and watching it since I first showed this, it has actually gotten taller in the span of time that we've been sitting here. So it's probably been about an hour since I got this thing up and running. If you were to look at or wind back the stream, if you could be bothered, don't do it now, do it later. You can actually see that the prominence has actually gotten taller and has also changed shape, like the main part of it. I mean, I like to call them trees because that's what they look like, but the main part of it has actually changed shape. But the one thing that's sticking out, in fact, I'll use my little mouse like on this thing here, has actually gotten taller. And it will continue getting taller and taller until it will just basically snap apart. I doubt it's going to snap with this one because it doesn't look like it will.
Yeah, so a lot of times they just kind of are held aloft for a day or two, and then all of a sudden they just go away. They just dissipate. And it's really not conclusive in hydrogen alpha whether it's gone away or not. It could have just changed temperature.
Right, that's generally what it is.
Yeah.
I mean, I've actually had a moment, and then somebody else had a shot where they actually saw the snap and then the actual thing leaving, and then you can see this defined gap, and it just started to disappear and just fade out to nothing.
Dissipation. Yeah, that's common during solar max, and I really can't wait for that to come around because it's very common to see proms detach and even float off the side of the chromosphere for several hours. Change shapes, whip around. It's a real-time thing. You're not looking at the moon here, man. Things are changing. Things are actually happening. It's dynamic to the extreme as far as astronomy goes. There's not a more, well, maybe a comet would be more dynamic, but things are changing. So our scope, and by the way, it's overcast here, and the Skywatcher has still located the brightest part of the sky. And it's now tracking, it's not really tracking the sun because it can't even see the sun. It's just tracking the brightest patch of sky in the sky because we can see a tiny amount of brightness through the clouds. So I used this yesterday and set it up to practice when we had perfectly blue skies. Simon, the sun was beautiful. You'd be crying right now had it been yesterday's weather. You'd have a tear and a handkerchief. This thing found the sun within 3 minutes and it tracked it the rest of the day. And it's an out azimuth mount, so there's no flipping the equatorial or whatever. And it tracked it perfectly for the rest of the day on a 9-volt battery. You can't beat it.
So somebody's asking, compare contrast of a Barlow versus a power mate for solar imaging. So let's reference visual first, actually, because you should really ask about visual when you're doing power mates and Barlows. Do you want to go for this?
Well, it's been my impression that something called a power mate is usually from Teleview, and it's made to a lot higher quality than something called a Barlow. There's more optical elements in the power mate. So anytime you add another layer of glass on anything, you have a little degradation of the image. But if it's a super high quality layer of glass, like from Teleview, then you're not going to lose much. The sun is a single wavelength object through calcium or hydrogen. So it really, doesn't matter. Things like chromatic aberration don't matter. I never go higher than 2.5x power mate on the sun, only because it's way better to get a larger camera sensor than it is to try to zoom in closer with a crappy camera sensor. So what do you think?
Here's a good question for you then. So is it better to go with a higher magnification eyepiece or use a Barlow with a lower magnification eyepiece? I know it sounds counterproductive.
Definitely the eyepiece. Adding the Barlow in there does nothing for you because it generally degrades the image. Yeah, as far as visual observing, 16, 18, 20 millimeters is the place to be for solar observing. When you get down to the 8 millimeter range, you're going to see it closer, but I don't think there's anybody on Earth that has more time behind an H-alpha telescope than me right now. And I found 12 to 18 millimeters to be ideal for solar astronomy. Barlows, never use them. Never put a Barlow on a solar telescope. I don't, for visual observing.
So what about the type of eyepieces? Because again, this is like one of these urban myths, but it really is not an urban myth. The type of eyepiece also becomes critical.
Well, we may disagree on this. I don't know, but
believe you me, I doubt I'm going to disagree with you on this one. I already know where you're going.
Yeah, solar is way more forgiving for eyepiece quality than nighttime viewing, because again, you're viewing one wavelength of light. The reason triplet objectives are better for nighttime astronomy is because it's focusing red, green, and blue at different points and then merging them together. If you have a singlet refractor, if those even exist anymore, it's only going to focus one wavelength. It's only going to focus either the red, the green, or the blue, and you're going to have this chromatic aberration around it. This is my most commonly used eyepiece in solar astronomy, the CMAX 12 millimeter from Coronado. This is, I shouldn't say this because they do sponsor my program, it's a fairly crappy eyepiece. You stick it in, it works, it's focusing red, and that's all I wanted to do. So yeah, you can put a Teleview or a Nagler or something in there, and you're going to get a little bit better image only because of the build quality and the optical quality of the glass. But I don't think you need to worry about spending your money on expensive eyepieces to do narrowband astronomy.
I think that, and that to me, as far as I'm concerned, is an important factor. Is solar astronomy is actually a lot cheaper than people realize. It's an illusion that you see this scope and you see an Edelon, or you see this and you see that and go, holy crud, this is like just too much money. But there are ways to get into it for literally next to nothing. And Scott Roberts from Explorer Scientific has a particular product called the AR series. So it'd be the AR 102, the AR 127, and then 152. And so forth up. My point being here is it's an achromat and it's a doublet. They're made to be inexpensive. And more often than not, I see so many people who do a lot of solar photography that use this particular scope because it's inexpensive, and they just don't care. If you slaughter the scope, it makes no difference. Whereas I'm using a triplet, and my biggest concern here is it's an airspace triplet. I'm more concerned about the air heating up between the triplet and pushing the glass apart, which then ruins the collimation of my scope over time. So that's why I keep an eye on the temperature. When it reaches a certain spot, I just put the front cap back on, let it cool down for 30 minutes, and then carry on.
Right, and I have this astrophysics Starfire currently on the mount with a calcium K module, which is a total waste of telescope. The Scott Roberts you mentioned, Explorer Scientific, the 100 millimeter doublet from Explorer Scientific or Meade, really, they're basically the same, is the ideal telescope for solar observing in any wavelength. Kevin Lagore and I did a lot of these comparisons when we were doing outreach together. You will not find a better image than a moderate to low price doublet for white light observing.
So going back to the Barlow and the PowerMate, let's refer to the PowerMate.
Here comes the FedEx guy again, so I'm going to mute you for a minute.
Yeah, okay. So let's refer to the PowerMate in its correct name. It's actually known as a telecentric Barlow. They're actually quite widely available. You can actually get them from Explorer Scientific as well. They also make one. By comparison to the PowerMate, the PowerMate's probably one of the best ones out there. But the big difference is this: a Barlow, the further away you move the camera and the eyepiece, the more the magnification appears to be more apparent. Whereas a telecentric Barlow, as you pull it out, the increase of magnification is very, very slight. And more importantly, telecentric Barlows suit better for imaging purpose than it would be than a regular Barlow, because a regular Barlow creates this cup-shaped image almost. When you're doing visual, they're actually perfect for doing that because the surface of your eye is not flat, it's actually a curve. So when you're looking at this cup-shaped image, it actually looks like a flat field by your perspective if you're using your eye. Whereas with a sensor, the sensor picks up on the fact that there is this bulge. And it's more apparent if you're looking at something like the moon or something like that. If you use the Barlow and then use it without a Barlow, you'll notice that the shape of a crater on the edges changes shape ever so slightly, like it's almost distorting. Whereas with a telecentric Barlow, it tends to create a flat field view, or more of a flat field view. However, visually, I now suddenly see distortion because the cup now goes the other direction. So that's why we prefer to use telecentric Barlows when it comes down to imaging versus regular Barlows. It's a preference thing at the end of the day, because let's face it, a telecentric Barlow sometimes costs twice as much when it really does not need to, versus a regular Barlow. And Barlows you can get anywhere. Half the time they give them away for free.
I hate to admit it, but that's about 99 times as much as I know about that subject. And Jen Winter, who I think is probably the most learned person in the industry about optics, may have some more to say on that.
She will talk your ear off when it comes down to that.
The most intelligent person I know in astronomy. Of course, I haven't been friends with you long, so maybe you'll outdo that. But I take my little Barlows and, should I say this? I just unscrew the Barlow part of it and just screw it onto the end of my camera all the time, because to me, I like it better. And like some guy was asking me the other day about an image that was an apod. He goes, "Oh, it's not possible you get this field of view with that focal reducer." And I had to explain to him, a lot of the guys in this hobby are not optics experts, and they only, I basically only do solar astronomy. And I just unscrew the focal reducer off whatever crap it came on and just screw it onto the camera snout. So I have no idea how much focal reducing I'm doing. If it fits in the field of view, then it works for me.
Who cares? Exactly. I'm just going to mention this to everybody. So that one prominence, it looks like it's now connecting with the other one. It really does look like they're going to connect and cause a loop.
These magnetic fields emanate from the core of the sun, because the sun's core rotates at a different speed as the radiative zone outside of the sun's core, and that's what causes magnetic fields. And they come out of the sun at all these different strange angles. Right now we're in solar minimum, so everything's pretty well organized. But as the sun's differential rotation causes these magnetic fields to get all tangled and mixed up, that's what causes solar maximum, because the sun's north and south poles are so twisted out of alignment due to this differential rotation at different latitudes on the sun and internally with different layers of the sun, that the poles are actually twisted around and they change, north and south swap, every 11 or every 6 years, because that's what a solar cycle is. The fields go from north to south at a very quick pace, whereas the Earth's 30,000 years or something for that. But watching these magnetic field lines on your broadcast is cool to me, and I've spent a lot of time out here just staring at them.
Did you see the double loop by any chance a few years back?
You talking about the coronal loops? Yes.
Did you see that one?
Yep.
So the funny thing here is that's actually around about the time I got into doing solar in general, which was back in 2017, I want to say. So it hasn't been long by comparison. And I really wish if I knew what I knew now back then, I would have had a much, much better image of the whole thing. And I would have understood what was going on, because now I look at it and go, when I look through history, we haven't seen one of those, certainly not within our lifetimes. And
coronal loops are fascinating, and magnetic reconnection is a fascinating subject in the sun's chromosphere. And if you started getting serious about it in 2017, I'm gonna tell you right now that you're gonna get your socks knocked off in the next 4 years, because
dude, I am waiting. And you know what? That's what really upsets me, is talk about coming in late to the game. But the funny thing here is, because it's at solar minimum, there's very little going on for a group of us who do a lot of this imaging, and we bat backwards and forwards with each other. Any one minor feature that shows up, we're like, vroom. Well, that's what we look at for the next couple of days.
And
at solar max,
yeah.
we're sitting there and we're going to be going, I don't even know what to look at. There's going to be so much going on.
Well, you know, part of our nonprofit is the world's largest solar imaging internet forum. It's called solarchatforum.com.
Very familiar with that.
250,000 posts, and you know, I don't know how many thousands of users, but it's all serious imagers. People that started in solar minimum, like me, like you, by the time you get to any actual real features, you are so good at imaging minute nothings that you're just blown away by these, you know, Jupiter-sized sunspots or prominences that are 500,000 miles in size. You're going to be an expert on imaging minutia by the time that comes around. And like, this prominence is beautiful, but this, I wouldn't even bother imaging.
Yeah, this is nothing. Like, I know.
I would just skip over it to look for the real prominences, you know. But right now is a really fantastic time to get into solar observing and imaging, because if you get good with this type of features, you're going to be the best in the world by the time, you know, solar max runs around. That's my dog and my wife waving at me. Okay.
I don't know if you guys can hear my cat, but she is just like, just enthralled by what's going on. You know, she has like this thing that first thing in the morning up until a certain time, she'll be all over the place, rubbing up against the keyboard and everything. And right now I've got everything pushed out of the way so she doesn't hit something and then disconnects us.
Yeah, well, she's plotting how she's going to kill you later in the evening. What all cats do, you know. They're plotting your demise.
Well, unfortunately for her, she's actually in heat, so she's
oh, no.
Yeah, I haven't had this cat fixed yet. I really should, but there's a level of cruelty to me that fixing a cat that I'm not a big fan of, but at some point I have to, because she's doing all the usual, like peeing in the house, and I have to run around looking for the pee and wipe it up and spray it down with the enzymes and all that. She's gotten a lot better now, though, because dare I say, it's not you can train them out of it. You can control it to a certain extent.
Right.
So, guys, we're going to keep going on for another 2 hours, I think, with Steve, if you're all right with that.
Well, you know, I'm happy to. I don't think it's going to clear up, though, because it is solid overcast now.
Oh, boy.
And getting worse.
And the sun is running away from me again.
I'm going to walk over here for a couple minutes, and I'll try to come up with some more things to talk about.
Yeah. So in the meantime, if you guys have any questions online, watching through YouTube, feel free to fire them through. Ask us anything, pretty much. I mean, we have quite a big time slot here. Sorry, that was the cat jumping off there and decided to catch the wire. I told you she would get me sooner or later. So yeah, if you guys have any questions or anything like that, feel free to ask. We will continue to do this live broadcast of the sun, although the seeing has just took a nosedive, like they wouldn't believe it. Of course it would. So again, just so you guys know that this is live, I'm just going to play around with the histogram so you can actually see what's actually happening. You can see some of the surface details. Oh boy. Yeah, we're really falling apart there. I might have to run out to refocus, because I have noticed that the temperature has jumped up a little bit. Bearing in mind, I don't have an electronic focuser on this particular scope at the moment, primarily because I've got so many scopes. It's just like, put it on that one, put it on this one, put it on that one. Yeah, I should probably buy more than one. But for now, I might just run out there and refocus, because it looks like it's degraded, but I'll wait till Steve comes back for that. So you're not looking at dead air, as they say. So, questions. What you got for me? While Steve messes around with his dog, I'm assuming. So where is everybody from? We've got quite a few people watching. Yeah, seeing is actually getting bad. I do agree with you entirely. Again, I will go through my talk a little later on about seeing, but let's have a quick look at it. So again, this is a live view of the sun from all around the world, what's going on. And there is this is one of the sites that I use to actually look at how good or bad seeing is. So right now, we're just getting 3s out of 5s. It's not fantastic. A little bit windy as well. Humidity is, it's all right. Temperature's not that bad. But I will go through all of this in more detail when it comes to my talk. Otherwise, I'll just straight up run out of things to talk about when it comes to my particular thing. Oh, look, everybody's telling me where they're from. So San Diego, hello down there in San Diego. I'm up here in California. Atlanta, Jeff, go jostle with Steve, because Steve Ramsden is in Atlanta. If you're probably wandering around the neighborhood, you might actually spot some random guy with his telescope outside. Central Connecticut, never been there. Nottingham, UK, I've been there countless times. Nick Cook. Wait, that's not the Nick Cook, is it? Or is it just a Nick Cook? As in Ministry of Defense Nick Cook? I doubt it. Hey, it'd be cool if it was. San Clemente, hello there. Big Bear, of course. Eastern Canada, oh, it's kind of broad. Long Beach, California. Guffey in Colorado, middle of nowhere in the mountains. You know, I'd love to go over there, to be honest. I like being in the middle of nowhere, but here's the thing. I don't like the desert. I don't like sand. I don't like dirt. I like to see trees, grass, water. New Jersey, God. Brooklyn, New York. Hope you guys are doing okay out there with all this craziness. The Netherlands, hello. Usually we get a couple of people from Australia, but I haven't seen any yet. I think we had somebody from Hong Kong earlier on, which was crazy. That's the first time I've seen anybody from Hong Kong. Houston, Texas. I'm not the UFI Nick Cook, no. I didn't get asked. I had to ask. You see, obviously I'm from the UK, so I know who Nick Cook is. Ah, you're over in Newfoundland. Awesome. Is it cold up there? Actually, Nick Cook, if you don't know who he is, he used to work for the Ministry of Defense, and he wrote a book on like all sorts of things like UFOs and stuff like that. And he wrote a really cool one about World War II secret projects, and it's well worth a read. So if you guys don't know who Nick Cook is, do a Google on him. Really, really, really cool, amazing stuff. You know, he's like one of those guys that do a lot of alien conspiracy. He's not like that guy from Ancient Aliens when he goes, you know, big hair, and if it's aliens, it's that, therefore it must be aliens, etc. Sherman Oaks, California. You're literally just down the road from us. Somebody is in Australia. Woohoo! And Vancouver, Canada. Uh-oh. So Steve is back by the looks of things.
Yes.
So I'm going to let you talk for a second because I have to go refocus the scope. I don't have an electronic focuser, so I can see that it's starting to drift off of
Very good.
Focus here, so I need to reconnect.
So again, we were waiting here in Atlanta for the clouds to break, but as you can see, let's see if I can tilt my camera up. The clouds are not going to break. It is totally overcast here, and we may even have some rain coming up. So I might be fleeing from the broadcast at any moment. And that was my neighbor walking back and forth in the background there. For whatever reason, decided to come out and talk on the phone. But I'm going to have a Diet Coke and sit and wait. By the way, if you're not into birding, this is a great time. This isolation and this COVID quarantine has caused animals to prosper and proliferate everywhere in places where they weren't before. We saw a large doe walking down the middle of the street over here last week, and I live in the middle of downtown. So we've got deer, raccoons, possums, all sorts of birds coming out here in the downtown area that we never see before because the pollution's so bad. And I really enjoy birding as an extension of solar astronomy because, like I say, when you look at the bird, you're looking at sunlight reflecting off the bird. So Meade and Celestron both have fantastic birding binoculars for pretty cheap. So if it's cloudy outside and you can't get any astronomy in, why don't you go look at sunlight being reflected off everything around you instead of crying over your seeing conditions. You can look at this cedar leaf right next to me. It's green for one reason, because it's reflecting green light from the sun. A lot of plants will be darker in some regions and lighter in other regions. Like up in northern part of North America, the woods are generally a darker green than they are in the tropical regions like Florida and South Texas. They'll be brighter green, and that's for heat regulation because the plant is reflecting more light in a hot climate. It's reflecting more of the green wavelengths from the sun so that it doesn't overheat.
Sorry, I am not cracking a beer before you ask. It's Diet Coke.
Yeah, I've already cracked my Diet Coke as well. Cheers.
Cheers.
Cheers, mate. Birding, like I was just explaining, is really taken off during this isolation. And hopefully people are going to notice more of their surroundings. And nature has recovered so significantly in this short month or so that we've been doing this lockdown here in Georgia. I really hope that people can see how quickly it can rebound and get back to being beautiful versus how it was when people were everywhere polluting everything.
You know, that's the funny thing, that even though it's such a big deal with this coronavirus, that I have noticed certain things have changed from a wildlife standpoint. Like usually in this time of year, I get all sorts of weird and wonderful things and random infestations like ants and stuff like that. I have a completely different one. I'm getting fungus gnats this year, which I have never seen before. But it's only because that there is less people out and about that has caused certain things to become more apparent. Like certain wildlife, bears, wolves, coyotes, the whole 9 yards have all started to come out and going, where is everyone?
Yeah, Sunlit Earth, the Facebook group, has had a lot of discussion on that of late. And while you were getting your Diet Coke, we were talking about the doe, the full-grown doe that just walked past our house last week in the middle of downtown. We've had I took two coyote photos last week. We had a raccoon in the yard, and yeah, this is Georgia, but this isn't, country Georgia. This is downtown Atlanta. So the animals are recovering greatly. This year, my hummingbird feeder, the hummingbird started coming March 29th, which is 3 months earlier than it came last year. And that's a direct result of the air quality, because these birds are really sensitive to pollution and exhaust. And it's been a ghost town here since the beginning of March. And the air is so much cleaner than it was that all these animals are coming out. The hummingbird comes by every half an hour or so and drinks. And you got to be kind of older to appreciate this, but I would encourage everybody to look around and just check out nature a little bit more right now. And get yourself some optics for viewing nature, even a camera, a point and shoot, whatever it is. But just pay attention to what's going on around you. There are some good points to all this, and nature is the highlight for me, at least. That's why I'm using these Meade birding binoculars right now that you can buy at Woodland Hills to check out all the creatures that are running around. And it looks like it may even start to sprinkle here shortly, Simon.
Uh-oh.
Which means I'll be saying goodbye. And I don't know what else is coming up on the schedule. You have.
So Jen, who's next? Jen Winters will be on at 12 o'clock. So if I have to play a bunch of random videos, I will. I've got enough content to last me hours and hours and hours. It's probably enough to get rid of everybody too.
I think you may have to do that, because I reluctantly am probably going to have to put my gear away here soon, because I've got, let's see, $48,000 worth of astronomy gear in my driveway right now.
That almost got ran over by a Amazon truck.
And I'm not a fan of rain, so I think I may have to sign off and let you run it until noon,
Yeah,
if that's all right with you.
no problem, no problem. Steve, thank you very much for doing this.
Well,
We do appreciate you.
Before I go, I want to say how grateful I am to Woodland Hills for inviting me on here, and you know, having content right now is real important, and you guys are doing a great thing, and I appreciate all the work you're putting into it, Simon. So come see me on the Charlie Bates Solar Astronomy Project Facebook page, the Sunlit Earth Facebook page, or through our solar chat forum at solarchatforum.com. And adios from what used to be sunny Atlanta.
See you later. All right, guys. What are you trying to post? A message has been retracted. Uh-oh. I'm assuming you're posting a link. I have no idea why it's restricted. Sorry. So yeah, right now we are still looking at a live view of the prom that's happening on the sun right now. It looks like Steve has been rained out, but it is what it is. So for now, we're just going to leave this as a live view, and I'm sure you guys want to see the live view and not me. So let's pull me out of the way and expand this up a bit more so we can get a bigger screen. There we go. Cover the entire thing. So just so you guys know, remember, Jen is going to be on at 12 o'clock. We had a 4-hour slot for Steve because of it's being weather related. You know, of course, this is astronomy. When you want to do something, and it's always cloudy, is what it is. All right, guys. So I'm going to leave this running for now, and I am going to mute myself. So if you guys want to go off and get breakfast, lunch, dinner, whatever it is, because, you know, it's different times during the day for everybody. And I'm just going to go ruffle with the cat and then take a break, and I will be back in about 5 minutes probably. All right, I'm back for a second. Quick answer to the different questions here. Bruce, you're asking which solar filter am I using in the telescope that I'm using on the size specifically. I'm using a Daystar Quark Gemini. The scope size is 100 millimeters. It's actually an Esprit 100. What camera am I using to use live? I'm using the ASI 174 from ZWO. All right, so for now, I am going to play you guys a quick tutorial video. This part probably won't get covered in my talk later on today, but it'd be worth for you guys to watch it now. It's probably going to be a little bit out of context because this part should really come after the more advanced stuff, I guess, for lack of a better description. So we're going to play that for you guys now, just to fill in the time so we don't have dead air or you're looking at the sun. So here we go.
Hello my happy astro campers, and I am back with not necessarily a tutorial this time, but this is more an informational video about doing imaging specifically with solar. So what I actually have here is the sun, strangely enough, and we're going to be looking at 8-bit versus 16-bit in terms of color space. The program I'm using is SharpCap Pro, and as you can see in the drop down box here we have two options here for two different settings, 8-bit and 16-bit, and if you have a color camera you'll have other options such as 24 and so forth and so on. So what I'm going to go in here is, these are probably more advanced settings that we're looking at. Specifically we are paying attention to the color space and the type of file format. Now typically when you're using default settings, it is actually preset to whatever it determines is the best fit. Now in my particular case I prefer to use SER files purely because they are full uncompressed. Within 8 mono, for example, you have the option to be able to do AVI files. And what we're going to do here is we're just going to play around with the exposure settings for a second here. What you'll notice here is there is a frame rate that is located down here. Now this tells you how many frames that we can capture depending on your system. Now being selected in 8-bit versus 16-bit, we're going to obviously see a big difference. When we're here in 16, the frame rate actually drops down to around about 60 frames per second, and we can actually change the performance based upon the exposure time. So if I was to increase it, you can actually see the frames per second drop down quite drastically. So I'm just going to go back and reset this down to something that I use quite frequently. If you notice that there is a gain setting here, this obviously does not affect the frame rate, so if you feel that your image is a little bit too dark, it's actually better to push the gain up than it is to increase your exposure time. So we're going to take a quick look at the high-speed mode here. This is only really applicable for a legacy camera of some description, and it doesn't support high-speed modes. You can turn these on and off. This does affect the performance. If you have an older camera and you find frames being dropped, because basically what happens here is your computer itself cannot actually buffer the images faster than it's pulling it down. So you kind of have to slow everything down, and the easiest way to do that is to simply modify the high speed mode. Typically if you have a USB 2 camera, you need to set this to be off as opposed to on. If you still have other issues, even with a USB 3 camera, depending on who makes the actual camera, you may have to experiment with this. Typically this results in dropped frames, and you can actually see this down in the corner within the brackets. Of course this particular system is set up to be optimal, so I very rarely get dropped frames. Now one other interesting feature here is if you needed to do some type of analysis on the frame rates, you can actually set the timestamps with the number of frames, and that shows up in the top left hand corner. Typically you can actually modify this so it shows up in different places, but typically I keep this off because I don't want a timestamp all over my images because I'm not doing anything specific. Now one of these other parts that we're going to look at here is the pre-processing. You may have noticed that in a previous tutorial that I was messing around with dark frames and flat frames and things like that. In SharpCap you actually have the ability to do dark subtractions and apply flat frames live directly to the video. I generally don't like to do this because I prefer to do all the calibration frames at the end or afterwards, but if you were doing live astronomy and you wanted people to see a better image, you can go ahead and make your flat frames ahead of time and then simply drop them into here. It actually does a pretty good job in doing the calibration part, but typically what I found is once I've actually captured the footage with all these calibration frames applied, it doesn't tend to look as good as I was expecting it to be. And of course the band suppression does a very, very good job if you tend to get a lot of banding. On the IMX 174 there is a bit of banding that can be noticeable, but in this particular case we are always going to be using calibration frames after the fact, since we are not actually doing some kind of a live astronomy here. So we're going to take a quick in-depth look into 8-bit versus 16-bit when it comes down to processing, specifically on the sun, because I generally feel that shooting in 8-bit and 16-bit when you're doing solar imaging, there is a huge, huge difference. So let's switch over and I will see you back in just one moment. So I've gone ahead and stacked the raw video files for both 8-bit and 16-bit respectively, and we're going to have a look at the differences between the two. Now I'm working in monochrome for now because I kind of feel that it's the best way to actually get a better idea and a better look into how good or bad one particular image is versus the other. Now, in order to keep this fair, I've also used the exact same settings when it comes down to processing and doing all the sharpening. I didn't want to purposely make one over sharp versus the other, otherwise it may seem a little unfair. So right now what we are looking at is the 8-bit version of the surface of the sun, and we actually have a small active region right here, which is actually a sunspot as well. And when we actually look, first things first is I kind of feel like the image is very, very soft, and the way that the white has blended into the actual edge of the sun, or more commonly known as a limb, doesn't seem to be not as nice as it would look like normally. And even more evident is the prominence details just seems to be very, very wispy. Of course, this could always be attributed to bad seeing, but both of these videos were shot literally back to back. So now we're going to go over to the 16-bit version, and already there's a huge significant difference here. The prominence details, especially the one in the corner here, is a lot sharper, and it almost looks like there's more shading to it. And of course the actual blending looks a lot better as well. And then obviously the active region here is more pronounced, and even some of the detail up in this area here is a lot better than it would have been compared to the 8-bit counterpart. You can just about make out this area here is the same section. So I'm also going to have a look at the actual original file before it was sharpened, and there's not much discernible difference here, other than it does seem slightly sharper for the 16-bit. Now this is the unprocessed stacked file. The idea behind why I'm trying to show you this is so you can get an idea and an understanding between the two different files. Again, I'm going to make these files available to everybody who is a Patreon subscriber, so you guys can download that data and have a go at processing it yourself, and then check out the difference between 8-bit and 16-bit. But one major important part that I do want to point out first of all is when working with the 8-bit file, there is actually more data hidden inside of all of this. So typically when you're working with an 8-bit file, you're not going to get the color and the dynamic range as you would do compared to a 16-bit file. And I can show that. We're going to convert this over to a true 8-bit file, and I'm going to mess around with the HDR toning to see what the major difference is going to be. And already I can tell just by looking at this, it's not looking very, very promising, and there's a lot of noise, especially where the blackness of spaces and where all the prominence detail would actually lie, including all the spicules. It just seems very, very muddy, very, very noisy, and just simply not very good. So we're going to take a quick look now at the 16-bit version. And you can see there is already way less noise. And if I increase all the detail, we can actually start to make out that the prominence details is obviously a lot better off than the 8-bit counterpart. Now again, there's obviously a clear trade-off here, because in terms of file sizes, the 8-bit versus the 16-bit file, the sizes is absolutely amazingly different. Now, just to give you an idea, we're going to have a look at the original 8-bit file here, which is like 4.6 gigs, versus the 16-bit file, which is double the size pretty much, at 9 and a bit gigabytes. So it's quite a big difference here, and it's actually going to be even smaller if I had actually saved all these files in AVI format. In fact, it probably only would have been roughly a gigabyte, if that, for the 2000 frames that I had actually captured. So hopefully this gives you a good insight in the differences between shooting 16-bit versus 8-bit, and hopefully this will clarify a few things for you, and I look forward to hearing from you guys and seeing some of your work.
Alrighty, I am back. You're looking at a live view of the sun right now. I'm sure you guys probably want to see what's going on. So while we pad for time, for lack of better description, does anybody want to see some processing happening? Because I just did some quick captures, because I noticed that I had some good, in fact, actually seeing got a little bit better right now. I'm debating if I should hit capture right now. Probably not. So yes, does anybody want to see some quick processing happening? If you do, just let me know. I can just quickly do that. I don't want to do this or go over it again, because I am going to be doing my talk at the later time slot, which of course you can play back at any time you want. But just because Steve had to cut his talk short because it looks like it's going to rain over there. So if you guys want to see something happening right now, okay, Nick says yes, so it's good enough for me. All right, so let me just get me out of the way, and then I'm just going to fire up a bunch of programs, and hopefully this will work good. Let me just, actually, I'm going to move that over here. All right, so the program that we are going to use to do the stacking is going to be AutoStacker. Again, this is a free piece of software that you can download, and it's relatively straightforward to use. It's not complicated. Again, I will go over that information a little bit later. So now I've already captured some data earlier on, so we're going to actually go and check some of it out. So let me open one of them up so you can actually see this. I don't have any calibration frames, so please be aware that this may not look the best because I have no calibration information. So right now, this was taken a little bit earlier on, and it looks like we've got some pretty good frames, a little bit ripply because of the seeing conditions, and there is a bit of wind outside, so that's why it's wiggling like a maniac. So first things first, let's actually get this thing in here and start doing some stacking. So I'm going to pretty much blast through this. I'm not going to go into too much detail because, again, I do want you to watch the other part of it. So what I'm going to do here is pick a anchor point. I'm just going to randomly select a place. I'm using surface image stabilization with an expanded view. Now, where this green box goes is actually somewhat important. You'll understand when I go through this that you kind of don't want to go on the outside, like here, for example, because it can cause interesting problems. So I'm just going to randomly click on the location that looks like it has somewhat of a feature, and then just simply hit analyze. And off it goes. Again, I will go through this in my talk in more detail. I'm just doing this so you guys can just see what's going on. And we have a result. So let's do how many frames? Let's do 15%. We're going to place the grid, and off she goes. So depending on how good or bad your machine is, this is either faster or slower. Magically, this folder has appeared that has the stacked image. And what I'm going to do is open up another piece of software called IMPPG. And we're going to hopefully navigate through to it. So desktop, there it is. So we have this image. We want to process the entire thing. So out of your view is this great big histogram. I have two screens on my computer. Well, actually right now I have three, but I have two screens on my computer that allow me to do this. And I like to actually make this histogram as big as possible. And the reason being here is I really want to be able to fine tune all of this. So I'm going to keep it out of view for a second so I can see what I'm doing. And as I manipulate this, you'll see things change. Now, I do this in a very specific order, so I'm just going to pretty much do what I usually do when I'm doing this kind of stuff and just blast through it like I typically do. And then if you guys have any questions, don't hesitate to ask. I will answer questions as much as I can. But again, some of this stuff will be covered in the talk later on tonight, even though it's the middle of it's still the morning for me. I know it's the morning for other people out there. But I'm just going to quickly do this one. Just so you guys can see the final image processed from today. So there's my histogram. This is like an atypical curve that I would normally do. You don't have to do it as quick as this. You can spend a lot more time because the more time you spend on it, the more apparent it becomes. Again, I'll go through that in the tutorial. Then let's do some sharpening because why not? Maybe it's a little too many iteration. Let's try 200. Yeah, that's better. Oops. Go for an extreme first of all, and then dial it backwards. The amount. It's a little bit soft because seeing is not optimal. Again, in the video later on, I have examples of good seeing versus bad seeing, so you know what you guys are looking for. How long will each capture last? It depends what I'm doing. Usually if I'm doing proms as short as possible, 1,000 frames is actually more than enough because it changes so quickly. So I try not to have too many frames to try and work with, otherwise the features change too drastically. So right now I'm just going to try and fine tune some of this. Unfortunately, because of bad seeing, it is a little off the soft side. So the proms aren't coming up as nice as I would like them to. And there we go. We have somewhat of a good result there. Bearing in mind, this was literally just done a few moments ago. Oop. So if I bring over here, there's the live view of the prominence, and that's the after. Again, this was taken a little earlier on, so that the shape has actually changed. So if I can see if I can squeeze them both in, to both be in the view at the same time. And there we go. You can see the difference. She's seeing is actually pretty damn good right now. Let's grab a quick capture. Can't see where we are. Okay, so we got a fair few there. So let's actually look at that real fast, see how good that quality was. Captures. So that was that one there, I think. Copy. I just got to copy this thing over. This is actually on another machine that's outside, that's done remotely. This is the part that always takes the longest, the copying of file. All right, let's see how we did with that one. Analyze that. Yeah, not much better. Let's do 10%. Let's really clamp down on that one. Place the alignment grid, stack. Now, the great thing about IMPPG is these settings port over to the next image you open up. So if we actually open the next one that we have, so on the desktop, it was the 10% stack. I shouldn't have to really do very much. There we go. So we've got a much, much better prom right there now. It looks a little less muddy, a lot sharper, which is pretty damn good. Okay, so as a primer for the video, let me just see if I can find one of my other videos that I can play real quick. Of course, we never accounted for that we were going to have bad weather, but you know what? This is astronomy at the end of the day. Good weather, bad weather, it is what it is. Looks like I don't have it to hand, but that's all right. We can definitely show this another time. So, any questions for now? I'll be happy to take some of your questions. While I wait, I'm literally just going to tweak the snot out of this. Is that an easy ad for doing the size comparison? It's not super accurate, but the method that I actually use is I download a pre-existing image that has a comparison that is done by somebody reputable, preferably. And what I do is I just basically expand it to fit the same size as the sun that I currently have, like the curvature and so forth and so on. And usually that's the best way to get it. It's not foolproof, but it does work. How long should you capture the data for that isn't a prom? So now this one's actually open to debate. Again, the idea here is as short as possible. In other words, you want as many frames within a certain amount of time as possible, hence why high-speed frame rates is a critical thing. So let me just go back into this a second before it runs away, and I wasn't paying attention because it nearly ran away. The most important factor that I pay attention to when I'm doing any solar is the frames per second, which is down here. So right now I'm pulling around about 120 frames per second in 16-bit, but only because I've actually scaled this down. Now, if I actually go up to, say, full resolution, like close to 1080, you'll notice that my frames per second drops drastically, which is down here. So now there are other ways to try and get higher frame rates. Is we can also shoot in 8-bit mono, but as you saw the video previously, that's not always an ideal scenario. As you can see, there's like heavy banding occurring here, because in 8-bit, I cannot get enough shades of gray to create a smooth looking image. But this is also another way to actually get higher frame rates. Now, the smaller the frame size, the higher the frame rate gets. So now I'm pushing 160. So let's go crazy. Let's see if we can go even further than that. Let's go to a square. So we're only looking at this prom. Looks like a piece of broccoli grown out. And I get around about 165 frames. And even in 16-bit, still roughly the same. So it's a direct correlation of how good your hardware actually is and your field of view, or the capture area size. In this case, SharpCap refers to it as region of interest. So that's what we're looking at right now, is within this region of interest. So the idea here is, or the name of the game is, as many frames per second in the shortest span of time possible. So if we just go into this and say, I want 1,000 frames, this thing is just going to tear through it, and it's within seconds. As you can see, we're almost already done. And then it will spit out a file at some point, which we can go and look at. So if I want to go to the folder, there's all the data that we were just capturing. There's the file here. Notice it's considerably smaller there because we've changed the frame size. So if you guys want to see how that looks, let's go back to this, and let me just pull that piece of data off real fast. So we're going to do this one. Let me just copy it over to my machine quickly. Let's slap this on there. So notice that the frame size is obviously a lot smaller. So this might be becoming an interesting challenge here. If I can get an anchor point. Yeah, it does. So we'll just do a quick analysis. And we'll stick with the same 10%. Don't need a lot. So let me just save this, because this is actually not a bad image. I'll dump it on my desktop for now. So date today, 20/25/13. It's now 10:51 a.m. So let's go check out that image that we just did. Which one was it? I think it's this one here. Select all. There we go. That was just a quick capture. I mean, this is how fast this really is, especially when you have the settings. Again, I will go through how to use this program in a bit more depth. I'm just blasting through this right now. I'm using a Solarmax 70 with a 183 MC. This is fine for full disk capture. Yes, it is perfectly fine. The frame size of the 183 is quite big, so and then it's also a 70. You would actually get a better result if you use the monochrome version, believe it or not. But for the interest of cutting a few corners, if you've got a color camera, that's fine. Some color cameras do have monochrome modes that you can actually use. They're not ideal, but they do work, and it's perfectly fine for the task at hand. For the banding, do you use the Daystar interference eliminator? I have one. Do I use that particular one? The answer is no. I actually use the ZWO one because it fits better for my ZWO camera, and it's already been preset. I've had that thing set in that particular way for God knows how long, and it's fine. For those people who don't quite understand what we're talking about, interference eliminator from the banding, it's actually called Newton rings or Newton rings. Bad accent. What happens here is it's two optical plane surfaces that are parallel to each other will cause interference patterns, much like how these filters on your solar filters work. So by tilting it, it changes the angle of incident. The idea here is you're introducing a tilt into the camera, so Newton rings can actually be tipped away. But be aware, if your tip is too severe, you will end up tilting the image. So a lot of the times you may have to fiddle around with your setup And even something as simple as rotating the Edelon or the camera or anything else will actually help reduce some of these rings. Sorry, I just got to check the temperature because it's been sitting out there for quite some time now, so it's going to be red hot when I go touch it. And as you can see, seeing has pretty much gone downhill. We'll go back to the larger view so we can see more of it. So if you just got the Quark for a camera specifically, like a Nikon or a Canon, they actually make them for those types of things. The best lens that I've come across generally is any fixed prime with whatever focal length that you would want. It's kind of pricey. The Nikon 300mm fixed prime, that by far and wide is one of the best ones. If you can afford to push it out there, the 400 is also a good option to go for. If you don't have that, you can totally use zoom lenses. The 100 to 400, the 70 to 200 are more than enough. You do need to choke down the aperture, so you don't want to be shooting at like f2.8 or anything crazy. You kind of want to be like f5.6, maybe f7 tops, and you can get some pretty good good views with it. It's a very, very different process because it's in color. It's very, very red. Scene conditions are not super critical, but you will get a full disc no matter what. You know, there is no close-ups per se unless you get a longer zoom lens or even use a telecentric adapter. They do sell the 2x and the 1.4 teleconverters. I personally have not tried them, so I couldn't really tell you if they're any good or not. So any other questions out there? So I'm just going to fill in for another 5 minutes, and then we're just going to have a couple of pre-made home videos, we'll call them, to fill up for the rest of the time. Jen will be on at 12 o'clock. Again, because of bad weather, Steve had to cut short, unfortunately. Otherwise, between me and him, we could probably talk for more than 4 hours. So yeah, any other questions, feel free to fire them off. Remember, I will be doing a very in-depth dive into the processing side of things, the difference between seeing conditions and stuff like that. And of course, what you just saw is what we were looking at today, which is that prominence right there. So this prom is that prom right there. This is live, it's happening right now. Oh, you son of a... I completely missed that. That was a plane going into the shot and I wasn't recording. I don't believe that. Oh my God. You know what? I have waited and waited for that to happen, and it happens and I wasn't recording. I suppose I could watch it back on the YouTube stream in a minute. Oh man, that is so disappointing. I've been wanting to capture that for ages. Sorry. Sounds like 100, 200 frame stacked is a good number, no matter if proms or surface details. I'm not going to answer that right now. I'm going to go into that a little later because there's two parts to this. Yeah, I'm going to go in that a little bit later on. I'm going to save that one. How do you convert black and white images to color, or can you do that? Again, that's going to be covered in the talk later on today. I don't want to do this right now, otherwise then I'll have nothing to talk about later on tonight, and then it'll be a very, very dull evening for me. You talk about a heat buildup. How long will it usually take before the blah, blah, blah? Okay, so that's something I won't be covering, so I should go through this. So right now, my camera has a temperature sensor on it, and come back, son. You know what, I can see everybody now is just replaying or winding back just to see that damn plane go past, because I am going to do the same thing in just a minute too. More importantly, heat buildup. So I have a triplet refractor, an Esprit 100 to be exact. And the problem here is This is a high-end telescope that is designed more for nighttime astronomy than anything else. It wasn't really optimized for doing solar. So the problem here is with an airspace triplet of any description, the air inside does actually heat up. And as it heats up, the pressure builds up and presses against the glass. So as the glass gets more pressurized on two sides, it wants to push it out. And then what happens here over time is the more I leave it out and the more I use this, the more likely the collimation of my scope is going to go out and then cause me a bunch of problems that I kind of just don't want to deal with. And hold on, seeing conditions just got really good. Sorry, when you're doing solar, this is what I do. I just stare and then just spot things. This is actually going to be pretty damn good. And if it would just stop jittering because it's windy outside. Oh my gosh, this is actually really, really good. All right. Sidebar, sidebar, sidebar. We're going to go look at how good that was. Let me just pull that down. This is the thing about doing solar is a lot of it is what we refer to as lucky imaging, just like that plane going past. And when I see how stable the air is, there is no way am I just going to not hit record. So that's exactly what I was doing. And we're going to go check out how good or bad that actually was, because that looked very, very stable. I'm just going to scrub through and you can see how stable and clear it is. There's a little bad patch that just happened right there. You can see how it blurs. But this part here, we might actually get some good frames. So let's have a look at this. Just going to let it process real fast. Yeah, definitely. See the graph here is definitely giving us a better result. Again, I'm only going to stack 10%. I don't need that many. Off we go. All right, let's pull out that image real fast. File open. Oh, yep, this is a better one already. Yeah, you can definitely see something here. So I'm going to show you what happens if I do more frames. Let's be a bit more aggressive. Let's do 40%. And we're going to try and flip between the two. Right, so that's done. So this is the 10%. Let's save this real fast. TIFF. We'll just call this 10% for now. File open. Let's go over to that one that we just did with 40. There we go. File, save, TIFF. And this is the 40%. So what's going to happen? What's happening here is this. What we've done is we've stacked 40% out of 1,000 frames and 10% out of 1,000 frames. So essentially 100 frames versus 400 frames. Now, because we were shooting at such a high frame rate, very little has changed. So I can afford to go for a higher frame rate and higher stacks. So what I'm going to do is let's just get this so we can do a side-by-side comparison. So open with, where's open with gone? There it is. We're going to go into photo viewer. So there's that one. Let's put it over that side. And this is the 40% open with photo viewer. So here's the two differences of a 40% is on the left and the 10% is on the right. The processing didn't change, remember, because we just used the same settings. And the interesting thing here is the first thing you guys are going to pick up on is if we zoom in on both of these is more important is less noise. The more frames you stack, the less noise that occurs. However, you're going to more likely result in blurred details. And what I mean by that here is if you're only capturing, say, like 10, 15 frames per second, and it took, say, 2 minutes to capture 1,000 frames for argument's sake, what will happen here is the prominence will have moved a lot more than the first shot. So when you stack all of this together, you get this fuzzy, hazy mess, which is why we always go for higher frame rates and then stack the best out of that group. But because I just spotted in the corner of my eye that the seeing was actually really, really good, you know, there was this brief moment where you see this jittering that is occurring. It was nowhere near as apparent, and certainly it was looking smooth. So right now, you're seeing is wind. The rippling is actually the seeing conditions. So I'm going to just limit this. You see how you got that rippling that's going on the surface or the edge of the sun. That tells me what my seeing is going to be like. The shaking is just straight up wind because I can see the trees waving in the background in the window. But that's not that big of a deal. Usually the stacking process does eliminate a vast majority of that. Okay, so going back to the questions real quick. Oh, sorry, let me finish off the heat thing, sorry. So that's why I have a temperature gauge on here that I can keep an eye on. And right now at 43 degrees, that's not too bad, but it does tell me that the internal temperature of my scope has obviously increased quite dramatically. And all I have to do is just go outside and physically touch the scope. And if it burns my hand, I have to stop. So there is a limit to how long you can leave a regular refractor out in the sun for, because you're going to run the risk of damaging the front element. Ultimately, if you want to leave the scope out for long periods of time, you really should use what is known as an ERF, an energy rejection filter. They can be quite pricey, but to be totally honest, if you have a $5,000 telescope, and a $1,000 investment for an ERF is quite worth it, in my opinion. But, you know, again, that's entirely down to you. I have a Newtonian. Could I make that into a hydrogen alpha off axis? The answer is just straight up no. It is not recommended to use a open tube SCT style, Newtonian style scope of any description. There are cases where you can use, say like an 8-inch SCT that has the mirror, or not the mirror, the corrector plate dielectrically coated to actually reject a vast majority of the sun's energy, and then that's perfectly fine. The real big problem here is with something like a Newtonian, the light is so heavily focused that I've seen this happen before. By the time it's hit the primary onto the secondary, the light is already getting heavily focused, and it is just so strong that it actually melts the aluminum off of the actual diagonal. This is not an exaggeration. This can happen. It just depends on your type of scope and how fast that mirror actually is rated to be. Does the ZWO autofocuser work well for solar imaging? Autofocusing does not work well for solar imaging in general. It's just the way it is. I've tried it numerous times. It's for whatever reason, it just does a very, very strange job of actually doing the autofocusing. So it's better if I just do it manually. Stacking with hazy skies. Yes, it does. You can actually image it in hazy skies, or should I say with bad transparency. All that happens here is when you have poor transparency or low transparency, is your contrast is essentially lost. And you can try and cheat some of that back. It's not the end of the world. Normally with good seeing comes okay transparency. It's very rare that you get good seeing with good transparency. And if you do, it's actually a bad sign. To be totally honest, because you're going to see that heat rippling effect from just the surrounding areas alone. So it is what it is. What about 6-inch RCs? Again, no, because there is no corrector plate on the front that you can have dielectrically coated. All of these scopes, however, you can do white light. If you get a white light filter that fits on the front of the scope, not a wedge, they are perfectly fine. So you can do white light imaging. And in fact, some of the best white light images I've seen are used with large aperture scopes. Now, I have a 12-inch Newtonian, And I'm kind of in the search right now for finding a white light solar filter for that guy. I'm going to go full aperture because I'm not physically looking through it. I'm not that crazy. And put a camera into it. And the idea here is I really want to catch that crackling surface. But there is a lot more to it because I do have to reduce the energy down quite considerably. So there's a little bit of research that I have to put into it before I start going nuts. Oh, Kevin's on. Oh my God, Focus Astronomy's on. For those of you who don't know this, Focus Astronomy is another outreach program that does a lot of this kind of stuff. The guy that runs it is Kevin Legore, and I'm sure I'm going to have him on one of our live streams one day talking about something or other, probably outreach programs, because that's his big thing, and meteors, and this guy's got a collection of meteors like you wouldn't believe it. All right, so here's a good example of bad seeing. There it is right there. That is dreadful. Oh boy. All right, so I got a feeling my tube is heating up because I just noticed the temperature jump again by another degrees. This is in Celsius, not Fahrenheit. I am a Brit, so I still go by Celsius. It's really weird for me to see Fahrenheit. It does drive me crazy. So what I'm going to do is we are going to play a video as a short break. So if you guys want to run off, go to the bathroom, make lunch, breakfast, dinner, or go to bed, it's entirely up to you. We're going to take a quick break, and I need to break down the scope before it explodes dramatically, which it won't. If it does, I'll come running back and I'll film it so you guys can see it, because it's, I like watching stupid things. That's kind of why I'm called the stupid astronomer. All right, I shall be right back.
Part of the challenge that the amateur astronomy community is facing is to bring in more people into the hobby. So we've been actively trying to contact different people, science communicators, people with influence are also interested in astronomy, to help them help us popularize the hobby. I think it's very, very important for all of us to do that, because as a hobby, we want to make sure that it's growing. And one way to do it is reach out to younger people, make sure that the next generation, the younger people, are actually getting into the hobby.
Basically, I look at it now and I think of astronomy as more of a really artistic. You look at all the beautiful pictures that they do, and I think that's going to bring more people in. It's like getting the big buck for the hunters. You want to get the most beautiful picture that you can get, and it's kind of a competition, really. Something that can be achieved, and you don't have to have physical strength. You don't have to have all these different things, but you can go in and just be able to have that creative spark and eye, and go out there and work with it.
I guess what I do is I have a small group of friends near my home. And if I have a night where I decide to take out the telescope, I'll invite them along. It's not really their hobby, but it's nice to branch that out. But I would like to do some outreach to some high schools or elementary and get the kids interested early, so that it's not something you're starting when you're 20s or 30s. It's something you start early on, and you just get that for your whole life.
Already we can see that the impact of social media has popularized astronomy a great deal amongst people who just have no real direct interest in astronomy, but they get excited about these things. Like this eclipse that just occurred, had one of the largest turnouts that have ever occurred for a solar eclipse. And I think it's 100% due to social media and the news coverage that it gets. So I think that is making it more important. In other words, you can reach people much easier now than you ever could before.
I think the general public is more into the now results. So a lot of people like to share things. I find that people like sharing. They want to see results. They want to make things easy. So I see a expansion into just easy imaging and sharing.
There's a lot of people now doing science, not just astrophotography anymore. There's a lot of people doing science. There's a lot of citizen science, and there's schools that are doing science. The easier we make the telescopes, the more science that the schools can start doing. We get colleges doing science, and maybe even down to high schools doing some science projects with NFS grants and such. So because the capabilities of the telescopes today are so much more, I think the way to get the young people involved is to get them using them in schools.
On the scientific point of view, astronomy is trying to answer very fundamental questions, and most of them have to do with cosmology, meaning where does the universe come from? And there are still many questions. Most of them are unanswered. The other search, I think, in astronomy is searching for other planets, other intelligent civilizations, or even sign of life, simply sign of life on other planets. I think that's the second quest. The first, I believe, the first should be trying to find out, answering the question, the big question of cosmology today.
I think there's a renewed interest in astronomy. You know, it really peaked for our generation, or the generation slightly before us, with the moon landing and the Apollo program. And then we had the space shuttle, but with the cessation of flying the space shuttle, people predicted that there would be less interest in astronomy. But you know, as Cassini and some of the other probes have demonstrated, a lot of interest is generated because we're getting looks at our solar system with the technology that has been put into these probes that we were never able to get before. And I know that the generation, my children's generation, has a lot of interest in these types of things, and I think that interest will continue. And those are the future astronomers and future amateur astronomers that are coming out of that.
I think what you're going to see, and what you're already seeing, is that amateur astronomy is making significant strides in the professional realm. You've got amateur astronomers finding comets and asteroids and near-Earth objects, and I think that's just going to continue to happen. I see a network of astronomers, maybe a network of satellite imagers. You know, if you can turn households into a satellite spot, and suddenly you've got a satellite telescope that's the size of a hemisphere, you know, just because amateur astronomers are working together. I see that happening. I see the entire community coming together and doing more.
In terms of making astronomy something that it can reach a much broader audience, we want to see more development of those accessibility options via the internet and ease of use, to try to make it a simple process. Using your iPhone is a pretty easy thing to do, and it'd be great if we can get to where people can access these high-end telescopes and take these terrific images and also do research. You think about the science projects we did when we were young, in some respects pretty primitive what kids can do today.
You know, one of the most successful programs that I've seen for engaging younger students and younger kids in astronomy is the Sonoma County Astronomical Society has a program where they have students, little kids, like write essays, and then they take the best essays on astronomy and they give them telescopes. And these kids, I've been surprised, it's mostly girls. These kids, they get these telescopes, they bring them to star parties, and they become little experts, little amateur astronomy experts, and they give public talks and presentations, and this is one of the most successful places. I'm a member of about 5 different astronomy clubs, and this is a great way to bring in a younger generation and help them maintain it, because we've seen over years now these kids come in and they stay in there, and this is a kind of program I think we need to scale it, we need to use it as an example and do it elsewhere. Just sort of one small example of one thing we can do.
We live in a fast age, right, where our movies and our music, our media, fast edits, instant gratification, loud and in-your-face kind of stuff is required to hold people's attention today for a half a second, which is sad. And so the subtle and the esoteric stuff suffers. I think it's very difficult to get a lot of younger people into this as a hobby. It seems like there's more younger folks, even women, who manage to get into the professional sciences, astronomy, cosmology, whatever it is, but in the amateur way, getting them to a telescope, getting them to a dark sky, inspiring that wonder in them is difficult, I think.
Giving someone the opportunity to not only see it for themselves, but do it for themselves, and say, here, have a look. If, for example, if they have the privilege of looking through a telescope and seeing the rings of Saturn, give someone that opportunity to do that and see it for themselves with their own eye. It has an incredibly powerful impact. And what I'll find, and for those who, like I say, there are many outlets where you have an opportunity, city star parties, outreach events. Once you see it for yourself, it's like a catalyst that the rest starts to take care of itself. The interest will be there.
One of the things that concerns me greatly is the fact that so many people are moving away from science and from facts. The fact of the matter is math, history, science, and facts matter. And so to advocate that and to advocate education, I believe that college education should be absolutely free. We should be investing in the brain trust of this country. And so to me, our job is to advocate science. Our job is to inspire people to really embrace what is right.
The stars are for everybody. And I would like, if I could do that, if I could spread the interest out amongst everybody, that would be the biggest contribution I can make. Skywatcher started out in 1999 in China. David Shen opened his factory, and this was his first brand, the Skywatcher. Does very well throughout Europe. Didn't really get a lot of traction in the US, didn't get a lot of marketing, which is why I was brought on in 2012. The product was not known, it wasn't advertised, so people's perception of the product was based almost exclusively on its price point, which is actually one of its features. It's a really good product for a decent value. So my job was to let people know, make them aware of the fact that Skywatcher products are in fact quality products at a value price. In the US specifically, we have been targeting mid to upper range astronomers, people that are a little more knowledgeable, maybe astrophotographers. We have specifically not focused on the lower end products, acromats or mass market tubes that you would find in department stores, that kind of thing. Ours are more specialty, simply because one, we don't have the manpower to handle the kind of volumes that the lower end stuff would require, and it's allowing us to really hone in on the message and to the people that would appreciate the message of quality and value. Well, the first bit of advice I give people is to be patient. There's a learning curve, and it is, it's science. It's science, but it's amazing science. It's science that you can experience visually and tactily right there in front of you. But it also is going to take time to become proficient at it. So enjoy. Don't be afraid to play around, and again, just be patient. One of the things that we do consciously is interact with the factory on a daily basis with feedback on new products or even existing products. We have a couple of people who are very hands-on, very active out in the field using these products. So when it comes time to modify the products, when it comes time to upgrade the products, we have very valuable real-world experience with them so that we can operate as a partnership with the factory and with product development. So what we found over the last few years is that the photography market and the astronomy market has a great deal of overlap. And by pushing photography products that do astronomy, we are able to introduce a whole segment of the population to astrophotography and astronomy that might otherwise not be exposed to it. We are the party animal of the astronomy community. We try not to do it in the office, but when we are out at star parties, that's definitely true. As far as what age range we're shooting for, Astronomy, just as a hobby, generally skews towards 40 plus individuals, 40 plus years of age and older, but we're finding that with the photography products, our star trackers, our other photography products, those are actually bringing in much younger people in their 20s. It is terribly important that we get these people in, otherwise the hobby dies, and we don't want that to happen. Some of the things that we've been doing is photography first, astronomy second types of products. We're also developing a lot of our products with Wi-Fi capabilities so that you can manipulate them through your phone with a smart app. So I think anything where somebody gets to use their phone is going to skew a little bit younger.
All right, guys, we are back. Jen is going to be here in about 30 minutes. It's now 11:30 Pacific time here in sunny California, although clouds are starting to whip up outside. Luckily, I took the scope down in time. Otherwise, we'd have had a ruined view. But that's fine. So just to show you the results from slightly earlier, the picture on the left is the 40% stack, picture on the right is the 10% stack, so gives you a good idea of what was going on. So I'm sure everybody who was watching the stream earlier was winding back looking for the plane that flew in front of the sun. I haven't found it yet. I don't have the time to try and search for it, so I'm going to have to download the video later and just go through it. But I'm so gutted that I wasn't recording at that exact moment. It is what it is. Hey, that's what lucky imaging is about, as they say. So what I'm going to do is I'm going to play you guys a couple of more videos, and we will be back at 12 o'clock Pacific time with Jen Winters from Daystar. So if you guys have questions and anything like that, now is your chance to ask them. We have compiled a list of most frequently asked questions, so we'll work our way through those first, and then we will go into any of your questions and answers that relate or pertain to all of this. So remember, Jen Winters is from Daystar Filters. She's actually quite knowledgeable on other subjects, especially when it comes down to like things like optics and the sun as well in general. So yeah, it's well worth hanging around for that in about 30 minutes or 30, well, less than 30 minutes at this point in time. So again, we'll see you back here in just a moment.
Hello my happy Astro campers, and I am back with not necessarily a tutorial this time, but this is more an informational video about doing imaging specifically with solar. So what I actually have here is the sun, strangely enough, and we're going to be looking at 8-bit versus 16-bit in terms of color space. The program I'm using is SharpCap Pro. And as you can see in the drop down box here, we have two options here for two different settings, 8-bit and 16-bit, and if you have a color camera, you'll have other options such as 24 and so forth and so on. So what I'm going to go in here is, these are probably more advanced settings that we're looking at. Specifically, we are paying attention to the color space and the type of file format. Now, typically when you're using default settings, it is actually preset to whatever it determines is the best fit. Now, in my particular case, I prefer to use SER files purely because they are full uncompressed. Within 8 mono, for example, you have the option to be able to do AVI files. And what we're going to do here is we're just going to play around with the exposure settings for a second here. What you'll notice here is there is a frame rate that is located down here. Now, this tells you how many frames that we can capture depending on your system. Now, being selected in 8-bit versus 16-bit, we're going to obviously see a big difference. When we're here in 16, the frame rate actually drops down to around about 60 frames per second, and we can actually change the performance based upon the exposure time. So if I was to increase it, you can actually see the frames per second drop down quite drastically. So I'm just going to go back and reset this down to something that I use quite frequently. If you notice that there is a gain setting here, this obviously does not affect the frame rate, so if you feel that your image is a little bit too dark, it's actually better to push the gain up than it is to increase your exposure time. So we're going to take a quick look at the high-speed mode here. This is only really applicable for a legacy camera of some description, and it doesn't support high-speed modes. You can turn these on and off. This does affect the performance. If you have an older camera and you find frames being dropped, because basically what happens here is your computer itself cannot actually buffer the images faster than it's pulling it down. So you kind of have to slow everything down, and the easiest way to do that is to simply modify the high speed mode. Typically, if you have a USB 2 camera, you need to set this to be off as opposed to on. If you still have other issues, even with a USB 3 camera, depending on who makes the actual camera, you may have to experiment with this. Typically, this results in dropped frames, and you can actually see this down in the corner within the brackets. Of course, this particular system is set up to be optimal, so I very, very rarely get dropped frames. Now, one other interesting feature here is if you needed to do some type of analysis on the frame rates, you can actually set the timestamps with the number of frames, and that shows up in the top left hand corner. Typically, you can actually modify this so it shows up in different places, but typically I keep this off because I don't want a timestamp all over my images because I'm not doing anything specific. Now, one of these other parts that we're going to look at here is the pre-processing. You may have noticed that in a previous tutorial that I was messing around with dark frames and flat frames and things like that. In SharpCap, you actually have the ability to do dark subtractions and apply flat frames live directly to the video. I generally don't like to do this because I prefer to do all the calibration frames at the end or afterwards, but if you were doing live astronomy and you wanted people to see a better image, you can go ahead and make your flat frames ahead of time and then simply drop them into here. It actually does a pretty good job in doing the calibration part, but typically what I found is once I've actually captured the footage with all these calibration frames applied, it doesn't tend to look as good as I was expecting it to be. And of course, the band suppression does a very, very good job if you tend to get a lot of banding. On the IMX 174, there is a bit of banding that can be noticeable, but in this particular case, we are always going to be using calibration frames after the fact, since we are not actually doing some kind of a live astronomy here. So we're going to take a quick in-depth look into 8-bit versus 16-bit when it comes down to processing, specifically on the sun, because I generally feel that shooting in 8-bit and 16-bit when you're doing solar imaging, there is a huge, huge difference. So Let's switch over and I will see you back in just one moment. So I've gone ahead and stacked the raw video files for both 8-bit and 16-bit respectively, and we're going to have a look at the differences between the two. Now I'm working in monochrome for now because I kind of feel that it's the best way to actually get a better idea and a better look into how good or bad one particular image is versus the other. Now, in order to keep this fair, I've also used the exact same settings when it comes down to processing and doing all the sharpening. I didn't want to purposely make one over sharp versus the other, otherwise it may seem a little unfair. So right now what we are looking at is the 8-bit version of the surface of the sun, and we actually have a small active region right here, which is actually a sunspot as well. And when we actually look, first things first is I kind of feel like the image is very, very soft, and the way that the white has blended into the actual edge of the sun, or more commonly known as a limb, doesn't seem to be not as nice as it would look like normally. And even more evident is the prominence details just seems to be very, very wispy. Of course, this could always be attributed to bad seeing, but both of these videos were shot literally back to back. So now we're going to go over to the 16-bit version, and already there is a huge significant difference here. The prominence details, especially the one in the corner here, is a lot sharper, and it almost looks like there's more shading to it. And of course the actual blending looks a lot better as well. And then obviously the active region here is more pronounced, and even some of the detail up in this area here is a lot better than it would have been compared to the 8-bit counterpart. You can just about make out this area here is the same section. So I'm also going to have a look at the actual original file before it was sharpened, and there's not much discernible difference here, other than it does seem slightly sharper for the 16-bit. Now this is the unprocessed stacked file. The idea behind why I'm trying to show you this is so you can get an idea and an understanding between the two different files. Again, I'm going to make these files available to everybody who is a Patreon subscriber, so you guys can download that data and have a go at processing it yourself, and then check out the difference between 8-bit and 16-bit. But one major important part that I do want to point out first of all is when working with the 8-bit file, there is actually more data hidden inside of all of this. So typically when you're working with an 8-bit file, you're not going to get the color and the dynamic range as you would do compared to a 16-bit file. And I can show that. We're going to convert this over to a true 8-bit file, and I'm going to mess around with the HDR toning to see what the major difference is going to be. And already I can tell just by looking at this, it's not looking very, very promising, and there's a lot of noise, especially where the blackness of spaces and where all the prominence detail would actually lie, including all the spicules. It just seems very, very muddy, very, very noisy, and just simply not very good. So we're going to take a quick look now at the 16-bit version, and you can see there is already way less noise. And if I increase all the detail, we can actually start to make out that the prominence details is obviously a lot better off than the 8-bit counterpart. Now again, there's obviously a clear trade-off here, because in terms of file sizes, the 8-bit versus the 16-bit file, the sizes is absolutely amazingly different. Now, just to give you an idea, we're going to have a look at the original 8-bit file here, which is like 4.6 gigs, versus the 16-bit file, which is double the size pretty much, at 9 and a bit gigabytes. So it's quite a big difference here, and it's actually going to be even smaller if I had actually saved all these files in AVI format. In fact, it probably only would have been roughly a gigabyte, if that, for the 2000 frames that I had actually captured. So hopefully this gives you a good insight in the differences between shooting 16-bit versus 8-bit, and hopefully this will clarify a few things for you, and I look forward to hearing from you guys and seeing some of your work.
All right, guys, we are back live with Jen from Daystar. It's like a madhouse in that place right now, and it's
what?
You guys are having too much fun. I think we should just like have a spy cam in the corner watching what you guys do all day.
Oh, no. We have those. We have lots of those. Yeah. I don't know how well you know our engineer Fred. He's camera-holic. He has like 4 different servers that you can put multiple cameras on, and at any time we may be out of the country traveling. He'll log in and look at all the cameras and see who's parked in the parking lot, and so.
Oh, I bet. I mean, I've got the same setup at home, so I'm just as equally bad. So
what do we have? 16 cameras? A lot. That's before you count the wildlife cameras. Those you have to go and actually change the chip.
Oh, wow.
We had to put wildlife cameras in because we saw bear tracks in the back field. So,
really?
Yes.
Okay, that's right. You guys really are out in the middle of nowhere. So for those of you who don't know, Daystar is located here in the US, and where she lives is pretty much the compound of where the entire office studio slash.
You could put an X in the middle of the country, separate it up and down, and you would pretty much come up to Warrensburg, Missouri.
So if aliens were going to invade, and they go, let's go for the middle of that spot, they literally
right there.
They are literally going to land on your roof.
Well, that is if the aliens understand the border of Canada versus Mexico. That Canadian border issue, they'd have to really pick, that. And I do have to say, and I know maybe this has happened to you if you've traveled internationally, oh, you're from the US. Do you know my brother Harold? He's in Chicago. So imagining that, inside the US, everybody knows each other.
Yeah, especially Harold from Chicago.
Absolutely.
And in fact, Harold from Chicago is on the line. No, he's not.
Hi, Harold.
So we've got an hour to kill, essentially.
And we're going to completely murder this hour.
And we have a list of questions, and what I'm going to do is I'm going to start with always the common questions that are always asked. I get these questions, you get these questions, and anybody else doing solar gets these questions. So we're just going to go through some of these, and then we're going to also open up the floor. But before we do that, let's talk about some of your products, because you don't just make the quark, you have more than the quark.
Well, actually, quark came on pretty recently. I think it was 2015 was when we developed it. But Daystar, believe it or not, Daystar predates Meade telescopes. The original, yeah, right. I have stock in my possession from the previous owner. I bought the company 2006. I bought it from the former owner Dell Woods, who passed away shortly thereafter. And Dell had been building filters since the late 60s, early 70s, and our earliest Aden-Sky telescope was spotted in 1973.
Wow.
And I have service filters that were built in 1973. And the old style of filters, why don't you grab me one of those up off the top? The old style of filters, they're still floating around in the backs of cabinets and labs everywhere. So here's one of the older, you can see they were all silver, and they had a power supply. I don't know how many people keep this handy. That's not a really convenient power supply. Their electronics needed upgraded. And so as soon as I bought the company, it was abundantly clear that we needed to do some upgrades and modifications to the designs. And give me that one. Yeah. So with the help of the engineer, this is where it all came together. We started, let's try and make it more convenient and more simplified than it used to be back in the bad old days. So, because we all remember the bad old days. So our other mainstay was that we took that filter and we modernized the electronics and put it into a new housing, which is the quantum housing. And the very first thing is to have power that was 12 volt DC. You can always get a wall wart, but we shouldn't have to have an inverter. So this is effectively a 32 millimeter clear aperture, and you would put this on the rear of your telescope. The trick is that in order to have that narrow bandpass, these are really, really narrow. A lot of people have a hard time grasping how narrow is. And I have a new method for trying to help describe. You'll like this, Tiffany. Yeah. So the coronavirus is pretty small. It's actually quite a bit smaller than even like a common virus like rabies. Rabies is about, what do they call it, 60 microns. And the coronavirus is 120 nanometers in size. So 120 nanometers in size means that's 1,200 angstroms across. And an angstrom, let's say a bandpass filter, the chromosphere is a half of that. So that means the bandpass of this is let's do the math here quick. It's 2,500th of the width. If you write a coronavirus into 2,500 slices, that's how wide the bandpass is. So we're really starting to get into tiny fractions that are just really hard. The same way astronomical things are hard to conceive, the tiny things are hard to conceive.
So theoretically,
we make quantum.
Right. So theoretically, I can run around with a hydrogen alpha filter and say, hey, the coronavirus can't get me.
Ding, correct.
So yeah, now suddenly we're going to be selling sheets of this stuff now for people.
That's another project.
Yeah, that's another thing that we can talk about at a later time. So you also have not just the filters, but you also do the scopes as well.
We do. Once you bring me we just recently came out with our little bitty, our baby fun scope. This is the most entry level itty bitty that we have. And what we did here, we tried to take the basics of the quark and its interchangeability, and we'll see more about that interchangeability in a minute. But we just tried to compact it down. This is, another company makes a 40 millimeter telescope that's popular. We wanted to put this in that price range, but it's 60 millimeters. And so we tried to just cost reduce the daylights out of it while still having all the benefits of the quark. So this one just came out last year?
Yeah, last year.
Yeah. I don't know the price.
It is $7.95.
Tiffany says it's $7.95. I have to ask her. I never know these things.
There was a price.
There was a price. Yeah. Okay.
Yeah.
So
prices are relevant at this point in time. So then you have the larger versions. Now I don't expect you to pull one of those out of thin air, but you have
one.
Oh God. So just so you guys know,
it's lighter than the Easter Bunny.
oh look, hi Tiffany. For those of you who don't know this, so for those of you who don't know this, the person that answers the phone is that girl there in the background. So now you know who this person is.
Does this tell you how light this telescope is? We did an ultralight weighting on it. I'm not even touching. Carbon fiber lightweight, we call it the QT. It's 127 millimeters. Here we go. And it's basically that quantum married into, and this is our own custom designed, custom fabricated H-alpha glass that was designed, prescribed, and coded just for the H-alpha wavelength.
Oh, wow.
And that's not done. So obviously, our goal is to optimize everything. And yes, a big beauty of Daystar is being able to take the filter and putting it on your already good telescope. But there are just some people who just want to have a dedicated setting. We see sometimes that's in outreach. Sometimes the guy just doesn't have time for all this fiddling around and putting pieces together and optimizing. And the other advantage of a dedicated telescope is that we can put design features into a dedicated telescope that other telescope manufacturers can't.
Right.
Or don't really worry about. Solar has some special nuances that make it harder to maintain that contrast. If we want to beef those up in a way that's special for us, that really, can help that observer in their performance.
So out of interest, what is the wait time on a scope that big?
A couple of weeks.
Oh, so it's within reason then.
Yeah, the original 127s are still available for custom order, but this new QT, what we're doing with it is we found it was very popular with the quarks to not have to decide a 0.6 or a 0.7 angstrom. the difference between a 0.6 and 0.7 angstrom is 1/12,000th of the coronavirus, okay? So the time is always spent in classifying and qualifying that one specific sample of the mica. And if we can just put them either in a prominence or a chromosphere range, well, then it's a lot faster for us to deliver. And that's why these QTs, we usually deliver those in 3 to 4 weeks. Sometimes we have that one in stock.
So these are based off of the quantum, not the quark, though.
Technically, because it uses the patented marriage of the optical elements and many of those design elements, it falls under the patent protection of the quark, but it uses some of the design features of the quantum as well, with the faceplate and the button control, the tuning range, and the full aperture being larger. So it's a bit of a marriage between really 3 technologies.
So as crazy as this sounds, what is going to be the difference that I'm going to see out of the Solar Scout versus the QT?
Aperture, 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 and aperture. There's no substitute for cubic or square inches. Yes, that's it.
Cubic feet, I mean, that works too. If you get a telescope that big, I'll be very interested.
All the motorheads always say there's no substitute for cubic inches, or there's no replacement for displacement. There's just no substitute for aperture. And if you've got the aperture 60 millimeters, there are days you can't really resolve anything with the 60 millimeters, and you can't. If you've used a Daystar, I think you have, you grasp the difference between full disk and getting in there and seeing all those high-powered details. We keep full disk up on the background at any given time. You can see we always have to know what's going on outside. You can see we're socked in clouds, but a full disk image is nice. But if you want to go in and get those Ellerman bombs and the spicule and field transition arches, all the really, really good stuff, you just need more aperture to resolve more. And so we're starting to have more observatories, more permanent installations. That's where they've really been going in the last couple of months. We've had 3 deliveries this spring that went to permanent observatory installations. Yeah, they're exporting really well. And again, that outreach application for the dedicated scope is a good fit. But again, our best customers already own a telescope. They love their telescope. If you ask anybody to tell you about their telescope, you're going to lose an hour. So
of my life, yes. And it's even worse when they have more than one telescope.
Right, right. Yeah, that's over here. So we know that a customer, I mean, some, like an AP owner, how long did you wait in a waiting line for your glass? You took a lot of love and patience and resources. We know it's a lot of scratch to go and get your telescope, to pick your telescope. And so, maybe you only have one mount, and to be able to put the filter onto that telescope safely and have good results really can make a big impact in your experience with your telescope. I keep saying you and your telescope. It's become, what is your experience like for you? And the customers just really like the experience of putting a filter on their telescope.
Right. So this is a great transition into these questions, because there's quite a few here. So I've got a feeling, hopefully we don't run out of time here. I already have a white light filter. Can I use that as an ERF?
We get that about 3 times a week. No, the reason you can't use a white light filter has to do with the way the filter is filtering. It's reducing down all the light from the top down. And so if we have a spectrum that has all the colors going across the spectrum, if we have that spectrum that's going across and we want to squish down how much light is getting through this way, then that red light will still get through. And this is basically what a colored filter does. Here's your red colored filter, and then there's your yellow colored filter. It's blocking everything down here and passing everything up north. So a white light filter will reduce it all down by 99.99%. So it's going to do that to the red also. you won't see any, your transmission will be 0.001% of hydrogen alpha, and it'll be black. You will see nothing.
Right, and then we're back into the doing nighttime photography where it takes a 10-minute exposure for anything to even show up.
You wouldn't see anything. We've had them try.
I know. I've tried it before too. It's just like, yeah, this ain't gonna happen. Why am I wasting my time?
Yeah.
Okay. So then the interesting thing here is I get a lot of people ask me this. They have a Petzval style telescope, and you can't use a quark on those. How true is that?
That's not true. And I should advise you that a lot of these ERF rules I made up. Okay. You've always heard, Scotty, don't tell them the actual specifications. So as time has passed in the 13 years since I've owned the company, I've noticed it was really wild west on who needs one, who doesn't. And so I've been trying to establish a set of guidelines and suggestions. And some of these are based on the customer's comfort level. Back with the discussion about that AP owner, that APO owner waited, what, 10 years on a waiting list? His level of risk tolerance is so low that he's just going to be more comfortable with a front mount energy rejection filter. But the Petzval issue has to do with a concentrated beam of light. If you're taking 150 millimeters of aperture, 125 millimeters of aperture, and you're going to concentrate that light down, this is how you burn ants. So you're going to concentrate that light down to a smaller beam, then the amount of energy is concentrated more than just on your hand. I mean, my hand doesn't light on fire, and my hand is, the size of an aperture telescope. So we know this isn't enough energy. You have to concentrate it. The second issue has to do with how much energy is absorbed by my hand. If I was going to focus that magnifying glass onto my hand would now get hot because my hand can absorb the light. All right, my hand isn't transparent. So with an aperture that is clear, what's our transmission of that second element that's back here in the Petzval that's getting a concentrated beam? For starters, it's clear it really isn't going to absorb anything. It isn't going to get hot at all. Then there's a question of what about those coatings? Are the coatings at risk? So you have concerns over whether or not the coatings could heat up or react or have an exposure to the UV. So for that example, a front mount energy rejection filter would protect those coatings or any perceived fear or concerns that you have that your clear piece of glass might absorb heat. So the answer for Petzval is to put a front mount energy rejection filter on it.
So little sidebar from this, because you didn't mention, because this is not part of the list, airspace, oil space. Airspace, perfectly fine. Oil space is questionable.
I'm in trouble for this. Boy, did I put my foot in it. So when I made these recommendations, again, based on the perceived risk level and the risk tolerance that people who spend all that money on their astrophysics had. Takahashi owners, astrophysics owners, tech owners all kind of seem to feel a certain way about their beloved. And so I have had that recommendation that APO owners should really just have a front mount. They have enough money. It's not a question of money. Well, they used to have enough money. But then one day I was at a show in Tucson, and Roland came up, and he wasn't very happy. And he stands here in front of my booth and kind of gestures at me, Jen, why are you telling all my customers they need front mount energy rejection filters? I'm like, well, have you met your customers, Roland? They just don't want the risk. And honestly, Roland was offended because that implies that his oil might react with the UV, which is a problem he solved, the industry solved probably 4 or 5 decades ago. And it's irrelevant what I'm going to tell you. The astrophysics owners need to call astrophysics and ask astrophysics directly. Everybody's afraid that they're going to get sued because somebody made a recommendation in their oil space. Again, I only say this based on my understanding of the assessed risk and how comfortable the owners are. I don't have any empirical data because there has never been a telescope that was injured by pointing it at the sun with the Daystar on the objective has never been injured. We've had people pointed them at the sun and injured other things where the beam shot out the back. And apparently some guy thought paper baffles was a good idea. Don't put paper baffles in your solar telescope.
You know, the funny thing here is, without telling people anything, doing a setup and not having any blocking filter at the other end, you've essentially made yourself a laser gun.
A bit. Just got to go find some ants.
Yeah.
There was a cartoon somebody did with Al Nagler with giant eyepieces as a kid with ants. That's cute.
I've never seen that. What? Hold on a minute. Where is this?
Oh, it was decades ago.
I gotta find this now. So basically, the short answer is, if you are uncomfortable with anything, please use an ERF.
Well, please use a front mount. There are also rear mount ERFs.
Yep, there are rear mounts.
Yeah, and the UVIR, this is what Roland Christian told me on a day that he uses when he observes. And again, the energy rejection, it doesn't just protect the telescope, it also prevents the unit from overheating. Because if you have heat gain inside that system, then the filter will overheat and perform poorly. And so there are issues related to that. But the truth is, can you hear me, Amy? The truth is, it's bizarre to think about that your telescope is going to gain more heat pointed away from the sun than it is towards the sun. So think this through. Towards the sun, this is clear, and all the energy, oh yeah, you can see the block.
Yep.
So pointed at the sun, all that energy is going to come all the way back here. The front element of a Daystar is reflective, but here's where it's going to gain more heat. So it sounds counterintuitive, but...
Well, it's not. Larger surface area. That's what it really is. The next question, why do I need a front mount energy rejection filter on a 150?
All right, so back to the guidelines about energy rejection. 150 millimeters is the point at which you're starting to get up an aperture that we need a different discussion altogether. And we're really hoping that that would encourage the phone call, that we would get a chance to reach out and speak to and work with that customer who's now pushing the limit of daytime seeing. And that we ourselves experimented with all sorts of different applications. We went up to an 8-inch. We've tried, we did funny thing with a ring aperture. That was a mess. But at 150 millimeters, you have a lot more energy coming into the scope. You may actually need to have both that front mount or the UVIR and the front mount. I have a little graphic here. So this is the spectrum of solar radiation, and the red bit is what actually makes it through the atmosphere. And so you see that if we're going to pass all of the visual spectrum here, that's the bulk of where this energy is. And so the UVIR, yeah, it's going to cut below this. There's not a lot below. It cuts all of this above, but it leaves like half of this in here. And so if you use both a colored glass filter and a UVIR, then you really only have about half of the big tall chunk here. You have none of this and only half of that. So it can reduce the amount of heat load that you're putting on your filter. And so if you're out there and you're tracking all day, every day, and you're imaging because that's why you're using 150, if you're doing this, then your filter could start getting too toasty, run up off of, because there are little bits in here, while they're never, ever going to catch on fire, you can see that there are black bits that could absorb energy and start to slowly radiate that through, in addition to what we need the filter to heat to.
So I image with a 150 and I don't have an ERF on the front of it. How safe is that? Needless to say, safe. I do not look through it.
So the question really isn't about safe at 150. The reasons to use it have very little to do with safety. They more have to do with, they have more to do with thermal control and with the actual discussion of how much aperture your local seeing conditions will support. We really can't stress this enough, because daytime isn't nighttime. Just because you have 14 inches of aperture that you can get away with at nighttime, nothing whatsoever to do with your environmental issues with daytime seeing, because at nighttime, you don't have this big mean sun that's cooking the ground around you. causing all these thermal waves, like looking out over the desert road, when you see all the mirage over the highway, that doesn't matter at night. You have other issues at night. These are our uniquely solar issues. And our tests have shown at about 125 millimeter, 110, you can get away with that in almost any condition. But when you go to 150, it's time to start looking at different times of the day, local environment, what you can do to, and I'm sure at 150, you've noticed that, you know, morning seeing is better than noon seeing, or in your setting, maybe afternoon seeing is better than, so you'll have different times of day that perform differently. And again, the energy rejection, maybe I made a mistake in making this suggestion, but we just really hope that there's a discussion about what you can do at 150. You're safe. You're not going to burn the house down. I am reminded, however, you said safety and aperture. We did have one instance, a filter came back. It had been installed on a 16-inch. It was a university, I won't say which one. The grad students put it on a 16-inch LX200 with no ERF for about an hour. And it was fine until it kind of started to drift off the sun and the aperture moved over onto the Delrin and started smoking and melting the Delrin. And so they took it off when it started smoking and said, I think something's wrong. It survived. We've had them crash from space and survive. They'll be fine. We just, you know, replace the little plates on it. It's fine.
You know what? I thought I'd never do this, but I did leave the stupid cap on once and put the quark in, not paying attention.
Welcome to the club. We have T-shirts.
Which luckily for me, and I know Tiffany has seen my setup, she goes, why do you butcher your setup? And it's this hideous thing and you've added all this crap onto it. I said, for that sole reason, when I forget to take the goddamn cap off, the worst that's going to happen is it just ruins my UV-IR cut filter, and I could pull that off and put another one on.
Yeah.
Been there, seen it, done it.
Yeah. It's a problem.
So next question, what about on my 80 millimeter? I mean, we've gone from 150, now we're down to an 80.
All right, so I have listed the 80 millimeter as the maximum aperture I suggest. Just pick rules randomly, no.
Scrolling from the past.
In the past, the former owner of Daystar, Del Woods, he sold calcium K-line filters. And the story about K-line is very long, but in his effort to, how do you do energy rejection for calcium? If that's cutting off, you know, again, we're going to cut off the light that's below yellow. Well, calcium's way down here. All the colored glass CRFs would filter out calcium. And so his recommendation was just don't use more than 80 millimeters. And there just really wasn't enough, you know, your hand is, this is the kind of scale of the amount of energy. I'm not going to spontaneously ignite from sunshine hitting my hand. And likewise, the elements in the filter are fine. Nothing in there has ever been damaged with 80 millimeters. So for the, let's see, what was it? 45 years that we've been doing calcium, there's never been any issues with 80 millimeters and under. And I think that's a pretty good run to be able to assert that 80 millimeters is safe. Unless you have paper baffles.
So I'm going to switch these questions around real quick because it makes more sense to ask this question now than it would be the other one first. What about SCT scopes? Like Schmidt-Cassegrains?
So we have look, a little LX200 here. And I wanted to show, you'll use an off-axis energy rejection filter. And so what we do here is, this helps in two regards. We haven't really talked about focal ratio, but for very narrow bandpass, we have to have the light coming very straight on towards it. And so to have a light cone that's angular, this light is at the outside is a problem. So if we reduce the aperture down, then all the light's coming from the same angle. Then we have an exit angle problem. We would sort that out. But for SCTs, we reduce the aperture and just offset it so that it's not in the middle of the corrector plate. So this just goes right over the front, and then in the back, remember how I said we don't need to Barlow because we reduce the aperture? Well, then we have a quark for that. This is a combo quark. And that would just drop in the rear with one quick exception. Because this is off axis up here, we need to kind of cock the angle back here to compensate for the angle that the light's coming out off axis. And so we made this funny little, I don't know if this is going to show up. It actually has a little bit of a wedge in it with the angle. And we have a little tag that says align that to the ERF hole. So you line this up, the orientation of the ERF, and boom, there. That's complicated, right? Oh, an eyepiece. So. There. There. So SCTs, we get an off-axis ERF, and we use the combo with the wedge plate aligned.
And there you have it. You can actually use an SCT with an off-axis ERF. And right, so but that's the thing. That's a big difference between the combo versus the regular. So you can't use the regular quark on there. You have to use the combo.
Well, we've had folks try. There's one fella who's trying to use a full aperture like a C925 and then put a quark on the back with Barlow's. Again, their earlier conversation about maximum aperture, we tried 8 inches of aperture with the Barlow the same way we would do on a refractor, and it just, we didn't find a single setting where we could actually get good. Not having good seeing in nighttime, your stars might dance around, but with the sun, there's so much light coming through and it's dancing around so much, you're blurry.
Mm-hmm.
So you can't get a hard edge of the sun, you can't focus, and that becomes a problem with, there really is no point. You're not gonna have a good result, and people are gonna try it, but this is our recommendation.
Right. So now, what about Newtonian scopes? Because or any Newtonian design scopes.
Well, we've struggled with that because Newtonians, you remember you put the eyepiece into the basket itself instead of having, and the focus travel is very short. That's because on a Newtonian, the point where that eyepiece goes is actually inside the basket. So, darn those baskets, that you can't, it doesn't work. You can't reach focus by putting that onto a Newtonian. And again, you would have to have an off-axis ERF, which is, they're big. So what are you going to make a 20-inch? If the energy rejection filter for the telescope would cost more than a new telescope of a similar aperture of what you would get.
So now, I know this is kind of like beating around here again. What about the Maksutov variants of an SCT or a Newtonian? Because they have correctors on the front of them.
They can work. Often we've had, well, for example, the Questar quark. We made one specific for Questar, which fits with their threads. We call it Planet Questar because they have their own wonderful itty-bitty tiny little threads. And that's a Maksutov. And we just put a full aperture front mount, pardon me, front mount energy rejection filter on the front. And then they actually have this neat little fligger that flips in between magnified. So it's got a Barlow inside.
Yep.
But Maksutovs, usually they're in the F10 to F15 range. And so a 2x Barlow works great on those. Then we come into telecentricity, and that's another discussion.
Yeah, as a whole, we don't have time
A
for that
whole
one.
other thing.
Yeah.
It's an important thing, okay?
It is
an important thing.
No, it is. Walk us through how we actually get a quark onto a refractor then.
Well, that's pretty easy. I have another section over here that we've set up just for this point. Where's my telescopes? There they are. So here's the fun bit about the quark. I can take my quark here. Here's my eyepiece. Do I have an eyepiece? Eyepiece in the quark. And so on. Am I in here?
Yep.
Here's a 66 EDA-PO. Just put it in there and you're ready to observe. You don't need a front mount energy rejection filter. There's an 80 millimeter F480. He's an F6. I really like this, this focal length because it's the biggest aperture that you can use without a UVIR, and it still gets a full disc through the quark. There, you start getting a limit on how much the front element of this is so small. It's kind of small here, but still in blocking filter land, 12 millimeters isn't that shabby. So at that point, we can still get a full disc through. We don't need an energy rejection filter that's 80 millimeters of aperture. It's pretty fair. So then when we go to the next size, this is an AT111, pretty nice scope. I like this one. At this point, we're going to add UVIR cut onto the diagonal, and I have yet to meet a diagonal that doesn't have a thread. And the reason we put this on the diagonal is that, again, you have a piece of optic that has a concentrated beam. And this is the first place that concentrated beam could encounter the sun. And we just put this into draw tube, bring the cork here, and we're in. I should also comment, I know there are a lot of concerns about back focus, that folks are always worried, how far do I need to change? And the advantage of having that Barlow inside there is a little bit like with bino viewers. If your viewers have used bino viewers before, you know that with the bino viewer, you need to borrow the Barlows in front of there so that you can achieve the focus. This 4.3x that we have in here allows the room for the rest of the filter in such a way the focus really doesn't change versus an ordinary eyepiece when you put the quark inside. So many of those concerns really just, they don't apply because the quark occupies the space that the back focus is added, provided that you apply it correctly at the rear of the telescope. So then here's a TOC 120, and when we use our TOC 120, yeah, why don't you run around and put that on there, Tiffany? So with a 120, you could use a UVIR, but Takahashi owners, they just want a frontline energy rejection filter. And we make these in size ranges that are every 10 millimeters. And then we add the, actually, let me see that real quick. So
don't drop it.
I'm gonna have to make another one. So we make the aperture every 10 millimeters, and then your front clear aperture is based on your choice. Because remember the off axis, that would use is very small with a big cap, and everybody's dew shield is unique and different, and I'm really sorry, but the manufacturers, they sometimes change those dew shields. Just telling us what telescope you have isn't good enough. We really need a measurement. Sometimes they're little screws or heads butting out. All we need is the measurement of the dew shield that it'll be on. Pointing out also that we ship it with felt inside here, so you can put felt to keep it from marring the surface. And we also have these great little nylon thumb screws that will come through and contact your dew shield without scratching the dew shield. And another last note, the glass is supposed to rattle. That's because this glass is colored and it blocks by absorbing all that light, all that energy, which makes it heat, which makes it swell. If this didn't rattle, it would take one use and it would snap and crack in half. So your dew shield has to, or your ERF has to rattle, and then he'll just mount up on the front.
You know what? You wouldn't believe, I've actually sold one of those before to a customer, and he taped it because it was rattling, and he was saying that it was like bad quality, and I was like, okay, hold on 1 second, and I went through the whole spiel with him. By the end of it,
we install a letter. The letter goes with the ERF in the box. And that letter is,
you know, people don't read that.
The letter, it's called the ERF should rattle letter. It goes on top of the ERF in a box. But maybe he got it secondhand. We don't.
But no, I had to go through it, and then once I went through it and went through the science behind it, that he got it, and then goes, "Oh, you guys really thought of everything." And I was like, "Yeah, we didn't just give you a dud filter. You know, that's not how we work." Jumping ahead.
There's a lot about those filters that's critical. Do you mind if I show you?
Sure.
We have a lot of folks who go, they're so expensive. Why does that glass have to be that expensive? And folks don't realize when you put that energy rejection filter in front of your objective, that has to have the surface figure that your objective did, or it's going to distort your view. So, we need to do quarter wave glass. Here's a good example. We had somebody who sent this guy in, or we've got it in a circle. I don't know. We sourced this glass, and it's perfectly smooth, lovely, gorgeous, scratch-free, no bubbles. Don't get me going on bubbles. There's a bubble specification for glass. Do you know this? When you source glass, how many bubbles per millimeter?
Yeah, don't get me started, please.
So nice, lovely piece of glass, but is it of an accurate surface figure? This is the Zygo report for this piece of glass. So if you take just sun colored glass and stick it in front of there, it will block the energy, but it will also completely trash your surface figure or your effective view. And that would be, something else to consider. This is what looking through bad seeing is like also. So if you're looking through bad seeing, the air is doing this. So we have a lot of, little details.
Yeah, that's a funny thing. I'm glad you mentioned that, because I always get that when somebody says to me, can't I just put a piece of yellow or a piece of red something in front of it? I said, of course you can, if you want to degrade your image. And they don't believe me. And they'll run out, they'll try it, and then they'll say there's something wrong with the whatever it is that they're using. And I was like, well, what was your ERF that you were using? I said, I tried that red thing. I had the piece of red acetate. I'm like, oh God, here we go.
Oh, wow. Yeah. Now, in another video, we're putting together a video about flat fielding.
Right.
And that would be really great for that. Because
oh, that would be great.
Yeah. As a Ziploc, we've done a bunch of tests. Ziploc bag looks pretty good. The fruit bag is another one, but.
Oh, boy. I'm looking forward to see that one. So what does that little knob do that I keep seeing on the Quark?
Oh, yes. So the knob, here comes most frequent question number 7. I like to sometimes say that I put the knob on there because the astronomers need a knob to turn. They just do. But I wish it was that simple. Actually, let's do a little spectroscopy because we can.
Yeah.
This is Majel. She is the voice of the computer, because when I operate her, sometimes she sings. Anyway, she's the voice of the computer. You get it.
Yep.
So the spectrometer here we have tuned to H alpha. I'll show you on the screen here. You can see on the screen this nice little emission line. This is from the actual lamp. I just put the lamp of hydrogen on here. So we have hydrogen alpha from an emission source. We know that's the correct wavelength. We're going to tune to that wavelength again in the range of, a couple 10,000, 12,000th of the size of a coronavirus, just little details. But then if we put an etalon so you can see now, let's look at that monitor. You can see now that we have these peaks. Can you come over to my right hand here and hold this? No, you're blocking with your hand. Oh, that's true. Oops. So, Tiffany's trying to burn her hand. So these are they call these interference fringes. These are the transmission peaks coming out of the etalon right now. And so this peak is a 6560.7. Its half bandwidth is 0.28 angstroms. And if I heat it, based on how much we know about our process, if I heat it to 108 degrees, it will be on the hydrogen alpha line. So if, however, we tilt, did you notice that they jumped there? Can you see well enough?
Mm-hmm. Yeah, I can see the screen. I mean, a couple of people.
Around. The reason they're jumping is that I'm tilting them. I tilt the etalon, and they move down in wavelength. They shift blue, which is which means if I add heat, they go up in wavelength, and if I tilt it in any way, they go down in wavelength. Again, 1/12,000th of 12,000 points across that coronavirus. 12,000 points. You're not cutting it like a piece of pizza. You're cutting it like dust, to the degree that we have to tune. And so each knob click on here represents 1/12,000th of the span that coronavirus is in tune. And so to center on that hydrogen alpha line, which is actually 0.28 angstroms, 0.28 angstroms.
Oh, we just got disconnected. Hold on 1 second. Panic! Marvelous invention, the cell phone. Ah! Oh, you have got to be kidding me! Don't you love Windows Update? Maybe, maybe not. So for those of you watching online, we're reconnecting right now. Microsoft really boned us today. It wasn't anything else. It's just Microsoft Windows Update decided to do an update. All right, don't worry about it too much. Just reconnect when you get a chance. And I'll just keep talking because everybody's seeing us doing this live. They're probably thinking, what the hell are these crazy people doing? All right, just rejoin the meeting when you're back. All right, I'll see you in a second. All right, I'll see you in a second. All right, so we're going to reconnect Jen. Thank you, Windows, for doing a Windows update. Good timing. So yeah, I can see a bunch of questions coming through. Really do appreciate them. We will try and answer them towards the end. We just have a program that we've been working through because this is part of the presentation. I mean, it's pretty smooth so far up until this bad point, but hey, this is what happens when you use the internet. It's a live broadcast. Put the speaker on the phone while her assistant works on it. Well, I would, but you should see them both panicking. When something goes wrong with these two guys, it's funny. It's like a comedy show watching those two panic. I wish I could see the camera on them right now with them like doing this, running around in circles. It's actually very, very, very amusing. For us, it is. For them, it's not amusing. They're panicking. All right, let's get her back in. So hopefully we should be able to see her. All right, so we just got to wait for the audio to connect. Hold on a second. There we go. Right, we're back.
I can hear you. Can you hear me?
Yep, we can hear you now.
Thank you, Windows. We love you.
I was just telling them that when something goes wrong horribly with you guys, it's really funny to watch you two panic. And all I can imagine is just circles running around going, ah!
We refer to Fred as the windmill because he's got he's wingspan 6'5", 6'6". When those arms go, it's something to behold. And Tiffany's, she scurries underneath. Anyhow, I was just trying to depict that when, for tuning that etalon to that degree of accuracy, everything matters. Like your fellow said, you thought of everything. Unfortunately, physics doesn't care if you thought about it or not. It's going to do what it's going to do. And so when you change the temperature of that etalon, it goes up, it changes up into the red wing shift. And when you tilt it, it goes down in wing shift. And unfortunately, unless you're on a breadboard or floating in zero gravity, your telescope has a tiny little bit of flex and inconsistency and imperfection and collimation. I know you think it's an awesome focuser, but we've sent them to space. We've done them on every single other application will have a degree of slump. Each telescope is unique, and that degree, we're talking a fraction of a degree in movement of that focuser will cause the filter to go down in wavelength. So we tune them a little bit up, but we guess, we do an average. And so that means that every individual user has the privilege of turning the knob until he likes it the best, and then turning it the other way and saying, no, that's not the best. And usually they put them right back in the middle. But if they aren't right back in the middle, Tiffany gets a phone call because obviously there's something wrong with the filter. There's nothing wrong with the filter if your best view comes 2-3 ticks off of here. 2 or 3, 1/12,000th of the span of the coronavirus. So there's another factor involved, which is maybe you have a prominence that is leading on the side of the sun. Most folks don't realize that the sun is spinning so fast that the leading edge coming towards us is going to compress the wave and be blue wing shifted. The following edge going away from us is going to be red wing shifted. So the sun itself has a half an angstrom, which is the whole tuning range of the knob, half an angstrom different. Now, if you have a prominence over here, it's coming towards you, you may want to tune for that. Over on the other side, you may want to tune for that. There are reasons to give a little bit of tuning. We don't want to give you too much. Otherwise, maybe you have a school teacher throwing this on for the first time to her 3rd grade class, and she's, help, I can't find tuning. So the center tick is where it worked at the lab. Feel free to dial it around a little bit. This works based on temperature, so temperature takes a little time to move. You have to be patient. It won't be instant. What would be instant is if it wobbles. You would see that immediately.
Right.
So that's what the knob is for. And so that astronomers have a knob to turn in. Something to try.
I'm actually on full screen right now. The reason why I don't want to be on full screen for you guys is because of this constant flicking backwards and forwards, but they want to see the screen in the background in a close up. So start talking so it can flick back onto you.
We're going off live power here. Okay, so here's the screen. Yeah, right, the best juicy part, it went and cut off on us. Yeah, so I'm gonna give it a little tilt here. You see it just jump down and it dances back up. It can move a lot. All interference filters do this. Every single interference filter on the planet. This is just the way interference filters work. So you see it just dances all around. So it's just not possible to have that degree of control over every single owner's unique telescope and unique focuser. Some institutions, we have some very, a couple of big pro manufacturers that we know their focuser performance specifically, and they're one of these institution planetarium type of settings, and we know how their focusers behave and how they install them. So for those folks, we can customize it, but it's really rare that we would be able to do that. So breadboard, space, or a domestic focuser that will have a small degree of slump, and we compensate for that.
So can I use a zoom eyepiece on the Quark? And what about the Panoptics eyepieces?
Tiffany's rolling her eyes.
Yeah, of course she is.
Those are great eyepieces for other telescopes. Most of those great eyepieces that you spend a great deal of money on, they're great. They're great because they've worked, they've done a good job working with fast focal ratios. And we're not a fast focal ratio. We're talking f20, f30. How many telescopes are f20 or f30? Not a lot. That would, that'd stick out the front of the observatory dome. So slower eyepieces, 30 millimeter. What? Dell.
Uh-oh, what's happening now?
Do not wish Dell command update. No.
No.
Update the wires.
Yeah, no.
Bless their hearts.
Do we need to update Tiffany as well and Jen?
No. I'm a curmudgeon. I do not like an update. Where were we? Eyepieces. So we have really two issues going on. Slow focal ratios need longer focal length eyepieces. You need to have 30 millimeter. Here are our favorite eyepieces ever. This is them. This is mine. I like the 32 millimeter Televue Plaza. This is Tiffany and Fred's favorite eyepiece, the 40 millimeter TeleVue Plaza for quarks. Those are our favorite visuals. They like the 40 millimeter because they're usually in an outreach setting. And the 40 millimeter at a long focal ratio, you can have trouble with that exit pupil, the angle that it comes out at, and having to have the kid find the exact angle is a real problem. And that 40 behaves really well for that because it's a porthole. But bar none, the TeleVue 55 wins everybody's favorite if you can. But obviously, putting this on this, you would think you can't do that. We have an adapter for that. The other advantage of plausible eyepieces over other types is that they don't have very many elements to scatter the light. So this is a 2-inch adapter that you can take your 2-inch eyepiece and use this with our quark someday. So now you can use a 2-inch eyepiece with a quark by just changing out the interchangeable adapters. We have a lot of these. Can I show a few of them real quick?
Sure.
So here's our second most popular adapter. This is a quark to T adapter. And this quark to T, you see we've got our, a thread here. And you can just now thread it straight onto a camera. Maybe you've got a ZWO. And we make another couple of accessories that work with T-thread. One being, I just noticed we're getting close on time. This is an interference eliminator tilt mechanism. This will kill the interference patterns that can show up. I know if you've imaged in H alpha, you've gotten interference. Where's our interference pattern picture?
Right, so that's actually another question that a lot of people ask, is that the bandings of those images. And it's basically Newton rings. I know what they are.
Right, which is actually exciting because that's how you make an interference filter. You take monochrome light and you bounce it in between two parallel surfaces, and miraculously you get fringes. So this area over here with all these fringes, if it's showing up, we would extinct those with our interference eliminator, which comes in T-thread or C-mount. It's C-mount when it's so cute. But I wanted to focus a little bit of attention. Here's a little C-mount, isn't he adorable? The interference eliminator is significantly different than the construction and design of like the ZWO tilt. I think there's a German place that makes one. But we went to great lengths and expense to make this unique design that has this kind of potato chip behavior here. And this is built on the focal plane of the T-thread. So the distance back here to the focus plane means that you can tilt it up to 5 degrees. It's the only one that has that much tilt. You can take it 5 degrees and it'll stay in focus. Those other tilt mechanisms, they aren't designed for this purposes. Those are designed to help with like a crooked CCD chip. So this will kill those interference patterns by making the light not parallel. So that's a real popular accessory. We sell a lot of those for the imagers. And that would just go straight onto your ZWO. Tiffany's waving the ZWO. So another popular accessory is our focal reducer. The focal reducer, it's a non-spherically aberrated focal reducer. Say that 3 times fast. So what we have here, we have 2 achromat lenses custom fabricated. Everything we do, we custom design, custom prescribe, custom fabricate. And he's got a T-thread back here. And so he'll go, this is actually more popular with the larger apertures where folks have a 150 millimeter telescope. I don't know anybody with a 150 millimeter telescope. And you can actually change it from a 0.5 to a 0.33x just by adding spacing. And this is another good example of, if you look in here real close, you see all those ridges inside? Everything that we make in our accessories, we add this internal baffling as tightly as we can. Like the cork has 13 baffles inside. That acts to trap light that might be bouncing and scattering in there so that you can see it's not going to make it past there. I know it's shiny, trust me, doesn't matter. What matters is those knife edge baffles are going to trap that light in like a little, almost like sound dampening, which is also why we love the TeleVue eyepieces versus different brands. I'm doing a plug. Sorry, love TeleVue, because TeleView uses these baffles between their elements. They thread them. It's just higher contrast. Your blacks are blacker. You don't have a glowy background.
See, I never knew about that 2-inch adapter, and now that I know you have one, I might have to get one.
Simon needs a 2-inch adapter. Make a note, Tiffany.
Well, actually, hold on. Will that work on the Gemini, though?
Absolutely.
There you go.
Everything is interchangeable. That's one thing that we try to do. Everything is backwards compatible. You don't realize that this thread is the size that used to be used in the 70s on an old T scanner, is what Dell called it. It was a non-heated Daystar that he tuned by having it up in wavelength, and then you would tilt it down. Well, people were racking the knob really fast and they couldn't see it. And I was like, let's just heat it all. Electronics are cheap these days. And they are, especially when we make them here.
All right, so
here.
So this is going to be the last question before we go on to the internet questions, because there's quite a few and people are just furiously tapping away at them. Some of them we have covered, so you'll have to forgive me if I've ignored your question. I'm not doing it because I'm ignoring you guys. I'm doing it because we've actually already covered it, and you can wind the video back or play it back at another time. So the last most frequently asked question that we got part of this presentation, and I know we're over time, but luckily I scheduled a 30-minute break into this because I kind of had a feeling we would run over time because there was a lot to cover.
Right.
So I want to get a chromosphere quark, but I still want to see prominences. Can you turn the knob to see it?
Yeah, that's our most common decision question. The knob doesn't change the band pass between the chromosphere and the prominence. When we were looking at the screen, the band pass is how wide this is to let light in. And the knob only changes where the peak is in position. So the knob isn't going to affect that, but the most common misconception is that you can't see surface with a prom or prom with a surface. We sell 10-to-1 chromosphere versus prominence model because the chromosphere will still show prominences. Prominences are like tornadoes. When you see the tornado, he's moving across the horizon pretty slowly like this, 60 miles an hour. But in the tornado, there's Doppler shift going on that radar because those winds and rains and things are moving so fast. So the prominence is the tornado, and your view with a narrow bandpass won't see fast moving rain. It'll still see a tornado, but if the rain is moving too fast, the tornado will seem thinner. So the prominence model will catch all light that is being thrown quickly by movement in a direction towards you or away, because it's broader. It'll cast a broad net. The narrower filter will still see the prominence. It will just have, instead of like, say, a giant magic marker, you'll have like a Sharpie.
Marvelous. So we're now going to open it up onto the internet questions, and I'm just going to have to scroll back, so just forgive me for one moment, because there was quite a few.
I bet.
Pamela Shivak, or I hope I didn't say that name wrong. Pamela Shivak says hi.
Hi.
That's not really a
Yes,
question.
you guys.
I saw the question. Where is it gone? Okay. Is there a scope or a filter that covers both chromosphere and prominences? Duh.
Duh. Here it goes. This is Simon's favorite. This is our little guy. He's so happy. His name is Gemini, and he does a little dance. So in this filter, I was just thinking on the way home from NEAF last year, I was thinking they'd really love a filter wheel, but they just can't. That's too much money. So this one, we put 2 filters inside and just track between the 2 filters. We put a prominence. This one's glasses. Where's my glasses? This is chromosphere. This one's prominence. Yes, I'm wearing my glasses. I know.
Oh, let me load that up so they can see it. So sorry, one more time.
Prominence, chromosphere. So it switches in between each of them. And you have the 2 different knobs to tune each filter individually. Maybe there's a prominence and you want to tune for that one unique prominence, but then they keep the surface detail. So this little guy will do both at the same time. You just put him in your eyepiece, or put that in your draw tube, put your eyepiece in here, and then you have the choice of swapping back and forth. Some images really like this, but honestly, this kills it when we're doing outreach. because in outreach, you get to have both conversations at the same time without having the customer or the visitor goes twice through the line. You get more content with less time. It's just simpler. And sometimes doing outreach, you don't have all the features to show off. So you can use one tool. Oh, look, a prominence came up. And then so you have a choice.
I mean, I do imaging more than anything else. I mean, I don't do outreach as much as I used to when I first started, but to me, there is a big difference between the two, especially when I'm actually doing something specifically for the prominence. Again, that will be covered in my later talk. I know you guys who are watching earlier on, I was actually in prominence view, just so you guys know I was not in chromosphere view. And I will go through the differences of one versus the other. The next question, and this is actually really, really good, believe it or not. At some point, imaging quality between two views, either an f23 or an f31, if they are the same or if they are different. In other words, is one focal ratio better than another when it comes down to imaging?
What changes with your focal ratio? You have obviously two things that change. One, of course, obviously your brightness will go down and your focal ratio spreads out. You get a longer focal ratio, just like a camera. If you're at f11 or if you're at f2, f11 is going to take a longer exposure. So that's a small change in the performance because you just change your, how often you're taking that, snapping that. But because the reason we bring them down to parallel beam has to do with the wing shifting behavior of the light when it is an angle. So the more straight your light is coming to your filter, the narrower its performance will be. So if you're less than f30, you have a little bit of a light cone. So you're going to have a little bit of widening of your filter, not much. And we've also found out that the telecentricity, if let's say you're using a TeleView PowerMate 4X or 2X is our favorite, most truly telecentric light will be very parallel. And if you are in a truly telecentric, you probably won't even detect a difference. But the difference would show up in wider or narrower. You get slightly narrower. And we've picked f30 because over the decades we've learned there's diminishing returns after you get beyond f30. 30 is enough.
Right.
You don't have.
So next question, are plossels recommended, and is there any problems with using higher magnification other than the 25 or so?
What happens, remember, we've just tossed a 4.3x, and I don't know how much planetary work you do with a 5x in. You're pushing Dawes limit when you get that focal length and focal ratio that long. You're pushing what you can do with your glass. You're pushing what you can resolve. Fred made a chart here, but it's for imaging. So the point is you've reached Dawes limit, and all you're going to be doing is taking the same information, and it's basically take a low resolution picture. You can only blow it up so far. That's what you're doing when you go beyond a 25. We like the plossels the best for the lack of number of elements. The ERFLs, I don't even know if anybody makes them anymore.
Make who?
Those are ERFLs, E-R-F. I don't even remember. I'm sure someone will correct me, but it's a very, very, very old style of eyepiece. Yeah.
I don't remember hearing that one.
ERFL.
I'll have to look that up. I mean, I know Daniel Mounsey will probably know what that is in a heartbeat and pull one out of his ass from nowhere.
I think it has just one doublet or something in it. It's interesting. So.
You still have that printout from the ERF?
Yeah, the bad figure.
The crap one. Do you have a picture of a good one?
Not handy. I wasn't expecting that.
But yeah, somebody was asking what the difference is going to be because they want to see it.
We offer, all of ours are spec'd to a quarter wave through. And through means that both of the sides, because you send your laser in one side and out the second surface, and then you bounce it and it comes back. So through, it's 1/4 wave or better is what we would see. And sometimes you can micromanage, but okay, it sounds good.
This is from Kevin Legore.
Hi, Kevin.
What is the narrowest H alpha etalon you have ever produced?
If I say this, somebody's going to want to buy it.
But
And
that's
trust
all
me.
right. I'll sell it to them.
Am I allowed to plead confidentiality on this?
You're
We
the
have made
owner.
Very, very narrow. When you get narrower, they get darker, not just because they're excluding light, but because the overall transmission goes down. And things that are below, say, mid-0.2 angstroms, we do make mid-0.2 angstroms pretty regularly. We'll probably kick out 4 or 5 a year that are in the mid-0.2 range. But truly, we start getting difficulties with customers at that range because they're just dim. You just don't get a very bright. And then even if you're imaging, you can turn the exposure up. Now you've got signal to noise ratio, and you guys know what signal to noise ratio means. You need a brighter image to have that detail. You're making a blank look. Signal to noise ratio.
No, it's the question that I'm not quite sure what it means, but I'm going to read it to you anyway. It says, would there be any advantage or drawbacks by mixing a Gemini with a front mount single etalon?
Oh, the double stackers.
That's what he's referring to.
Know
okay.
the double
Now it makes sense.
stackers. We've had folks who decided to try and take this and mix it with this. There are very specific and proprietary reasons you shouldn't do that. You know, our other saying is the double stacking is for babies. When you take two, the concept is that when you take two transmission peaks and you overlap them, they will become narrower. That's the everything has law in physics. The trouble is if they're in any way off, they will actually widen. They have to be 1/12,000th of a width of the coronavirus. They have to line up that accurately or they will widen. So it's just make them narrower. It seems to me that it's a workaround for a limitation that the Daystar just doesn't have. We did, however, one reason people gripe that we don't let you take these apart. It has already happened, bless his heart, a gentleman called in, he bought a used combo quark, and somebody had taken the blocking filter out of the combo quark, sold it used, whether the guy passed away, who knows. So it seems harmless to just get in there and fool around, but that guy, we were fortunate we caught it before some damage could happen. So for the love of God, just don't open your filters. We will service them. It's covered.
You know what? I'm going to say this for any solar telescope. It doesn't matter whose you buy. It could be one versus the other. I have enough knowledge to dismantle most of these scopes and check them out and look for certain things that I'm looking for to fix them. And I'm not going to go into it because I don't want people doing it. It's just straight up, don't mess with this. At the end of the day, you are still looking at the sun. It doesn't matter what kind of ERF, energy rejection filter, blocking filter, cardboard, tinfoil hat that you've got on. Don't mess with this stuff. There is a reason why they make it in such a way that you can't mess with it. So please don't mess with it.
Let's imagine what had happened if he had been injured. If that man had been injured because the filter had been disassembled, then I could have been sued. If I'm sued, I go out of business and you guys can't buy Daystars anymore. And if I lose, my insurance company is now going to rate every single other company in the same way. And all those telescope companies are going to go out of business. And all it took was one guy deciding he could take out his blocking filter and it can take down the entire industry. You want to talk about a selfish act of doing one thing because you wanted to try it, forgetting about the other people. Congratulations, that's a real good way to kill the whole industry.
Yeah.
So,
on
an up note.
We had to get that out because that is actually one thing that has forever bothered me when people, every now and then, and I don't want to single anybody out, there'll be somebody that I come across, doesn't matter if it's in the store, outside of the store, outreach, whatever, and they're all optical engineers, and they always come up to me, and this is part of a question. They pull out their hydrogen alpha filter and say, why can't I just use this H alpha filter? It's still a H alpha filter. It should still block out that light. I'm an optical engineer, and I hear this non-stop. And I'm like, how much time do you have before I can bore you to death explaining this? Or do you want the short answer? What is your short answer? Because I've got my short answer. I want to hear yours.
We block off-band X-ray to 2 microns. What's the off-band blocking of that filter?
We don't know.
Yeah. We don't know. And I know for certain, if you can look through it and see a light bulb, then you shouldn't be looking through it on the sun.
Yeah, and that's the thing. I've always said this: if you can see through something, don't use it like that. That's not what it's for. You know, that's what a blocking filter is there for. There is all sorts of things that are put in there from a safety aspect. You know, respect the safety. But how much time we got left? We got about 15 minutes. So if you guys have any more questions.
Oh, wow. Does that mean we can talk about focus problems? Focus problems are a real big issue for a lot of customers.
Oh, I want to hear this. Come on, bring it on.
Yeah. Because Tiffany does a great deal of yeah, sorry. I needed those, yeah. She's straightening up. Our most common problems for focus with the quark. We're just going to go down the list and hopefully just knock these right out. Number one, give me a diagonal. Number one, the quark belongs behind the diagonal, period. I know that you don't like having this big teetering thing up here, but the problem is, if you've ever paid any attention, if you're an optical engineer, you know this, that the further ahead of the original object that you push a Barlow, you take the magnification of that Barlow and multiply it times how many inches. So if your telescope came to focus here, 1 inch, but you put the Barlow 4 inches ahead in the focus train, that means the new focus is 16 inches back. 16 inches of glass on the that you're going to have to deal with to focus that out. It's never going to work. And I don't know what, once a month, Tiffany gets somebody and 5, 6, 7 emails, phone calls. I can't get it to focus. Please send a picture. And there it is. They've put the quark in front of the diagonal. The second, maybe you have an imager who's trying to image and they don't want to use a diagonal. So if you're not going to use a diagonal, you have to replace that with like a spacer going straight through and then the quark. It has to go before the quark, not after the quark, because before the quark, it can be 4 inches long. After the quark, it has to be 16 inches long. So put the space before the quark, whether it's a spacer or a diagonal, that quark right back where you put the eyepiece. That's how it was designed and will work. Bad seeing will cause focus problems because you can't get a sharp edge in bad seeing. If you've got the 8-inch LX200 in your full aperture, you're not going to be able to get a sharp edge on the limb, period. High scuzz, if it's kind of milky up there and you hold your thumb up to the sun and you have a corona around the sun, bad seeing, high scuzz, you will not get a sharp edge. You'll just get another way you can tell that there's too much scuzz is the background isn't black. If your background isn't black at all, you're not going to be able to focus. We've seen really dirty optics or dust. Maybe you went to Texas Star Party. Now you've got scattering everywhere. If you've been to Texas, you know. We've even seen with calcium. Calcium is exceptionally hard to focus because telescopes are not designed for 393 nanometers. They're designed for 500 nanometers. And usually in that design, they completely abandon the UV range or the near UV range. So the optics can even be, and the anti-reflection can be bad down in calcium. So that falls into the category of, is your telescope a budget model, or did you spend a lot of money on your apo optics? And we've seen Newton's rings be a problem. We had a gentleman who drove to our facility from another state. He's a pilot. He's like, I'm just going to bring it out there, and you're going to show me how to focus this. And it turned out he was trying to image, and he had terrible Newton's rings, and he couldn't get a sharp edge on that edge. So And he knew he had the Newton's rings, but he tried the CWO and it didn't work. So he said, all right, let's put a regular interference eliminator on here. And he got that, and then we were able to achieve focus. Our number 2 problem for why people can't focus is coarse and fine focus. Zoom, zoom. When you put a 4x in there, you have got to move out to the little fine knob and go slowly, because the coarse focus will scream right past it so fast you won't even see it coming and going. And our number 1 focus issue is, drum roll, field stops. This has to do with the image size relative, the image of the sun, big fat sun coming through choked little field of view with your field stop. And if your sun is in any way out of focus, say, you're tight at 480 millimeters, but if you're out of focus, that image is yay. So now you're trying to focus when your field stop is here and the edge of the sun is out here because you're out of focus. If you focus, let's see, we've got some graphics. Where did Fred put it? We're missing one. Here it is. Ta-da! So that's a field stop. That's the limb of the sun. So you can see it would be exceptionally difficult to tell one from the other. How on earth do you tell one from the other? Well, the only way you can do that is to, while you're dialing slowly, you need to move around so that you can see one of these moves and changes with the sun's movement. So if it stays in the same place while the scope is moving around, that's your field stop. And then eventually you'll be able to, you'll still have the field stop that cuts off, but then you'll get that sharp limb. That's our number 1 problem with folks who claim this just never came to focus. And it's so frustrating for poor Tiffany, for those poor clients. They'll call over and over and over, and they'll send the filter in because they swear something's wrong. And we put it on the sun and it focuses just fine. Oh, well, it must be my telescope. Well, then we talk to the manufacturer, and great guys like Kevin McGore and John Betancourt, they've taken those corks out and put them on every model in there. So we know that the focus issue isn't the telescope, doesn't seem to be the cork. We're seeing there's a field stop frustration because the image is so big.
So moral of the story is, if it's not the idiot inside, it's the idiot outside.
Well, we don't like that term. It's a very frustrated astronomer. That's who it is. He's frustrated.
Have him talk to Tiffany then.
Thanks a lot, Simon. She is a delight, and anybody who's talked to her will know that she is an absolute sweetheart and would love to hear all about all of your difficulties as long as you want to talk to her. Isn't that right?
That's true, though.
It is. She does. She loves to chat. And we're in the Midwest, so that's technically okay. We went to New York, and I kind of started looking at her weird because she was asking people in the airport, "How was your day?" And they were really, really confused.
Yeah, it's like being in the UK sometimes. You should never ask anybody anything. It's like, just get away from me.
Yeah, no, we're not that way here. It's different out here. It's also helped us a lot to be able to be open, aside from the fact that technically when I'm closed, I'm open because I'm just a few feet away. And so if the UPS man comes, I'm shipping. We make everything here. I coat here, we make the electronics here, we do the machining here, we assemble, we have all the optics. The only thing that doesn't happen here is we don't anodize, and there are some optical polishings that we have to send out for.
But we can actually comfortably say this is it's all made in the US though.
Yeah, yeah.
And to me, this is a rare thing because there are very few people or companies out there that are US based or US manufactured, and you guys are one of the only ones, to be totally honest. 100% US.
Yeah, and some of these have been really difficult decisions, and some of them were just because our skill sets worked very well, and we're fortunate. Bless his heart, Fred. Fred he's the Wizard of Oz back there. He just, I don't know how it works, but if there's a new process, he just gets in there, needles, and what he already knows. He just bought a pick and place machine and put it in there, and it just works. He just designs things and I don't know. We rave about him. He's also kind of one of those, at the same time, he's kind of a broken toy.
Poor guy.
But,
Cat's
oh,
one.
hi there, Cat. Hi, Cat.
Oh, she's going to sit right there. Of course she is. That's
Yeah.
where the mouse is, the whole 9 yards. Everyone gets to see
Perfectly
my
fine.
cat as usual.
No, there's another really important reason the Daystar has never sent any of our technology out, and that has to do with our understanding of the way proprietary information works overseas. And what's allowed us to stay in business so long has to do with the, I'm not going to say that's distracting, but it's just adorable. Kitty. As if you send your process, any proprietary process out, I don't care what piece of paper you have to protect it, that company, as soon as you're done, can sell it right through the back door. And we're fortunate we can't be reverse engineered, and that's, I suppose, kept us safe. And it also worried me and our ownership that what if the standards of safety are in any way compromised?
Right.
You know, blocking from X-ray to 2 microns. I know it's blocked from X-ray to 2 microns if I made it. I don't know if it is if they made it. So having that control helps the customer stay safe and keeps the industry safe and protected from liability issues and safety issues. So I'm trying to do my part.
So this is my question, and this is the last question because I got to go for a break and go to the bathroom, obviously, at some point in time. The size of the blocking filter and the exit pupil, the aperture at the back of the quark, do you have any plans of making that bigger for larger sensor cameras? And I'm not going to be the only person to ask that question, by the way.
Right. So there's a couple of issues going on here. The quark is a budget piece, and a lot of people don't appreciate that there are more expensive filters on up. And when we start to get into we talked about maybe having a larger quark someday, and the difficulties in that come to do with exactly what telescope would we design it to fit. You know, now we're going to we have to redesign, and that means making stocking decisions, and we're not sure that the market will bear what that means and the costs that would be associated with a more expensive one. I also wanted to address the issue of the bigger chips. Wait, no. First, we need to talk about the focal reducer because we do, oh my goodness, we did this nice, pretty installation overseas, won't say where. We have done custom, very, very large aperture. I think the largest aperture I did on a quantum style was 76 millimeters. It was, you know, a monster. And that 76 millimeters, hi Clyde.
Hi, Jan.
Yeah.
Yeah,
So
Clyde's joined in the video.
The difficulty with those is, you know, then you have to take it down to the chip. And at that point, then you really need to think about matching your pixel size. So when you have your pixel size and you have your aperture, now you have to talk about your resolution matching your pixel size and binning. And honestly, a lot of those pixel sizes are so small that it would be better to use a focal reducer to get your resolution onto the smaller pixels rather than to expand your aperture up to have pixels that you're going to blow out. So most of these solutions are solved with a quality focal reducer that, again, we make ours that's non-spherically aberrated so that you don't have the edge effects and the vignetting and whatnot. So.
All right. On that note, we are definitely over time. And since Clyde is finally here, we're going to pretty much just roll straight through. I really got to go to the bathroom and I got my legs crossed the whole 9 yards.
I see Claude's got his airplane headset on. You been flying today, Clyde? Claude? Sorry, bad day.
Oh, he's muted. Let me unmute him. Unmute yourself, Claude.
Okay, I'm unmuted now. You can hear me now?
Oh, we can hear you.
Yeah, no, actually, I'm supposed to be working from home today, so I just got off a staff meeting from here at home just a little while ago. So I missed the beginning of your talk, Jen, but I caught most of it.
Did you catch the nice Windows updates we had to do real quick?
Yeah, hopefully, I have a Lenovo. Hopefully that's not going to hit me next.
All right, guys. Jen, thank you very much for doing this. I kind of wish we had more time because there's so much to talk about. And for those of you who don't know, that's Tiffany over there in the background. Now you finally know what she looks like.
All right. Have fun, Claude.
Hey,
Tell
take
Teresa
care.
I said hi.
She's in the other room.
All right. Bye-bye now.
All right. See you later. Okay. Oop, didn't want to do that. We're going to go full screen. So, Clyde, you're going to do a screen share. Is that correct?
Yeah, I have a PowerPoint. So should I jump into that?
Yeah. Do you want to initiate that? There we go.
Okay. Let's see. I'll just, I guess, get going. I'll give myself an introduction. My name's Claude Playmate. I'm the engineer and chief observer at the Big Bear Solar Observatory. For the telescope has been in operation now for a bit over a decade, and we've gotten rather used to referring to ourselves as the highest resolution solar telescope in existence. However, that has recently changed. Many of you may have seen the press releases from the National Solar Observatory's 4-meter telescope, the Daniel K. Inouye telescope out in Hawaii, that recently got first light. So unfortunately, I think we're going to have to reconcile ourselves to just referring to ourselves as the second highest resolution solar telescope in existence. So today I'll talk a bit about our telescope, what it is, what it does, and how it compares and its association with DKIST and some of the other solar telescopes around. I probably don't need to talk to this group much about solar astronomy, why we do solar astronomy. Of course, the sun is the only star we can see in detail. The sun is vitally important to all life here on Earth. It provides an ideal laboratory for understanding high energy physics. And in general, our telescope, we look at the solar surface out through the chromosphere. We're really not a solar interior observatory. We really don't do the corona. We'll talk more about that. But what we really strive to understand is the generation and the distribution of magnetic fields, and ultimately the goal would be to be able to predict and understand eruptive phenomena such as solar flares, coronal mass ejections that disrupt power and information transmission here on Earth. So where is Big Bear Lake? Now I hope you can see my cursor. I'm planning to use that like a pointer here on the screen. And down here, this is a map of Southern California. Down here is the LA basin. And up just sort of northeast of LA is the San Bernardino Mountains. If we zoom in a bit, here's the San Bernardino Mountains here's Big Bear Lake right in the middle. For those of you who buy bottled water, there's Arrowhead Lake over there. And if we zoom in a bit more to Big Bear, here's Big Bear Lake. And just in the center of the lake, coming out of the North Shore, you'll see this straight line. That's a 1,000-foot causeway with our telescope at the end of that causeway. So why on earth would you put a telescope out in a lake, other than it being quite scenic? Well, Caltech back in the 60s wanted a world-class observing site within a drivable distance of the campus. The Southern California mountains were already well known for good, stable astronomical scene, as demonstrated by Mount Wilson, Mount Palomar, Mount Laguna, things like that, all these fine observatories we have here in Southern California. Southern California also, of course, enjoys good weather statistics, although it's a little chilly up here in Big Bear today. I'm wearing my fleece. The astronomer Robert Layton had an idea that the lake water up would suppress the ground layer heating that causes thermals to rise up around your daytime telescopes. Anybody that has tried to observe during the day, you understand that necessarily we're observing during the day, the sun is beating down on the ground heats, you get thermals rising up around your telescope, that damages your observing, your astronomical scene. Well, Bob Layton's idea was the lake would hold down that ground heating and maintain the natural good astronomical scene throughout the day. And I popped up a few of our images just to demonstrate, yeah, it actually works. Okay, the image of the Earth there is not one of our data products. I put that in to compare that to the size of that sunspot there. Well, a site survey was conducted back in the 60s, and it was determined that Big Bear Lake turned out to be a fairly ideal observing site for a solar observatory. Professor Hal Zirin would develop the site and was named the director of the Big Bear Observatory. The first light, or the first generation of telescopes for the observatory were two 10-inch telescopes. Well, this was long before my time here, but I found a couple of pictures. The two 10-inch telescopes were mounted in this common spar with the light coming out the back end to the image plane behind here, where you see these two 16mm film cameras. And ahead of the film cameras, I do recognize these two LEO filters. These are Halley filters built back in the day. We still have these things around. I've seen them before. So inside the tube were these two 10-inch telescopes. Then mounted on top was obviously a third telescope. I believe I've heard that this was called the Singer telescope. I'm really not sure. So long before my time at the observatory, I can't tell you too much more about it. And here's a image of a plaque that used to be out apparently on the outside of the building that shows our relationship back then, at least, to Caltech, Mount Wilson, and Palomar observatories, and with a little sign that says, the purpose of the observatory is to study the sun. It is located in the lake to reduce the image distortion by heat rising off the ground. Please do not disturb the observer. I wish I knew what happened to that sign. Well, the second generation telescope, in around 1972, there was a telescope built for Skylab 2. Remember, Skylab was our first US space station. It flew, it had a UV solar telescope, did wonderful solar astrophysical work. And a 26-inch reflector was designed for the follow-on Skylab 2. Of course, Skylab 2 never actually flew, which meant there was this orphan telescope. Somehow Hal Zirin got his hooks into that telescope and convinced NASA to send it to Big Bear for testing. Well, that telescope was mounted on the same mount that the original twin 10-inch telescopes were mounted, and it had to be mounted inside a large vacuum tank on top of that poor little mount. And my God, just look how overloaded that poor mountain looks. But that was a superb telescope for them. There was a workhorse telescope that went from 1972 through 2007. After it was decommissioned and removed from the observatory, it was then donated to the LA Astronomical Society. And a couple of years ago, I had an opportunity to visit down at Griffith Park Griffith Park Observatory, and they pulled out the telescope to allow me to see it. So here it is in its current configuration. They have it on an altazimuth mounting. They were taking it out for solar for public observing there at Griffith, but I believe their plan is to eventually relocate it to their dark site. Okay, finally, Zirin decided to retire in 1997. At the time, of course, Caltech was heavily invested in their nighttime astronomy programs, developing the 10-meter Keck telescopes over in Hawaii. So they took that as an opportunity to divest of their solar assets, which included not only Big Bear Solar Observatory, but the Owens Valley Radio Solar Array in Eastern California. A request for proposal was issued by Caltech for operation of BBSO. And of all places, New Jersey Institute of Technology wrote the successful proposal. Well, that seems like an odd mix, but several of the faculty at the New Jersey Institute of Technology's Center for Solar Terrestrial Research had done their postdocs, or excuse me, their doctoral research at Caltech, and were quite familiar with BBSO and understood its potential. So the astronomer who headed that up, Dr. Phil Goody, was the PI on that proposal, which was the winning proposal, and was named as the first NJIT director at Big Bear. Okay, so here's our alphabet soup for, we are, of course, the Big Bear Solar Observatory. We are a field site of the Center for Solar Terrestrial Research at New Jersey's Institute of Technology. So Phil became director 1997, right towards the end of the 20th century. And about that time, there were many future plans in solar astronomy. For one, the Japanese were developing and had plans for a half-meter solar space telescope called Hinode, as well as the National Solar Observatory, my previous employer, was making plans to develop a 4-meter solar telescope, which just finally, 2 decades later, has seen first light out in Hawaii. So Phil's problem at that time is with just a 26-inch, 0.65 meter solar telescope, how could Big Bear continue to be relevant and compete in the 21st century? Well, he knew he had to think big, but how big did he need to go? Well, as we all know, in telescopes, size matters. Bigger is always better. The more collecting surface, of course, allows you to see fainter sources, fainter objects. That's a bit secondary when you're looking at the sun, but larger aperture also increases your resolving power. And I hope most of you are familiar with this equation. The resolving power in radians equals 1.22 times the wavelength divided by the aperture of the telescope. So if you hold wavelength at just one, stably at one wavelength, say the middle of the visible, I plot here the resolving power of a telescope versus the aperture. And not surprisingly, as you go to larger and larger aperture, you can resolve finer and finer detail. Your resolving limit is a smaller angle on the sky. And already here at an 1/8 of a meter telescope, that's 5 inches, you're already able to resolve an arc second. That's pretty good. Go up to a 10-inch 1/4 meter telescope, you're down at a half arc second. And here with Hinode at 0.5 meters, down at 1/4 of an arcsecond resolution. Go to a meter, and of course you're down in 1/8 of an arcsecond. That sounds great until you realize we sit below an ocean of atmosphere. The turbulence in the Earth's atmosphere limits the effective resolving power here at the Earth's surface. And even at the best sites on the Earth, your resolution is limited to about 1/2 an arcsecond, give or take. Of course, there are instances where that can be beaten a bit by lucky imaging or back speckle interferometry, a few things like that, but still it's a reasonable rule of thumb. So you could say that as you increase your telescopic resolution, you hit this floor here at 1/2 arcsecond, and beyond that point, well, you might say anything above about 1/4 meter telescope, a 10-inch telescope, is just wasted aperture. So it's not coincidental that the first generation telescopes at Big Bear were 10-inch refractors. To beat that limit, of course, you can lift your telescope into space. Space has effectively perfect seeing, but space is exceedingly expensive. The rule of thumb I've heard is about 3 orders of magnitude. So say you have a $1 million telescope, you want to loft that into space, add 3 zeros, your $1 million telescope becomes a $1 billion telescope. Well, we just don't have that kind of money in solar astronomy. What can you do? And here is a bit of a cartoon showing what we're talking about. You have some astronomical objects sending out wavefronts that are effectively perfectly flat wavefronts. Here you have your telescope above the atmosphere. It's able to take that flat wavefront in and make a perfect diffraction limited image. However, here we are for us on the Earth's surface. The wavefront passes through that last 100 kilometers for us after 150 million kilometers moving through space. The last 100 kilometers, that wavefront gets distorted and we have a fuzzy image. What to do? Well, the answer comes in the form of adaptive optics. Adaptive optics was first conceived of back in the 1950s by a couple of astronomers at Mount Wilson here in Southern California. But try as they might, it was impractical to develop before the advent of high-speed digital computers. The concept, however, was not totally forgotten. And in the late 70s and 80s, the Department of Defense began developing the concept in secret. Then in the late 80s, they at least partially declassified the concept. And of course, adaptive optics is a talk in itself, but in a nutshell, the idea is here over on the left, you have your perfect wavefront coming in. It passes through the atmosphere, again, in that last 100 kilometers of travel, and it comes out in some randomly distorted shape. Of course, keep in mind, it is a random distortion and it changes moment by moment. Neglected in this cartoon is in here somewhere you'll have a telescope, but we can ignore that fact. That distorted wavefront is then reflected off of a deformable mirror that under computer control with actuators can take on just the proper shape to cancel out that wavefront distortion, re-achieving a flat wavefront. That flat wavefront is then sent on down to your science camera, where it's able to image to, if the adaptive optics system is properly designed and running, down to the diffraction limit of the telescope. Well, there will be some residual wavefront distortion even on that corrected image. That then is some piece of that wavefront is picked off by a beam splitter or dichroic mirror, something like that. It goes off to a wavefront sensor that determines what that wavefront, the residual wavefront error at that moment is. A computer then takes that information, decides how much voltage needs to be delivered back to each actuator of that deformable mirror to take out the residual distortion. It makes that correction before the sky has a chance to change, and around in that servo loop it goes. The difficulty is those corrections must be computed and applied faster than the sky has a chance to change. And how fast is that? Well, it depends on your site, your telescope, the winds, etc. But a rule of thumb is maybe around at least 1,000 times per second. Here at Big Bear, our wavefront sensor corrects at just shy of 2,000 times per second. So yes, an adaptive optics system can correct to the diffraction limit of a telescope, quote unquote, as good as in space, but the caveat is over a very narrow field of view. And I can describe that very simply as, think about the fact we are sensing and correcting this flat wavefront, how it is distorted here. But imagine off on the side of your field, you're looking off this direction, going through a different part of the atmosphere that gives a different distortion. So the correction you apply will only apply to this particular direction and will apply less and less as you move away from there. Here's an image of the actual deformable mirror we use at Big Bear. It is a small, only 100 millimeter circular mirror. We put a pupil image of the telescope focused on that, though I guess doesn't help to point with my pen, onto the front of this. And it's a very thin piece of glass, only about 1 millimeter thickness, which is mounted on 357 actuators. Out the bottom of the optic, you can see this this umbilical of all those wires. Those are all connected to separate actuators for the deformable mirror. And how well does it work? Well, I hope you're able to see this on your side as a reasonable, it's not too choppy of a video. Here's a reasonably bad seeing day. This is 40 arc seconds across of the natural scene on, as I said, a fairly poor seeing day. Switch on adaptive optics, and this is what you get. Okay, a dramatic improvement. You can see granulation, the intergranular region. You can even see magnetic bright points between the convection cells, but we're not done yet. Each of these images we show is actually a stack of 100 frames taken extremely quickly. In post-processing, we can apply a method called speckle reconstruction, which pulls out the finest detail at every pixel across that. Now, I better be hearing lots of oohs and ahs out there across the internet at the moment. For me, this is a incredible movie done here. And you can see dramatic detail in here all the way to the edge, down at the resolving limit of our telescope. Those small bright points between the intergranular region, you're approaching 1/10 of an arc second there. So this really is diffraction limited across there. I'm not going to say much about speckle reconstruction, but it is think of it a bit like lucky imaging, where you're picking out the best detail through a stack of images, but instead of picking the best image, you're picking the best pixel through all that and reconstructing the image that way. It's not a very good description, but kind of gives you an idea.
Sorry, Clyde, I don't mean to interrupt there, but I know what's going to happen next. They're going to ask, can you get that software to do the despeckling?
The software we use is proprietary. It was written by the Kiepenheuer Institute for Astrophysics or Solar Astrophysics in Germany. But I think there are some algorithms out there somewhere. If you could figure it out, you could probably do it, but no, it's not a commercial product that is made available.
Yeah, because I mean, obviously, deconvolution in this particular case is not going to help. I mean, I got to admit, that's the first time I've ever seen that, and I can see it now. People, there's a couple of comments already popping up because there's a slight delay on the stream, but I know people are literally just freaking out over seeing that right now. I've never seen that before.
Yeah, well, I would suggest doing some looking. Google the speckled reconstruction, and it is inside solar astronomy. It is a fairly common, although fairly recent technique, and it's certainly not just us that use it. The Germans use it, and I know that they are using it heavily at DKIST now as well. Okay, so the question was, back to Phil's conundrum of how big is big enough? Well, any next generation telescope would have to fit within the confines of the existing facility. It would be completely impractical to build a new larger building. The cost would be prohibitive, plus just the permitting here in California would be probably impossible to get through. So any new telescope would have to fit both within the space and weight limits of the existing structure. Also, remember, the sun is not a solid object. The sun is gaseous. And so the surface, although it appears sharp to us from 150 million kilometers away, it is actually rather somewhat diffuse. The photosphere is a few hundred kilometers thick, so there is going to be a limit to how fine the finest detail on the solar surface is. There are some suggestions that that is some tens of kilometers across, so call it 50 kilometers. In the visible, that'd be about 0.07 arc seconds, which already dictates at least a 1.5 meter telescope would be required to hit that limit in the visible. Well, back when Phil was first proposing this telescope, there already was a 1.5 meter solar telescope. This is an image of the McMath Pierce Solar Telescope out at Kip Peak. I'm well familiar with that facility. I was with that telescope for 26 years before becoming a turncoat and coming to Big Bear back in 2011. So if there's already a 1.5 meter telescope, I'm sure there was some wish to, why not just make it the world's largest and push it just above 1.5 meters. And lastly, at the time, Big Bear, or the National Solar Observatory, was in the beginning process of designing the 4 meter Daniel K. Inouye, what is now the Daniel K. Inouye telescope, out in Hawaii. Big Bear was intended to be a quick up, fairly low cost Pathfinder technology demonstrator for the 4 meter telescope. And a good chunk of the development money actually came from the government for that purpose. Now, the primary mirror. The University of Arizona in Tucson is in the process of developing, I'm sure you've all heard of the Giant Magellan Telescope, one of this next generation giant telescopes, to being built down in Chile. The GMT is going to use 7 8.4 meter telescopes, or 8.4 meter mirrors. And remember, when you do a composite mirror like that, it has to, those 7 mirrors have to work together as if they were a single parabolic mirror. So they have to be the proper shape, they have to be in phase, etc. So around there is one mirror in the center that is symmetric, that's a standard parabola, but all these mirrors, in the 6 mirrors in the flower petal arrangement around the outside are segments of a parabola, an off-axis segment. You can't just take a parabola and tip it on its side. You have to actually grind that mirror as if it was a part of a larger parabola, with these optical axis over here and that shape going off over there. So before they could tackle the 8.4 meter mirrors, they needed to demonstrate that they could actually produce such an off-axis parabola. So Big Bear made a deal with the University of Arizona to share costs. The University of Arizona, the U of A, got to develop the processes for figuring and testing such an off-axis mirror, and Big Bear got the mirror. So our BBSO 1.6 meter parabola is a 1/5 scale model of a GMT mirror. Now, again, back to that primary mirror. The primary mirror is a daughter segment of a 5.3 meter parabola. So think of a 5.3 meter, 17.4 foot parent parabola with a 1.6 meter section cookie cuttered out of it. That's not the way it was produced, but conceptually that's what it is. And it's made of ultra low expansion Zerder by Schott. That's one of these very low expansion ceramic materials. And that is used such that, and of course, for a solar telescope, there's going to be some absorption and heating into the substrate. So we don't want the telescope mirror to, when it heats, to change its shape. So we want it dimensionally stable. And we're using an off-axis optical system to avoid any obstruction in the optical path. So it's a fully unobstructed beam. The beam comes in, reflects off the primary, comes to a primary focus over here off to the side before hitting our off-axis secondary mirror and sending the beam on down to our Coudet lab. Diffraction, well, for a stellar telescope, it's not that bad. You already know what a star looks like. It looks like a dot. Who cares if it's got little diffraction spikes on it? You can still find the centroid of that. It still has a lot of light. But on an extended object like the sun, every resolution element in that image is going to have diffraction spikes. So what you'll find is it will make a diffuse halo or diffuse glow, which will decrease the contrast of your object. While the sun is a very bright object, it's a surprisingly low contrast object. So that is paramount that that be maintained. Also, it's an all reflective system, which allows us to observe both in the visible and the infrared wavelengths, where most transmissive optics become opaque into the infrared. Now, we use a Gregorian optical system. And to a lot of you astronomers out there, you're probably going to find that surprising, since Gregorians have a reputation of being optically inferior to Cassegrains and like Ritchie-Chrétiens. Well, on a Ritchie-Chrétien or a Cassegrain, you have a convex secondary mirror ahead of your primary image, which then sends the beam back through a casshole to your image plane behind the mirror. For solar work, we want to have access to that primary image. So we use a Gregorian. And a Gregorian, what you have is a parabolic primary that forms a primary image. Beyond that image, there is an elliptical concave secondary, which then sends the beam on down. That gives you access to a real image of your image plane here. Here's another optical diagram showing our optical system. And here we have access to that primary image. Now, the reason for we want access to that is think about the fact that I heard Jen talking about people worried about a 150 millimeter telescope needing an energy rejection filter, and then her talking about somebody was running a 16-inch telescope without an energy rejection filter. We're running a 63-inch telescope without an energy rejection filter. Now, 1.6 meter, 63-inch, that equates to 2.01 square meters of collecting surface. Now, a lot of you may have heard of the solar constant. The sun, fortunately, we orbit a very stable star. Even between solar maximum, solar minimum, the output of the sun only varies by maybe 0.1%. So the sun is constantly beating down on the Earth with about 1.36 kilowatts per square meter of energy. That's above the atmosphere. Coming through the atmosphere, there'll be losses, reflection, scatter, etc. But I figure somewhere in the ballpark of a kilowatt per square meter is still striking the Earth's surface. That means that our telescope is collecting up 2 kilowatts of power and concentrating that down into a focus 36 millimeters across. That's enough heat, energy, that it will melt metal. How do we handle that? Well, at our primary focus, ahead of our number 2 mirror, our secondary mirror, we have a highly reflective aluminum surface. It's about an inch thick. It's hollowed out inside, polished on the front surface, and through which we constantly circulate water coolant, water glycol coolant, to keep it from melting down. And you might see right in the middle of that reflecting surface, there's a small aperture, which is 3 arc minutes across. That's about 1/10 of the solar diameter. So 1/10 the solar diameter reduces the energy load by 100. So I figure through that aperture, we're still passing only about 20 watts of power onto our secondary mirror and on down to our science cameras. Keep in mind that that aperture is only reducing the field of view of our telescope. It's a field stop, not an aperture stop. So it still has the full resolving power, full brightness, etc., that the telescope has to offer, just at a reduced field. And over on the left here is an image. We have a webcam. Since we are extremely concerned about maintaining control of where our telescope is pointing at all times, if the sun is to ever get off of that aperture, it would do damage to other parts of the telescope depending on where it hit. So we have a webcam that is constantly looking through a cheap solar filter that I bought at one of the companies online. I think it's one of the Mylar ones I put on the front of a webcam just to look at that heat stop. So here we are. This is our primary focus for the telescope. This is the heat stop around it. And you can see that 3 arc minute field that we're looking at through there. Now, again, it is paramount that we keep control of the telescope and know where the sun is striking at any time. Around the periphery of that heat stop, we have an array of temperature sensors. If any of them ever see anything awry, any strange readings, it will open up a solenoid here that will allow this spring to pull up a stainless steel cover to help protect the surface for some time, at least enough time to figure out, get things under control, close the mirror cover, what have you. Now, there was an incident I always like to point out before I came to work at the observatory in the early period of developing the telescope, where that actually happened. There was a cloud that came through the beam. The telescope got confused, the drive went off, but the mirror cover did not close. The stainless steel plate, which we sometimes refer to as the slammer, came into the beam, the clouds passed by, and here is a 36 millimeter infrared image imparted onto stainless steel. I'm told that was exposed to the beam for about probably 30 seconds before it burned through the stainless steel. We keep this around to remind ourselves of what we're really dealing with. Since then, of course, we've replaced the stainless steel plate, and we have not repeated that incident. We have many more safeties in place now. So, first of all, to shoehorn the new 1.6 meter into the existing facility, that original classic hemispherical telescope dome was replaced by a 5/8 34-foot 5/8 sphere, which is actually a modified radar dome. So it is lightweight, made out of fiberglass, that kind of thing. It's not metal, and it rotates and has an iris that can raise and lower to track the sun. The mount itself was designed and manufactured by DFM Engineering up in Longmont, Colorado. It's a modification of their standard 50-inch telescope mount. Here's a engineering drawing, and well, you can see it sort of looks like a standard telescope mount. Below the telescope, we have two coude labs for instrumentation. One floor below is dedicated to our mid-infrared instrument. 2 floors below is our adaptive optics and our near-infrared and visible instrumentation. We do have flexure in our telescope through the day, and being that this is an off-axis system, the orientation, not just the collimation and focus, but also the relative rotation of our mirrors are critical. So to take out aberrations due to flexure through the day, our secondary mirror, which is a off-axis elliptical mirror, is mounted on a hexapod. These are 4 rods that can translate, giving us 6 degrees of freedom. That would be rotation, tip, tilt, X, Y, and Z location to take out the different possible aberrations that we see through the day. Our mirror cell. Well, again, we have a thin, it's only 100 millimeters thick, 1.6 meter mirror. In reality, it's a 1.7 meter physical mirror, but it is so far off axis, 1.7 meters would produce an elliptical pupil image. So we stop that down to a circular 1.6 clear aperture. That is mounted in a 36-point passive flotation cell. You see each of these blocks on the back of the mirror cell. Each of those is a 5-pound weight that is mounted on a 10x force multiplying lever system. And the weights are adjusted up and back on the lever to just support the mirror, what we call floating the mirror. Now, imagine when you're looking at the zenith, of course, that works just fine, and you could figure out the amount of force you need to support the mirror. But as you go to different points on the sky, the amount of force you need to support the mirror is going to change. The nice thing about this design, which goes all the way back to Mel Wilson again, the same change in gravitational vector that applies to the primary mirror also applies to those levers. So it automatically compensates as you track to different points on the celestial sphere. The mirror cell was designed for active optics. Each one of these little mounting holes on the back of the mirror cell were meant to hold electric actuators that would back up the lever system to fine tune that. It was found, however, that once the telescope was put into operation, that it just wasn't necessary. So it was never put into operation. And as an engineer, you can well appreciate that if you have a working system, the last thing you want to do is tack 36 servos on the back of it. And our declination system is a little bit different than most stellar telescopes. Now, since we are dedicated to looking only at the sun, we have a limited declination range that we're going to look at. The sun only goes between 0 to plus and minus 23.5 degrees across the the seasons. So we don't need to be able to point anywhere arbitrarily, just over that range. So our declination drive system is a simple screw jack. Over here, we have a screw that just moves the telescope up and down through that range, and that is found to be adequate. Now, remember I said that there were severe space and weight constraints inside this facility. To accommodate this off-axis optical system, here's our primary mirror, comes off to the side here where our heat stop is here, the secondary mirror here. You can see my cursor, right? Okay, good. So our actual optical axis is way over here at the edge of the telescope. Now there's a third mirror here, which sends the beam through our declination bearing here off to a fourth mirror that then sends it down through the equatorial axle here, then on down to the Coude lap. So our declination, one of the modifications to this mount from a standard telescope mirror is normally you would have long forks coming up to the center of mass of the telescope. Up here, you would have the declination bearing up here, right at the center of mass of the telescope. Well, for this optical system, the declination bearing has to be way down here at the side of the telescope. So the bearing is here, center of mass is up here. You would think that, okay, well, you would need some big counterweight way down here to balance that. Well, first, there's not room in the dome for that. And secondarily, we're already pushing the limits of the telescope pier in weight. So that was a non-starter. So the DFM came up with an interesting idea. Instead of counterweighting the telescope, it is constantly off balance. And it is supported on each side by two screw jacks that compress against a spring inside a cylinder here. We know how much force is needed to be applied to support the telescope. And so we know how much that spring has to be compressed. The computer takes care of that. And so we are constantly riding on a spring suspension instead of having a balanced telescope. In the longitudinal axis, front to back on the telescope is balanced. We have two 600-pound counterweights that ride up and down actively as the telescope changes in declination inside these two tubes. And here is just an artist cutaway, illustration cutaway of the telescope to again give the idea of how the structure works. Our optical axis over here at the side of the telescope, the polar axle here, the beam then sent down to the infrared and visible near IR Coude labs down below. I'll also take an opportunity to point out this small dome we have just to the north of the telescope along the causeway. That houses a 100 millimeter, it's a 1.5 meter focal length, full disk H-alpha telescope. Now I'd love to tell Jen that we use a Daystar filter. Unfortunately, it's not. It's an old Zeiss filter. It's a Leo filter from the 1960s, quarter angstrom. Incredible filter, but we use that mostly as a context imager, looking on the disk. If there's some eruptive phenomena on the solar disk, we can use that for pointing information to get to quickly. Okay, the telescope, that 26-inch space telescope that was the workhorse telescope for the BBSO, was in operation from 1972, removed in 2007. So that's a 35-year run. It had a good run. Now down at with the LA Astronomical. First light for the 1.6 meter new solar telescope was May 2008. We first science, I think, was several months later in 2009. I came to the telescope in 2011. In 2013, our first NJIT director, Phil Goody, retired. And so our current director, Dr. Wenda Chow, we decided to have a ceremony and rededicate the telescope with to Phil. So the telescope in July 2017 was rededicated as the Goody Solar Telescope. So now the GST. And here is a image of the plaque that's now affixed to the side of the telescope pier. All day long, you've talked about the different atmospheres of the sun, so I think I'll blow through these slides pretty darn quickly. The outer atmospheres of the sun, of course, you come to the photosphere first, 400 kilometers thick. It shows sunspots, granulation, etc., about 5,500 Celsius. After that, the chromosphere, which is often characteristically looked at often in H alpha at 5563 angstroms, using special filters like the superb filters that Jen over at Daystar produces. And I actually do think they're superb filters. We have a couple of those running around the house here. Chromosphere, a couple thousand kilometers thick, characteristically. At the base, going from about 6,000 degrees up to 20,000 Celsius. And there you can see flare phenomena, plage, filaments, prominences, which are all magnetic features. Here's a couple of, I should point out that filaments are these dark structures on the surface of the sun. When viewed instead of against the bright surface of the sun and viewed against the dark sky behind them, appear as prominences at the limb. And here's a couple of images I stole from the well-known imager Randy Shivik. I hope if he's watching, he doesn't mind me stealing his images off the net. And the outer atmosphere is the corona. The corona is extremely tenuous and faint, extending arbitrarily far out from the sun, only visible during eclipses or using very specialized telescopes known as coronagraphs, which need to be above a predominance of the atmosphere and actually best done from space. Characteristic of the corona is its extremely high temperature, and shown in the corona are, well, magnetic loops, coronal mass ejections, streamers, things like that. Unfortunately, Big Bear is not a coronal site. We are just too low. We are only at about 2,000 meters, 6,750 feet here. We have just too much atmosphere above our site to be a viable coronal site. It is expected DKIST should be. Now here is an early image, which I kind of call the proof of the pudding image for Big Bear. This is a comparison of a simultaneous image taken between BBSO's, now GST, and that half-meter Hinode Space Telescope, taken August 2010. Now, this is not a simulation, blurred or anything. These are actual images from both telescopes. And you can see the comparison that, yes, we are certainly beating a half-meter telescope, even though it's a space-based telescope, and achieving diffraction limited images here on the Earth's surface. So for the time at least, it was outperformed any space or earthbound telescope and able to achieve the true diffraction limit of the telescope. And up in the upper right, just for a comparison, I put in an outline of the continental US. Now, fast forward a decade to the Daniel K. Inouye's first light image announced on December 12th, compared to that same early BBSO image. And yes, if you look at it carefully, they are beating our resolving power. Down here in these bright points, which are magnetic features in the intergranular region, you can see there is more detail down in there than we are showing. So yes, 40 meters is working, and they are getting slightly better resolving power, it appears, than we are. However, they're also using newer generation speckle reconstruction code than we are, and hitting it a little hard. So it would be interesting to go back and revisit some of our earlier work here. Now, for a side-by-side comparison between the Goody Solar Telescope and the Daniel K. Inouye, which again, I'd like to point out that this was built as a quick-up pathfinder demonstrator for the 4-meter telescope. So in a lot of ways, they are very similar systems. How am I doing on time? Oh my goodness, I'm running out of time. I better pick it up here. The Goody telescope is a 1.6 meter, of course, DKIST 4 meters. We have an equatorial telescope, equatorial mount. Theirs is alt-azimuth. And then we come down to resolving power. Our diffraction limit in the middle of the visible is about 57 kilometers on the solar surface. They're down at 23 kilometers. Out of 1.5 meters, 1.5 microns in the infrared, we're down to about 170 kilometers, where they're still at 68 kilometers. Now, I think this shows an interesting comparison, and obvious future collaborations is, while they could observe this astronomically interesting line at about 1.5 microns, they would have the same resolving power as we could achieve in the visible. So taking simultaneous observations, I think that shows some obvious collaborations there. First light for us, 2008. First light for DKIST, December 2019, about 10 years later. Our heat stop has a 3 arc minute aperture and reflects 2 kilowatts of power. They pass 5 arc minutes, so a larger field of view, but with that larger aperture telescope, their heat stop has to absorb more than about 12 kilowatts of power. That's a frightening number there. Our Coudet lab is fixed, which means we have a field rotation at our image plane, which we take out with software, 15 degrees per hour. Being an alt-azimuth, they have a variable rate image rotation, which they take out by rotating the entire Coudet lab on kind of a merry-go-round type of arrangement. We have a suite of visible IR imaging, spectral and spectral polarimetry instruments, along with multi-conjugate adaptive optics. Their first generation instruments will be heavily based on our instrument suite. Our altitude is about 2,000 meters. They're about 3,000 meters, thus making them hopefully a viable coronal site. The BBSO GST was developed over 5 years for about $25 million. DKIST took 20 years to develop, with the best official number I could find was $344 million. Operations budget, we're about $1 million per year. They're going to be about $18 million per year. Now, I mentioned multi-conjugate adaptive optics. Multi-conjugate adaptive optics is the next step in adaptive optics. Solar MCAO was been a joint project between BBSO and the National Solar Observatory because it will be needed for DKIST. The first test bench was developed here at BBSO, and over on the right here is a panorama of our CUDE lab. Most of our VIS-IR instrumentation is on the benches below. The benches above are all dedicated to MCAO. Now, what is MCAO? Well, instead of having a single deformable mirror, it uses multiple deformable mirrors that correct for different atmospheric layers. In the case here, 3 different deformable mirrors correcting for 3 different layers on the atmosphere. And what that does, it doesn't improve the image correction, but it allows a broader correction across the field. Now, here's an image of what is already now being called classic adaptive optics. So already jumped to MCAO. Stand by one moment. I hope it's not terrible if I go over time here. Jen did. Here you see classic adaptive optics, where the correction angle is maybe 15 arc seconds at most, 10 arc seconds, depending on the scene. Then go to the multiple adaptive DMs, the MCAO. You can see that's opened up to about maybe 50 arc seconds. So a dynamic difference. It will be very nice for us here at the BBSO, but with the large aperture of DKIST, it will be absolutely essential. Moving along, other notable solar. Yeah,
real quick, don't feel compelled to be rushed because the next person that speaks is me, and we can delay me for as long as we need to because this is far more interesting.
Well, I appreciate that. I hate when I run over. I try to keep the time, but
it's okay. You can run over all you want.
Okay, thank you. I appreciate that. Okay, then I'll take a sip of water here. Other notable solar telescopes include Gregor, another telescope we collaborate with quite a bit. Gregor is a 1.5 meter on-axis Gregorian solar telescope. It is a Gregorian for the same reason we are, but they decided to go with the simplicity of designing an on-axis system instead of an off-axis system, which probably makes for a much more rigid, they probably don't have nearly the flexure we do, but they do have diffraction due to all the spider structures in the beam. The telescope resides in the Canary Islands on the island of Tenerife at an altitude of about 2,400 meters, so a little higher than we are. It also has a high order adaptive optics system using 256 actuators, so very comparable to our 357 deformable mirror here. It's developed by, oh boy, I always obliterate this pronunciation, the Kiepenheuer Institute for Sonnenphysik, the German astrophysical group, which normally we just use the acronym KISS for them because it's a lot easier to pronounce. They had first light in 2012, but they originally started with a silicon carbide secondary mirror. They wanted silicon carbide because it is extremely light and rigid and has very good thermal characteristics. But apparently there were a lot of problems, I think, with the surface roughness. They just were unable to get it to perform well. That was changed out in 2018 with a Zurider secondary mirror, same material we use here. And since then, they've been getting rather good performance out of it, and I think is finally performing to its design spec. Although being very close in aperture to us due to the diffraction, it probably will never quite meet the image quality we get here at Big Bear. And here is a close-up of the secondary mirror. and ahead of that, their heat stop. So unlike us with the heat stop off to the side, they rely on the beam coming in around the side of their heat stop, having say just a small like Cassegrain obstruction in the middle of their beam. And then the Chinese Large Solar Telescope. Now, for many years, the Chinese have been talking a bit about developing and building a 1.8 meter solar telescope. Very little information has been released about it. Very little is known about it. They've been very tight-lipped about it. However, I was recently shown a picture, which I don't know if that person was supposed to actually have. I'm not sure if I should have done a screen snap of that, so I'm not sure I'm supposed to have a picture of it, but I didn't feel comfortable showing a picture of it. So instead I had Teresa, my wife, do a quick sketch of it to give you an idea at least what it looks like. It is a 1.8 meter Gregorian. It's located at a temporary engineering and development site in Chengdu, China. Eventually, it's expected to be moved to a much better site somewhere at a higher altitude. And just recently, the Chinese Academy of Science announced they did achieve first light on December 10th of 2019. So apparently, as far as I can tell, this is now the second largest solar telescope. Although they've gotten first light, I don't think they have all the adaptive optics. I haven't seen a data product off of it. So I'm still holding on to Big Bear being the second highest resolving power solar telescope until they can get the development finished on this telescope. It'll be very interesting to find out more about this when they finally do release some more information. From what I see, it appears to be modeled heavily on Gregor, but I'm afraid that's about all the information I have on this thing. Now, on to the data products. At any observatory, the observatory staff has to remember what is the point. A manager of mine once told me what you need to do is think of this like a business producing a product. What is the product? The product is not the telescope. The product is not the technology. The product is not the observatory. The product is actually the data. Everything else is secondary to just producing that data. And who are the customers for that product? The customers are, of course, our scientific faculty back at NGIT, and in general, the broader solar astronomical community. So with that in mind, what is really the most important point here is not the telescope, the site, but the end result. Now here we have an early movie from our broadband imager. This is a photospheric image taken in the red, showing that with adaptive optics, the telescope is able to achieve diffraction limited images, not just once or through lucky imaging, but through extended periods through the day. Can I replay that? Oh, okay. Oh, there we go. This is about 75 arc seconds across, so making that about 54,000 kilometers across there. And again, you can see these bright points in the intergranular region. You all know what the granules are. That's the material flowing to the surface convectively. It gets to the surface, it releases that energy, and then cools and falls down in the intergranular lanes between them. Well, keep in mind that material rising up is plasma. It carries magnetic fields with it. So if there's an unbalanced magnetic field, when that field is concentrated in the intergranular region, you're going to concentrate that magnetic field. So in these regions, what you're seeing is these brighter areas where that magnetic field is being concentrated and actually pushing those granules apart, allowing you to see down a little deeper into the solar surface. Now here is an image taken from our H-alpha imager known as VIS, the Visible Light Imaging Spectrometer. It shows, of course, H-alpha shows the chromosphere well. Up in the chromosphere, the hydrogen is trapped and traces out the magnetic field lines in the chromosphere. This is a line center taken, I mean, right at the center of the H-alpha line. And this, I should say, well, I'll wait to describe it till I go to the next frame here. But the important thing here is to note how H-alpha traces out nicely the magnetic field lines in these regions above the magnetic active regions. Okay, now here is a scan using this, the visible imaging spectrometer. This instrument uses a Fabry-Perot interferometer, which is very analogous to the etalons that Jen produces over at Daystar, with a couple of important differences. First of all, instead of being reflective surfaces coated onto a solid substrate, this is two reflective surfaces on plates that are separated and controlled through piezoelectrics actuators, allowing us to change the position, the spacing between them very precisely and very, very quickly. And what I mean by quickly is on the order of milliseconds. So this allows us to trace through the H-alpha line, or whatever line we're on, typically H-alpha, very, very quickly, and with the adaptive optics holding it stably, we're able to trace out from on-band to off-band. Now, as you are off-band, you're looking through the H-alpha line down to the chromosphere. As you come into closer and closer to line center, the line is becoming more and more opaque, so you're looking higher and higher into the chromosphere. As you're looking off-band, there are still H-alpha features that are Doppler shifted due to either falling in towards the solar surface or falling out. So by scanning through, you get velocity information about the flows in and out from the solar surface. Now here is a movie of the H-alpha center line. Not well produced, and yeah, here, yes, we have fringes, etc. That was not taken out in this, but I wanted to show that to show just what you get from umbral oscillations propagating up through the magnetic field lines up into the chromosphere, and then simultaneously looking in the op-band, we're looking in the red wing, showing that material falling back down onto the surface. If you looked in the blue wing, you would see material flowing outward. Also, here's an image I made, which I just think is spectacular, beautiful. It's a Dopplergram taken from that same data product from the VIS, the Visible Light Imaging Spectrometer, where I took off-band red and off-band blue images. I think I used the 0.4 angstroms off-band combined with the center line image. I colorized the red wing red, blue wing blue, and the center is yellow. So by being able to shift the wavelength exceedingly quickly and having adaptive optics holding the image stably, you can combine these to show the flow. Red here is material falling back down onto the surface. Blue is material flowing upward. Yellow is stationary, basically. And well, I'm just quite proud of this picture just because it came out so pretty. But this is a demonstration of what would be called a Dopplergram in H-alpha. We also have our near-infrared instrument, the near-infrared imaging spectrometer, NIRIS, which uses Fabry-Perot also, but sorry, Jen, we use stacked Fabry-Perot. So call us what you will.
She's going to call you a baby.
Yep. She's probably called me worse. Anyway, we use stacked Fabry-Perots to narrow the line further. We are looking at a line here at 1.565 nanometers. That's about 3 times the wavelength of yellow light, which is an iron line that is very sensitive to magnetic fields. The spectral line, under the influence of magnetic fields, will begin to broaden and eventually split into 2 components. One component will be due to one polarity, call it negative magnetic polarity, the other to the other positive polarity. By measuring the amount of splitting and the polarity of those spectral lines, one can deduce the magnetic field. But to do that, to fully deduce not only the field strength, but also the orientation of the magnetic field, you need to look at the optical polarity. Oh, I should mention those 2 split beams are oppositely polarized. One will be polarized circularly that way, the other direction. So by characterizing the different polarization states, one can deduce and map out not only the magnetic field strength, but the magnetic orientation and position, that sort of thing. So NIRIS, which is using stacked Fabry-Perots, sorry, Jen, can be used as a spectropolarimeter. NIRIS can also be used as a 2-dimensional imager. This is changing the wavelength from 1.565 nanometers to 10^830 angstroms, just into the infrared, just beyond the visible. There is a helium line there that is formed, unlike hydrogen alpha that is pretty much in the chromosphere. The helium 10^830 line is at the very top of the chromosphere. So this is a good proxy for what's happening at not only the upper chromosphere, but into the lower corona, which we can't see at this elevation. So here is a movie taken a few years ago, back when we used to have sunspots. And it's of a flare. It's rather important to be able to, okay, let's wait till this comes through again. By using this, which is much more optically thin than hydrogen alpha, it's easy to trace out the magnetic field lines along the plasma here and see the magnetic orientation before the flare, and then during the reconnection through the flare, be able to map out the resultant field configuration after the fact, which comes out to be a fairly nice arcade after that. Moving along, since I'm well over time, here is back to our broadband filter imager. It's just a high-speed CCD with a filter, 10 angstrom wide filter at centered at 7057 angstroms. So it's a photospheric image showing, again, a well-developed sunspot with several light bridges across there. And this really shows what you can see with extreme resolution on the sun. Those bright points down in the umbra are many of them around a tenth of an arc second, so approaching our diffraction limit. And well, at least back when I was an undergraduate, we believed light bridges across sunspots were just that. We thought that it was a bright material suspended magnetically above the sunspot. Well, in high resolution, just a casual look tells you that ain't true. You can clearly see that this is convection worming its way up through the magnetic ropes that make up the sunspot umbra. So you have convection here, You can see the development of the penumbra over here and the movement through that. You can see flows up there through. Anywhere you look in this image, there are fascinating things going on. I've gotten lost just staring at this movie. And then here was a movie of the Mercury transit on November 11th. We used our adaptive optics to lock onto Mercury as if it was a dark sunspot, and had to hand track across the sun, but used that to lock. And that worked quite well. It makes a very pretty movie. Unfortunately, our that speckle reconstruction code doesn't know how to handle this data set very well. So you can see like there's kind of a bright box around the dark planet. And as you get to the limb, the reconstruction code really breaks down and goes nuts. But that was a nice experiment that was we got some data off of and able to use some things. Also notice as you go across the sun is always in motion. You can see actually those 5-minute oscillations actively as you're scanning across the sun there. So another movie you can just get lost in looking at. Oh, and here is a movie put out from a paper that was put in Science back in November that shows the importance of comparing data across several different observatories. They compared photospheric and chromospheric data taken from BBSO to coronal data taken from the SDO, the Solar Dynamics Observatory. So what they did was they traced the bright features on the solar surface, correlated those with magnetic fields up through spicules in the features in the chromosphere up to the features continuing on up into the corona here from SDO images. So that shows that these features in the corona can be traced all the way from the corona down to magnetic features at the photosphere. So a nice paper and a nice demonstration of the importance of multispectral campaigns between various observatories using different instrumentation. Here's the same data set visualized differently, magnetic fields at the bottom, the photospheric image movie there with the chromosphere above that, and tracing into the SDO data up at the top. Okay, I'm finally almost done. I like to finish off with this picture. It's not a great image, but it's one I took several years ago here. And I think it's just pretty. It wasn't a great seeing day, but I just thought it was a particularly pretty image, so I colorized it, and I call it the bumblebee. And yeah, I just show it because I think it's pretty. And lastly, I thought I should say a few words about BBSO during the COVID-19 pandemic. We have just resumed observations. We had been shut down for several weeks with all of us hunkered down in our bunkers at home, but we came up with a plan to allow us at least to limitedly start operating the telescope again. Over the last couple of weeks, we've been bringing our instrumentation back online, testing the telescope, getting it back online. And within the last few days, we have restarted data observations. We are only allowing a single staff member in the dome at a time to operate. It's a lot for one operator to be able to handle, but there are 3 of us that are to the point where so long as nothing goes wrong, nothing really breaks, it is possible for us to operate solo. So, and as I told my wife Teresa here, I'm really more isolated there in the dome than I am here at home. Here at home, I see her. I can be at the dome and not see anybody all day long. Yes, tours will resume someday. What I suggest is you maybe check our webpage for any updates. I will admit that with all this sequestered away from the observatory, keeping the webpage up to date has been a low priority, but hopefully we'll start getting some things out there at some point. So yeah, if you want to find out more about BBSO, check our webpage. And with that, thank you.
All right. I appreciate you doing this. Do you want to end the screen share? So oh, you already did. So let's go back into the gallery view. Not many questions because, to be totally honest, I just kind of feel like most of us are just floored right now. It's unbelievable. I was not expecting that. I will admit this. I've seen things now that I can't unsee, and it makes me want to actually just get back out in the sun and dial in my Edelon, because I'm starting to realize I might actually have been off on some of the tuning, because now I know what I'm looking for. Obviously, I don't have that kind of aperture.
But I think Jen was pointing out, don't be afraid to also explore. Say you're looking at H alpha. Don't be hesitant to explore off band. You can often see features off band that are not going to be obvious in the line center, just because, well, you're looking at the top of the chromosphere. Down lower, you start to see some of those flows, etc., and you can see a lot of very interesting detail that way as well.
So there is one good question here: is it possible for amateur astronomers to detect magnetic polarity of sunspots?
That would be difficult. You would probably, the only thing that comes to mind would be you would need a high resolution spectrometer and see if you could measure splitting. There are a couple of lines in the visible that do show the splitting. It's called a Zeeman splitting. And it is possible with a high resolution spectrograph. One would have to develop a pretty high resolution spectrograph to measure strong magnetic fields by the broadening of that line. In the visible, you're probably not going to see a truly split one, but just maybe. That would be an interesting thing to try. I think one would probably need a pretty high resolution spectrograph, maybe fiber fed, something like that.
Right. Might be out of the realm of possibility for most people's limited wallets.
Or there are some clever amateurs out there that have done some very nice DIY projects. I wouldn't put it, I would not say it's impossible.
Oh, totally. Matthew Henry is asking, can you explain the active primary mirror balancing system on the DKIST?
On DKIST? I don't know very much about it. I do know that unlike us, we've gotten by with a passive system, but on their mirror, it's extremely thin. It has, I don't remember how thin theirs is, but being 4 meters across, it has to have a matrix of actuators that actually control the shape of the mirror. And active optics conceptually is very similar to adaptive optics. The only real difference is the time domain. In adaptive optics, you need to correct, like I said, in the kilohertz range. And for that, moving the primary mirror is just not possible. The inertia of that much class, you can't move that quickly. But for active optics, you're just trying to take out the deformation as the telescope points in different parts of the sky. So the time domain is very different, something more on the order of seconds or even minutes compared to kilohertz range. So it is done very similarly. they have some kind of actuator. I don't know what their actuators are out there, but they just have to be able to push and pull. They have a wavefront sensor then that measures the distortion off of that mirror and make the appropriate corrections. The details I haven't looked at.
These are more comments than anything else. I think a lot of people here know who you are, obviously. Jan from Portland, Oregon, Leo. Oh, geez, I can't pronounce that name.
Caballero.
Caballero, there we go. Thank you.
Hi, Leo.
They hope that you can make it to the Patagonia eclipse in December.
We're hoping to go down to Argentina for the eclipse, and Leo has invited us down. We're just hopeful that this pandemic will be over and we can still make the trip.
Right now, my head is just like swimming with so much things that are going on. Once everything is opened up, what can one expect from doing a tour at the observatory?
Well, again, we're a very small staff, and as you can see from our pictures, it's a very crowded environment inside the dome. We've had to shoehorn a 1.6 meter, 63-inch telescope into what was originally designed around a couple 10-inch telescopes. So space is a premium there. We do have to keep tours to an absolute minimum. Plus there's a lot of exposed equipment, etc. So what we have done is we have partnered with the Big Bear Valley Astronomical Society. My wife, Teresa, is the president, and they provide docents to act as tour guides to the observatory. During the summer season, when it's not an ice rink getting out to the dome, we have usually two tours per month. To sign up for that, one goes to our webpage and clicks on that little link, and you can sign up there or call our admin assistant. And what you get for that is you'll be meted at the gate, escorted in, give a talk about, not too different from what I probably said about the observatory here, brought down, shown not only the BBSO telescopes, but there is also the National Solar Observatory GONG instrument at our facility, shown the small telescope, then brought into the dome. And once inside the dome, brought through, shown the observing room. Oh, I didn't think to take a picture of the observing room. I guess I should do that sometime for a talk like this. Go up to the dome, of course, see the telescope, and if we're not too busy, myself or my colleague John Varsic try to come up to the dome and give a short talk about the telescope, answer questions, that sort of thing. We say the tours last about an hour. Sometimes I'm known for running on a bit, so they can last a little bit longer. The caveat is that the telescope is down a 1,000-foot causeway, which is a gravel walk. Vehicles are not allowed out there, so wear comfortable, safe shoes and be prepared to walk that distance. Then inside the dome, you need to be able to make it up and down 3 flights of stairs. There's no elevator, etc.
The data that you guys collect, and this is probably the big thing for most people at this particular point in time right now, is it accessible to the public, and can I have a go at processing it? That is a good question.
Yes, again with caveats. We are a private observatory. We are not a public observatory like National Solar Observatory. So our data first go to our principal investigator for whichever observing program we are doing. Those principal investigators have a proprietary period of I can't remember, 6 or 9 months where they get first crack at that data. There are a couple of our data products, such as I think the broadband imager and our H-alpha centerline are considered public from the start. They go after we observe through the day, overnight. Those data are transferred into our archive servers, where they are backed up both on disk and on tape. And then it is sent off to our data pipeline for the speckle reconstruction. That can take upwards of a day. Sometimes if we're really busy, we can get backlogged by a few days. Once they are in the archive as processed data, there is a form on our webpage that allows one to go and request data. So unfortunately, it's not set up conveniently for an amateur to go in and browse, but we do have some products in there that allow people to go through, see what data has been taken, look at our log, and it is conceivable that if there is a particular data product that has been taken and is now public, that one can fill out the data request form and get that image or those images. I will say that right now, with everybody hunkered down at home, uh, it might take a while for us to respond to a data request like that.
Yeah. This is a question that I personally am asking. How does one get into what you do for a living? I mean, obviously, going through all the science degrees and so forth and so on, but I guess what I'm saying here is somebody who's watching this video and says, that's what I want to do for a living. How do you get that person into it?
Historically, there have been different approaches. Since I am part of the technical staff, there have been different paths into astronomy through the side door, so to speak. I happen to have a master's degree in astronomy, so I have a particular angle that I take care of. But in astronomy, just like any industry, we have a need for many different talented people. So the first thing is, of course, try to get a background. Best is try to get some college background, astronomy, physics, etc. Very good, but also practical experience. At Kip Peak, where I used to work for many years, quite a few of the technical staff were ex-military who had electrical experience from the military, that sort of thing. Programming is becoming ever more prominent as a need in astronomy. So the main thing is follow your passion, follow your interest, and keep after it.
Brilliant. Okay, if there's no more questions, we have got a 15-second delay roughly. So if you guys want to just fill in your questions, I will be doing my talk at some point today. I will have to go for a break because I have been here since 8 o'clock my time here in Los Angeles. So I've been sitting here for quite some time. Clyde, thank you very much. I'm so glad that we had you on here. I'm so glad that Tiffany recommended you to do this talk. I got to admit, like I said, I wasn't prepared for what you were going to go into. And just to be quite honest, I'm just so blown away right now. It's just like I'm almost speechless. It's so crazy.
Well, I'm a hardware guy. I've been accused through my life of being a telescope hugger all my life. So that's kind of the direction I come at it from. And just let me say thank you for having me, and thank you to everybody out there. This is a difficult time. Stay safe, stay well, and we'll see what comes next.
Yeah. And it's good that we get to do these live presentations at the end of the day, because otherwise, where you guys would normally have the outreach, you wouldn't be able to reach out to anybody. And it's good to have stuff like this.
I
So
think we're all learning a lot of lessons through this, that there are different avenues we haven't really that much investigated in the past. I don't think going back to normal is ever going to be the normal we saw before. I think we're learning a lot about seeing different avenues to do a lot more.
I mean, technology, I got to say this though, technology has so drastically changed the way we do things. I mean, I'm talking about from the early days of solar astronomy by the Chinese, who used to just like build fires to make smoke, and they would purposely put wet bamboo in there to smoke it out and try and look at the sun.
Well,
We've come a long way from that.
Even through my career myself, I came into this, I hate to say how long ago, back in the mid 1980s, when Apple IIs were still around.
Right.
The transformation we've seen from technology just during my career has been mind-boggling. I remember shortly, right after I got my job, before I started the job at Kip Peak, a friend of mine said he'd read something about this new technology called adaptive optics and wondered what it was, something about somehow canceling out the distortion of the atmosphere. And my response was, you can't do that. That just sounds like magic. And I made it my goal at that point to not only learn more about adaptive optics, but someday to understand it. And now, a few decades later, I've actually built a couple of adaptive optics benches. The transformation we've seen from all going back to high-speed digital computers has been mind-blowing. We now deal with data processing in ways inconceivable back when I was an undergraduate. CCDs have taken us from back film had a quantum efficiency of what, about 4%. We're now approaching 90, 95, 99% quantum efficiency. It is what I would have thought when I was an undergraduate as impossible. So it has been an exciting career, and I think there's still tremendous opportunities ahead for us.
Excellent. All right. So no more questions. Like I said, I think people are still in shock with what they saw, because it's like you've literally covered every part of everything that anybody could possibly ask. I'm sure there is going to be one person out there that's going to have another question at some point in time. But if I get any more questions, of course they can still contact you through the website. Do you happen to have that slide up again? Because it's quite a mouthful.
Let me go see if I can go back and somehow, I have to share a screen. So I need to come back here, share screen, share.
Yep, there it goes. Yeah, so you can leave it there. So for those of you who want to check out their website, remember bbsoweb.njit.edu.
Or just Google Big Bear Solar Observatory.
That too.
If you Google Big Bear and astronomy, you'll get 2 hits, one for the Solar Observatory and one for our astronomy club, the Big Bear Valley Astronomical Society.
Perfect. Matthew Henry says, Sophia and Gigi says hello.
I still owe them an airplane ride.
Uh-oh. Thank God for the coronavirus that you don't have to fulfill that just now.
Just now, that's true. Okay, if that's it, then I guess I'll let you go, and I apologize for...
No, it was totally worth it. I don't mind running over for stuff like this. It's worth every second. It really is.
Okay, well, thank you so much, and we'll see what the next decade brings.
Yeah, and hopefully we'll see you back here for another event at some point.
I'd be happy to.
All right, then. Thank you very much, Clyde.
Okay.
Guys, we will be back later on with my tutorial. Until then, I am going to go on a quick break. So we're just going to play a couple of videos, and we'll catch you on the other side. So see you in just a moment.
Part of the challenge that the amateur astronomy community is facing is to bring in more people into the hobby. So we've been actively trying to contact different people, science communicators, people with influence are also interested in astronomy, to help them help us popularize the hobby. I think it's very, very important for all of us to do that because as a hobby, we want to make sure that it's growing. And one way to do it is reach out to younger people, make sure that the next generation, the younger people, are actually getting into the hobby.
Basically, I look at it now and I think of astronomy as more of a really artistic. You look at all the beautiful pictures that they do, and I think that's going to bring more people in. It's like getting the big buck for the hunters. You want to get the most beautiful picture that you can get, and it's kind of a competition, really. Something that can be achieved, and you don't have to have physical strength. You don't have to have all these different things, but you can go in and just be able to have that creative spark and eye, and go out there and work with it.
I guess what I do is I have a small group of friends near my home. And if I have a night where I decide to take out the telescope, I'll invite them along. It's not really their hobby, but it's nice to branch that out. But I would like to do some outreach to some high schools or elementary and get the kids interested early so that it's not something you're starting when you're 20s or 30s. It's something you start early on and you just get that for your whole life.
Already we can see that the impact of social media has popularized astronomy a great deal amongst people who just have no real direct interest in astronomy, but they get excited about these things, like this eclipse that just occurred. Had one of the largest turnouts that have ever occurred for a solar eclipse. And I think it's 100% due to social media and the news coverage that it gets. So I think that is making it more important. In other words, you can reach people much easier now than you ever could before.
I think the general public is more into the now results, so a lot of people like to share things. I find that people like sharing, they want to see results, they want to make things easy. So I see a expansion into just easy imaging and sharing.
There's a lot of people now doing science, not just astrophotography anymore. There's a lot of people doing science. There's a lot of citizen science, and there's schools that are doing science. The easier we make the telescopes, the more science that the schools can start doing. We get colleges doing science, and maybe even down to high schools doing some science projects with NFS grants and such. So because the capabilities of the telescopes today are so much more, I think the way to get the young people involved is to get them using them in schools.
On the scientific point of view, astronomy is trying to answer very fundamental questions, and most of them have to do with cosmology, meaning where does the universe come from, and there are still many questions. Most of them are unanswered. The other search, I think, in astronomy is searching for other planets, other intelligent civilizations, or even sign of life, simply sign of life on other planets. I think that's the second quest. The first, I believe, the first should be trying to find out, answering the question, the big question of cosmology today.
I think there's a renewed interest in astronomy. It really peaked for our generation, or the generation slightly before us, with the moon landing and the Apollo program. And then we had the space shuttle, but with the cessation of flying the space shuttle, people predicted that there would be less interest in astronomy. But as Cassini and some of the other probes have demonstrated, a lot of interest is generated because we're getting looks at our solar system with the technology that has been put into these probes that we were never able to get before. And I know that the generation, my children's generation, has a lot of interest in these types of things, and I think that interest will continue. And those are the future astronomers and future amateur astronomers that are coming out of that.
I think what you're going to see, and what you're already seeing, is that amateur astronomy is making significant strides in the professional realm. You've got amateur astronomers finding comets and asteroids and near-Earth objects, and I think that's just going to continue to happen. I see a network of astronomers, maybe a network of satellite imagers. If you can turn households into a satellite spot, and suddenly you've got a satellite telescope that's the size of a hemisphere, just because amateur astronomers are working together. I see that happening. I see the entire community coming together and doing more.
In terms of making astronomy something that it can reach a much broader audience, we want to see more development of those accessibility options via the internet and ease of use, to try to make it a simple process. Using your iPhone is a pretty easy thing to do. And it'd be great if we can get to where people can access these high-end telescopes and take these terrific images and also do research. You think about the science projects we did when we were young, in some respects pretty primitive what kids can do today.
One of the most successful programs that I've seen for engaging younger students and younger kids in astronomy is the Sonoma County Astronomical Society has a program where they have students, little kids, write essays, and then they take the best essays on astronomy and they give them telescopes. And these kids, I've been surprised, it's mostly girls. These kids, they get these telescopes, they bring them to star parties, and they become little experts, little amateur astronomy experts, and they give public talks and presentations, and this is one of the most successful places. I'm a member of about 5 different astronomy clubs, and this is a great way to bring in a younger generation and help them maintain it, because we've seen over years now these kids come in and they stay in there. And this is a kind of program I think we need to scale it, we need to use it as an example and do it elsewhere. Just sort of one small example of one thing we can do.
We live in a fast age, right, where our movies and our music, our media, fast edits, instant gratification, loud and in-your-face kind of stuff is required to hold people's attention today for a half a second, which is sad. And so the subtle and the esoteric stuff suffers. I think it's very difficult to get a lot of younger people into this as a hobby. It seems like there's more younger folks, even women, who manage to get into the professional sciences, astronomy, cosmology, whatever it is, but in the amateur way, getting them to a telescope, getting them to a dark sky, inspiring that wonder in them is difficult, I think.
Giving someone the opportunity to not only see it for themselves, but do it for themselves, and say, here, have a look. For example, if they have the privilege of looking through a telescope and seeing the rings of Saturn, give someone that opportunity to do that and see it for themselves with their own eye. It has an incredibly powerful impact. And what I'll find, and for those who, like I say, there are many outlets where you have an opportunity, city star parties, outreach events. Once you see it for yourself, it's like a catalyst that the rest starts to take care of itself. The interest will be there.
One of the things that concerns me greatly is the fact that so many people are moving away from science and from facts. The fact of the matter is math, history, science, and facts matter. And so to advocate that and to advocate education, I believe that college education should be absolutely free. We should be investing in the brain trust of this country. And so to me, our job is to advocate science. Our job is to inspire people to really embrace what is right.
The stars are for everybody. And I would like that, if I could do that, if I could spread the interest out amongst everybody, that would be the biggest contribution I can make.
Okay, I'm back. I had to eat something very, very quickly. I think that's the fastest I've ever eaten anything. I'm probably going to get indigestion in the middle of this, so please excuse me if I have weird involuntary bodily functions. You won't hear them, thank God. So what I'm going to do, I don't even know how I'm going to follow up with Clyde's talk with showing some of those images. It's just absolutely mind-boggling what you can do with aperture, aperture, aperture. So what I have prepared for you guys is a live demonstration of some of the processing techniques that I use from start to end. I'm not going to go through the capturing side of things because it's gotten cloudy now, and it's very, very windy outside, so that kind of just ruined everything for me. But hopefully what you saw earlier on when we were doing the talk with Steve Ramsden, it's pretty much what I do when I'm doing my imaging session. So I have, the scope set up and I have the program running and I actually watch the screen, and what I'm doing is waiting for those moments of clarity. So I'm going to show you something now that is indicative of good seeing versus bad seeing. So let me just move this out of the way. And yes, that is my cat. That's meowing down there somewhere. So here I have a video of, it's not a video, it's actually the data that I'm looking at when I've actually just done a capture. So let's just assume that we've just captured this on the sun sometime today. And what we're going to do is we're going to check out how good or bad the quality of this actual data that we've collected. So I'm going to play this in pretty much real time. It's around about 60 frames per second, so it will look a little bit jarring over YouTube. But what I'll do is I will pause it. Now, what I want you to do is pay attention to the fact that I don't really see a lot of surface details. It's ripping like crazy, and it just looks all smushed out. So I'm just going to pause this and allow the YouTube algorithm to catch up. I'm just going to shuttle into an area where it is just dreadful, which is right here. So give it a few seconds and hopefully this will stabilize on the video stream. As you can see, you cannot pick out much surface details or anything that's really going on. The spicules are very, very hard to see along the limb of the sun. And this is a good indication of bad seeing. So now when I show another video, this is more in tune to what is good seeing and having the contrast looking really, really nice and sharp. And you'll see a noticeable difference. And now this is just a still frame right now. So I'm going to play this back so you guys can see this happening in real time. You can see the huge difference between the quality of good seeing versus bad seeing. And when you go to process these images, it actually makes a huge difference. So when I'm working off of something like Lucky Imaging, as you can see, the frames that I get from here versus here are few and far between. Now, this is not done as I didn't defocus this, I didn't cheat, this isn't a filter, this is raw data that came off of my scope. And I wanted to show you guys the true difference between good seeing versus bad seeing. You know what, for fun, I should really put these on two opposing sides just to make it look like it's one image. These were taken at two completely different days and two completely different times. So just so you guys can understand, but you get an idea of, excuse me, I did say that I did eat very, very fast. This gives you a good indication of good seeing versus bad seeing. And again, I'm just going to scrub through. We can clearly see that this is going to just be dreadful. So I'm actually going to process both videos so you guys can get a good look at what's going on. So the bad seeing is the one that we're going to start off with. And again, we're going to use Auto Stacker to do the stacking side of things. If you guys got any questions, feel free to fire them off. I will try and answer all the questions at the end of this demonstration, which will probably be the easiest way to do this. Excuse me. So let's start with the bad seeing. What I'm going to do is, like I would normally do, I'm going to do a quick analysis to see how many good frames that we can actually stack versus how many frames we can't stack. And I'll just quickly run through this just so you guys can see the difference in the graphs, because that's the part that I kind of need you guys to kind of pay attention to. There's around about 5,000 frames here, probably way more than you really need to capture. But because it was such bad seeing, I really had to push the absolute limit of this to try and get any usable frames. Because I'm capturing at such a high frame rate, even at 60 frames per second, the time it takes to capture this length, features haven't changed drastically enough for it to be a problem. With the prominences, on the other hand, that does become an issue. So you have to have a trade-off of how many frames you're going to try and capture. So this is almost done. And yes, this is my cat right here still. She's my assistant. Now, for those of you who are not familiar with this and you want to be able to go through this in your own pace, I do have a video up on my Patreon page, which is basically patreon.com/Simon2940, or you can check out the free one that I put on the telescopes.net YouTube page. Again, it's absolutely free. You can watch it from there. You don't have to become a subscriber to my Patreon page. It just helps when I have people contributing. And then I can produce cool stuff like this, obviously. So because obviously the more frames that you have, the longer this takes. So this is why this has taken a lot longer than it usually does. So now we actually have an idea of how good or bad the quality of the video is. As you can see, a large majority of my frames are below the 50% threshold. That's what this line here in the center that runs through. This heartbeat, as I like to refer to it, it tells me where all the good frames supposedly are. So as we can see, somewhere here, the quality estimator has determined that this has given the best view and that all frames are now determined from this particular point because it's one of the highest scoring areas. It then gives me an average of how many frames that I can actually try and do the stack with. Now, in this particular case, this blue line here tells me how many percent that I can actually go for, 25, 50, 75, obviously 100 being to the far right. So looking at this, only around about 10% or even less than that, 5% of my frames are actually usable. And in reality, if I got results this bad, I would just simply trash it. But for the sake of showing you guys something, we're actually going to trust that this is going to give us a somewhat good result. So let's just go ahead and stack this and see the result. And then obviously we are going to do the side-by-side comparison in just a moment when you actually have good seeing. And we'll do a 5% stack. So, we'll try and keep this fair. Needless to say, there are 5,000 frames here. What I should have probably done is limit the amount of frames to make it a little bit more fair, but we need to give this footage some advantage. So off it goes, does all its things. Again, depending on how many frames that you've got here, it'll either be faster or slower. The frame size also is a huge determining factor. So if you do shoot in something like 1920 by 1080, that is considered high definition, and that can take considerably a lot longer. And again, having good hardware, like a good computer, does make a big difference when it comes down to processing power. So ideally, you need something at least like an i5 or equivalent. In fact, actually, with the AMD side of things, if you're an AMD user, Threadripper actually works incredibly well with this because Threadripper does nothing but crunch numbers, and that's exactly what this program is doing, is number crunching. So we're almost at the end here. And this part usually just is pretty quick. So now what happens is I've now finally got an image, and we're just going to preview it real fast. I'm just going to open it up in Photo Viewer. And there we have our final stack. Nothing to really write home about. It's not the best of images in the world, but this is what we're going to get from bad seeing. So it's taken all of those frames, averaging 5%, and that's given us what that stack is. So now what I'm going to do is we're going to go and open this up in IMPPG and see how much of it we can actually clean up. So we need to go into that file. That's the 5%. There it is right there. Let's shrink this down a bit, and I want to do a select all so I can see the whole thing. And now I'm just going to play around with the histogram real quick to see how much we can actually pull out of this. And it's not bad, all things considering. Needless to say, there is a prom there. I kind of knew that was going to be there because, hey, I took the footage, so I knew it was going to be there. And then we can try and do some kind of sharpening to try and improve the quality behind it. And in all honesty, with such bad seeing, we just simply cannot push this too hard. And no matter what we do, it just seems to have a very, very soft looking image. I mean, if this is your first time and you just want to see something, this is not a bad result, but it's not a true or a good representation of what you can actually achieve. So now what we're going to do is let's actually look at the good data. So let's bring that in, and we're just going to do a quick analysis to have a look at the frame. And remember what I just showed you earlier on. You may have to wind this video back. Not right now, preferably, but when we do the replay, you can actually have a look at the difference in the graph, which is going to show up here. So as soon as that shows up, I'm going to go into it in a bit more detail, hopefully. So now this actual shot is taken on a completely different day. I believe this was taken way back in July 2019. This was taken a lot more recently. I don't remember the date. I know the time. It was at 10 o'clock in the morning at some point, but that's about as much as I can tell you right now without checking up the information. So here's the big difference. Notice that the quality graph, majority of it is above the 50% mark. And in fact, we have at least 15% of these frames that are above the 75% mark. Now, we're only going to do 5% because remember, we want to try and keep this fair as the comparison to look at one versus the other. So I'm just going to leave it at that 5% for a moment. Now, remember, it's 5% out of however many frames. Now, I've only got 2,000 frames here compared to the 5,000 frames from the image that had bad seeing. So it's already got an advantage in that particular respect. So when we actually go to stack this, we're going to see a tremendous difference. Now, usually when you stack these frames, the more frames that you stack, the less noise that will appear. It's just like you would do with nighttime imaging. The more data that you collect, the less noise that you are getting. So again, we are back down to that argument of signal to noise ratio. The more signal that I have, the clearer the image. But there is this trade-off when we come to solar is the surface changes so incredibly quickly that if I try to do a 5,000 stack that was taken over, say, 10 seconds or even 15 seconds, the features could have actually moved so dramatically that it will actually smear the detail, resulting in what would appear to be a blurry or a poor picture. Now, I'm not going to change anything or any of the settings here. I'm just going to simply open this up so you've got a clear comparison. Now, remember, that is the original one, which is this file here. And now I'm going to open the one that we just stacked. And immediately we see a huge difference. In fact, the settings on this almost don't work because it's now overly sharpened. So this is where we have to really dial some of this back. Now, yes, this image is incredibly noisy because we only did a 5% stack. So now the big thing here is what happens if we actually increase the amount of frames that we stack over here. So let's have a look at this graph again. we know that we can have at least, okay, 15% of all of our frames are going to be above the 75% mark. But we're going to push this one out even further. In fact, we could probably go to 25% or even go as far as 50% because the data is actually so good. Now remember, let me just clear this so we can see this. As I shuttle through this, the only reason why certain frames are deemed not as good is because of the tessellation. So the tessellation is that wiggling effect that you see in the atmosphere that is claiming that certain frames aren't as good as other frames depending on the reference frame. Now, you've got to pay attention. This green line does not correlate to when I scrub through the timeline. It actually correlates to the gray heartbeat in the background. So what I'm going to do here is I'm going to push this one and we're going to go for 50% because we can. I'm going to place the alignment grid again, and then I'm just going to run the stack on that. So now what's happening here is it's looking at that reference image. It's finding the best one, which is somewhere in this region here, and then it checks every other image before and after to compare against the reference image. The next step is the actual image alignment. So depending on how good or bad your tracking is, if you're on an alt-az or equatorial mount, this will actually nudge each of the images left, right, up or down, or even rotate in order to line up all the images. So once it's actually figured that out, it'll then do the stacking part of this. So then each image, if you can imagine thousands of images being put on top of each other, it does not make the image any brighter, but what it will do is it will sort out what is noise and what is signal. Where it does the map analysis and the map recombination is it looks at the tessellation. So this grid that we've placed here, these alignment points, as we go through them, you won't see it here because it's just a reference point. These things actually move and change frame by frame as it does the analysis. And what that does is it tries to actually remove the tessellation that comes from this and then remap that part of the area. Now, I've had multiple arguments about the actual size of these. Is it better to go for bigger or is it better to go for smaller? The problem here is it's really what works for you. I found that 48 on the 174 with this type of pixel scale size has the best results for me because it's enough tracking information to look at any major tessellation movements. If the grid is too big, I do end up with an image that does appear a lot softer. Now, if I do 24, what tends to happen here is the image can break apart quite severely, and then I end up reintroducing tessellation into the final image. And when you go to process it, you get these horrible blocks showing up all over the place. Again, this is one of these things where you have to experiment with it and just test out all the different types of settings. You can actually fine tune it by, typing in the number, pushing it up or down. Whatever works for you would be the best way. So now that it's actually done the 50% stack, we're now going to open up that file. So here it is, there's our 50%. And by comparison, this does appear to be a lot smoother. In fact, the noise, I'm going to really zoom in here and just let YouTube settle down with the compression algorithm. You can see some of that noise, but it is nowhere near as bad as we would have gotten with the 5%, which is pretty severe. So, you can clearly see all of that noise all over the place compared to the 50%. And in all honesty, at 50%, because seeing was just so good in this particular case, it has actually produced a pretty darn good result. Now, from a sharpening standpoint, yeah, we're pushing this one out a little bit, so we need to kind of tone this down a wee bit because it is just a bit too much. And again, very, 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 very subjective. And I'm going to go through what's going on in just 2 seconds. So I kind of want to see more of that surface. So let's just bring some of that back up. So we can see quite a dramatic difference right now in terms of the surface detail, the spicules, and certainly the prominences, because as you can see, there are some serious problems happening in the background, not as big as the other one, but still nonetheless, they are pretty strong. And I can push this as much as I need to. The cleaner your data or the better the seeing, the sharper these prominences are going to appear. So obviously today we were capturing some data. I did quickly process some of that data and shot when it was at its peak, so to speak. Unfortunately, it's kind of windy outside, so it really was messing with me with all the crazy wiggling. Sorry, my cat's going nuts. So let's go into Auto Stacker a little bit more. So let's just minimize this and keep it out of the way. So Auto Stacker, let's get into the guts of all of this. So this is more specifically for solar imaging than it is for planetary. Of course, you can use Auto Stacker for planetary imaging. It was originally developed for that particular purpose. What you do is in the installation by default, it already actually has the best settings possible for you to start using right out of the box. But there are certain things that I like to go in and tweak, for example. So first of all, let's go into memory usage. There's buffering and no buffering. I've experimented with both of these before. I've actually found that buffering tends to be a lot better than no buffering, especially when it comes down to responsiveness, especially during the scrubbing and the playback. So you have to be careful here. If your file size exceeds the amount of memory that you currently have on your machine, buffering can be detrimental. So for example, if you have a computer that only has 8 gigs of RAM and the file that you are trying to load is 9 gigs, some of that obviously is taken up by Windows, so you only end up with, say, about 6 gigs of usable memory that's left over. A lot of it will be offloaded onto the hard drive, depending on how good your machine is. If you're using SSDs or you're using a mechanical hard drive, it can be detrimental to the performance. If you find that being a situation, then go with no buffering, and what it will do is it will load each individual frame by frame, resulting in a much choppier playback or scrubbing through the timeline. But because the machine that I'm using has 32 gigs worth of RAM, I don't really have a problem, so I'm just going to run with buffering. The next options here is color. Needless to say, we generally shoot in monochrome. So when you leave it on auto detect, the thing is intelligent enough to figure it out that this is a grayscale image. If you did use a color camera, you can tell it to see which matrix you are using. You will not be using RGB. That just doesn't even make sense when it comes down to that. But most of the cameras out there is actually red, green, green, blue. You do have to look at the specifications of your camera so you know which one's which. Majority of all ZWO cameras, QHY cameras, or CMOS chips uses the red, green, green, blue Bayer matrix grid pattern. Monochrome, obviously, needless to say, is just grayscale. So in the advanced section, there's quite a few things that people probably don't really worry about or care about, but this is actually useful in certain situations. Like, for example, detecting of abrupt horizontal or vertical artifacts, especially on the edge field of view. That's really only applicable if you're using a camera that has a, is it a global shutter? I can't remember. If it's a rolling shutter, it's a global shutter. Either way, if you see screen tearing or lines showing up, this can actually help realign all of that stuff. Again, it's a bit of a, you've got to test it out yourself to see if it works for you or not. Brute force alignment, you can actually use it. It's, like it says, it's recommended for deep sky type stuff, but that actually looks for any breakages in the actual image. When it comes down to things like rolling shutter, this was more developed for back in the time with the Melon cams and things like that, that you could actually utilize that type of stuff. It was great for comets, any type of fast moving objects that might have weird little artifact lines or even interlacing lines. Ultra smooth map recombination is basically the same thing in this particular case. It takes the first frame, last frame, combines it into two, de-interlaces, and honestly, I've never used it because it is just not worth it, especially when you've got when you've got data as clear as this. Experimental features, I've never played with it, to be honest, so I don't really know what that does. Discard worst global frames, that is clicked by default. All it does is it will automatically reject all the dud frames. So remember what I was talking about, this quality graph. Anything below a certain threshold is just straight up trashed and will not be included in the stack. Now, I'm always going to turn around and make sure that this is always selected. Again, by default, it is selected. And what that means here is it is less likely to pull out any of these bad frames depending on what your threshold actually is. So if it's set to below a certain threshold, normally 25%, I think it is off the top of my head, all of these frames are just simply discarded. So out of 2,000 frames, I may only end up with 1,800 frames, and I'm only stacking 50% of those 1,800 frames. So there is no way am I going to get bad data being introduced into my final stacked image as long as this is actually turned on. Image calibration. So this is a part that really rubs people up in different ways. Some people who use the IMX 174 sensor, e.g. the ASI 174, the QHY version of the 174, sometimes they actually turn this on and try and use this to correct for the horizontal lines. Now, let me just clear this out of the way for a second. You can actually see that there's no really apparent horizontal lines on this actual image. So the idea here is you don't actually want to turn this on, because what it can end up doing is calibrating and putting these lines in. You only need to do this if you actually have these problems showing up. And they usually take on the look of interlacing lines. Interlacing lines basically looks like every other pixel, a very faint white line runs through the image. I'm going to try and push the brightness of this. And you can see, if you look up in this area, again, I have to wait for the YouTube thing to settle down because of the algorithm that they use for compression. You can just about make out some of these faint bandings that go from left to right. And what this actually does is it actually helps reduce that problem. Now, when I'm shooting, doing solar, especially on prominences, I tend to keep the gain down as low as possible in order to avoid this horizontal banding effect, because it becomes more apparent the harder you push that gain. And it all depends on the type of telescope you have and the size of the aperture. The next things are master darks and master flats, and then dead pixel map, which is basically a bias frame. You can actually load these ahead of time before you actually run the processing. In fact, I actually recommend that you always do a flat frame when it comes down to solar imaging. What this helps is eliminates vignetting, anything that can be caused by the field stop, unevenness caused by the Edelon, regardless if you're using a Meade telescope, a Lunt, or any of those scopes, or even the Daystar. A flat field is absolutely critical. And it can also help take out any of those residual Newton rings that you might actually be getting when you're doing imaging. These do not completely remove the Newton rings if you don't use an interference filter. It's best that you remove it from the source than it is to try and calibrate them out. I'm not going to go into how to make flat right now because I think that's been covered by plenty of other people. Master dark, how critical is this? The answer is not as critical as you would be imaging with, say, deep sky products of any description. So if you were doing, I don't know, the 1600 and you were getting a lot of inherent noise coming from the camera, a dark will help drastically on things like that, especially amp glow that shows up. But because we're shooting such a high frame rate and very, very limited exposure time, amp glow isn't a critical factor. However, having a dark frame still actually helps get rid of some of these residual banding or patches that you might have because of the sensor. I tend to ignore it because it's just an extra step that I just don't really care for, to be totally honest. If you have an older camera or a camera that has dead pixels, ideally you should actually create yourself a bias frame. You could do this. It does not take more than a few seconds. A couple of shots is more than enough to do a dead pixel map, and that will just get rid of any hotspots or dead pixels that is on your camera. I do highly suggest that you do this if you find that you actually have problems. And of course, you can actually create master frames, although this is kind of not needed because it's actually done automatically. So that gives you an overview on some of these settings here that's actually at the top. Some of these are pretty much self-explanatory. You can save the stack as, save it where you want it. You can open and close. It's all the boring stuff that you probably don't really need to go into. So let's have a look at the image stabilization section. So right now, as we're looking at it, we're doing surface. This is not a planet. Even in full disk, you actually want to use surface. And the reason for that is it's going to try and look at the entire frame. And this red area here is the actual cutoff point. And if I was to do the analysis on this, it'll actually try and realign everything to be able to stack this. Now, the problem here is, though, it's not creating a full circle. So obviously, this isn't going to work. This is why surface stabilization works better than the planet stabilization. Now, here's the important part. You have the two different types of views, expanded versus cropped. Cropped image size only looks at a smaller section, whereas the expanded is anything around and possibly larger. So the idea is this. What you want to do is you need to ensure that where it does the stabilization anchor is not outside of whatever it is that you're looking at, because the blackness of space is not a piece of the surface. So there's no data that it can actually track onto. And what you'll end up doing is track onto noise, which, because it's highly random, it's just going to jump around like a maniac, which is why we try not to have this run off the edge. So ideally, you need to find a spot that is completely covered, but has some type of discernible feature. Now, because this one is actually really good seeing, it almost doesn't matter where I click on. This thing has got plenty to actually track off of. And because we've already actually done the alignment, we've actually done the analysis part of it, this has actually done a pretty good job of doing the tracking. So as you can see, I have some error, which was in RA and DEC, because if it was in one axis only, this would only shift one direction, but this is shifting on left, right, up, and down. Hence why I have this red bar that's changing. The next thing is the improved tracking. If you find yourself in a situation where you do have jumpy footage, what improved tracking does is it almost goes back and does the track again, and then does an average to make sure that you get an absolute smooth track. Now, if you know that your tracking is relatively good to begin with, having improved tracking will not actually help. And you can just tell just by simply scrubbing through the timeline, and we can see that it's actually pretty damn good. Quality estimator, noise robustness, etc., etc. So a lot of people don't really understand what this is, but the Laplace, for example, I always have it selected. It's just basically an algorithm that looks at noise versus signal, and then we can actually calibrate in what is signal versus what is noise. So if you're shooting something, so focus on very small, high signal to noise ratio data, as I run through this graph will update accordingly depending on how much the noise robustness is turned up or down, because that's also part of the quality estimator. So if you know that your data is good, you can actually turn this thing down, and this will give a much more stricter quality graph and then give you a more realistic number to actually work off of. The next one is local versus global. Global is going to look at the entire frame as your quality estimator, whereas local is actually based off of all your anchor points. Let me just run the analysis real fast so I can just quickly show you what I'm referring to. Which ones do I use over which? I prefer to use the local over the global frame. And the reason behind that is during the map analysis and the map recombination, I wanted to reuse that data that we got from putting down those anchor points. Now, when you're doing global, it can do the same thing, but what it tries to do is work it out without having the anchor point data, which actually takes a lot longer if you haven't already pre-done it. So obviously during the analysis process and then placing these alignment grids, it's actually a lot faster in the processing sense if you did it in that way. Does it give a better image quality versus one from the other? The answer is just straight up no. It's more of a timing thing than anything else. I've again experimented on both situations and I virtually get the same result. The next thing is the reference frame, double stack reference images. This is actually an interesting situation here. Is what it does here is it actually takes each frame that you've actually selected, so 50%, 20%, however many percentage of the frames, it'll stack that section twice, combine the two together, and then create an average reference frame to compare off of. And the reason why it does that is each time round you run this, a result may change depending on where these grids align. If I never change these settings, I would get the exact same number. But if I was to change the anchor points, the data that would be gotten from this is now going to be different compared to the one that I hit with 48. So by doing the double stack reference frame, it'll always have a way to look at the previous frame and the next frame, combine the two together to create an average. So it actually gives you a better looking result because it's able to average between the two. You get other things like sharpening, for example. I'm going to skip this part for just real quick because this requires a bit more attention. You can actually do deconvolution ahead of time by clicking on this, and you can blend in the frames, however many frames you want it to be sharpened or unsharpened. I tend to leave this off because we are going into a processing program, so it's actually best to have this off than to have it on because we need to be able to control it. Save folders and file names, all it does is just determine the name of the file and so forth and so on. This can follow WinDrew posts, naming conventions if you want to program that in. So essentially what we've got here is the time that this was taken, how much of the quality estimator, in other words, the Laplace or the noise robustness number 4, that's what lap and then 4 means. And then obviously the name of the file, which you can just call it anything you want. And then afterwards, you could just send it straight to a program and then have it open up. I have all of that turned off by default because I don't want to do that. And then drizzle, I'm not going to go into too much of this, but all it does is it resizes the image. So if I wanted to make the resolution of this image or the final image bigger, I can actually do drizzle. Now, bearing in mind, drizzle is only useful, or even resampling, it doesn't really make any difference. It's the same principle. It only works if you have good data. You cannot drizzle bad data. So as I said before, with the video that was bad seeing, drizzling this would actually create a worse result. And it's actually, drizzling is better than trying to enlarge in Photoshop afterwards. It's better to drizzle the data first, then put it into your image processing software, and then you can save that out. What tends to happen here is that you've got to be careful with the drizzling. If you do not have calibration frames or you have banding or any other strange artifacts, the drizzle can make this worse in so many cases. There's been plenty of times when I've been messing around with this and I really want to push it to its limit and I turn on drizzle and all I get is just horrible mess and it's blocky, it doesn't calibrate well, and it's just a nightmare. So you have to understand, you have to have good, clean data that's calibrated in order to be able to use the drizzle effectively. So hopefully that will give you a good rundown of all of this stuff. So why did I leave the stacking options to last? Because this is the critical part, at least to me. There is no magical number that I can give you that will give you this. You have to look at your quality graph. Remember, the midline has already been marked for you, that 50%. This green line is what we're paying attention to. Right now, I can see more than 75% of all of my data is above the 50% in terms of quality. At 25%, majority of it, because not all frames are that good, majority of it is above the 75% mark. That tells me that I am going to get a relatively good sharp image when I come to stack these parts together. Now, depending on how many frames that we stack, the more or less noise will actually appear. So the more frames we stack, obviously less noise. The less frames we stack, the more noise that we get. So what I like to do is, I don't mind blending in some of the bad frames, but I have to be very careful with doing that. Ideally, I don't want to stack 50% and then have this line somewhere down here that tells me that 50% of all my frames are below the 50% threshold, which all I'm doing is just stacking garbage into it. Garbage in, garbage out. So I want to try and get as many good frames as possible. So in this particular case, we've got a large majority of all our frames is above 50%, so we can go ahead and push that pretty hard. Now remember, this setting is discard worst global frames. Automatically, it's already discounted some of the worst frames possible. In fact, where you see this exponential curve just drop off and hit the ground, virtually everything in that 25% and below is just straight up trash. I don't know how many frames that is going to be. If I had to take a guess, it's probably around about, I don't know, 100 frames. So again, 50% of the stacked frame is not based on the 2000. It's based on the number of frames, including what was discarded. So we could only end up with around about 1900 frames that are going to be stacked, 50% of those. So quick math, 450, give or take a few, at 50%. So this is where the quality graph is a very critical factor on how to read this and how to determine how many images that you can stack. Now, as opposed to doing it by a percentage, I can also force this by stacking a group of numbers. If you like to do a lot of animation, the last thing you want to do is stack a percentage of frames that are considered good or bad. What we can do is we can run through and check all of our data ahead of time. Now, if you've got 10,000 frames worth of data, I hate to be you because it's going to take all freaking day. But more importantly is this. If I want to try and keep the consistency of the quality of the animation at a constant, instead of doing percentage, I want to choose how many frames are stacked out of any one given number. So let's just assume we took 1,000 frames every 5 minutes. And as I go through this, scene conditions can vary up or down. What I like to do at this particular point is I will pre-process everything. I will check the quality graph and then determine the best point and the lowest point. And all of my data is calculated off of the lowest point of the worst piece of data that I currently collect. Now, obviously, if you do batch, any type of batch processing, this won't be able to figure it out for you. You have to go in there and look at it yourself and be strict about it. So again, let's just say 1,000 frames, we'll keep the math simple. I will look through the quality graph. If majority of all of my data is above the 50% mark, then we know we're going to get a good result. So we now look at the worst result and see how many frames can we pull to create this animation out of the worst stack. So let's just assume it was 10%. So that means we've got 100, we know we've got 100 good frames. Now, instead of telling this thing 10% and run it across the entire board, remember what I was saying? Discard worst frames. We can now end up with a number that is anywhere between 750 frames to 1,000 frames. In other words, up to 250 frames can be rejected. So instead of doing a percentage, I am now going to create a fixed number of 100 frames out of the stack, regardless of how many frames it's taken. Obviously, you can't stack 100 frames if you don't have 100 frames. It'll just give you a weird result. It'll actually run, believe it or not, but they'll just give you a funky result. So the idea here is you want to keep this number realistic. Now, once you've done that and you've batch processed the entire set, what you will find is each of your frames, as it flicks through one section to the other, will give you a nicer looking image, and they're easier to work with when you come into something like IMPPG to do the processing side of things, and you can get a relatively good consistent result. And it's better than having a percentage of a number that is a high variable. We have now taken the variable, which is the percentage, and turned it into a constant. So I hope I didn't lose you guys too much on that one, because that can be quite intensive. Of course, replay this video, watch it 1,000 times if you need to, just to get a good idea of what's actually going on. So now we're going to go look into doing the sharpening or deconvolution of all of this. So let's just reset all of this. So first of all, let's reset the histogram, and we're going to reset all of this. So what I'm referring to about the histogram is this thing here. Depending on the type of machine you have, if you've got 2 screens, this is actually a lot easier to expand this to go over to the second screen, because by default, when you've only got 1 screen, this thing is going to be like this small. And it is very, very, very hard to manipulate some of the finer details. But for the sake of this demonstration, I'm just going to assume that you've only got 1 screen so you guys can see this. Now, we can leave the sun as is. So this is its true look based upon me shooting this. So what we do is as we play around with the curve adjustments here, and remember this thing in the background is the histogram, you can see the sun get brighter and darker. So the darker it gets, the more pronounced any of the surface detail is. And you can see the active areas within the surface of the sun, some of the spicules and stuff like that, just like Clyde and Jen and everybody else was talking about earlier. We can see these magnetic field lines and how the hydrogen alpha line just follows it. I'm not the best at explaining this part because, you know, I'm just an imager, as they say. So the idea here is we're trying to find the best balance to give us the most amount of detail. In other words, we're messing around with the contrast. So pick a spot and start with it. So let's just start with the darker parts here. And then what I can do is I can add or remove more of these curves in order to create a higher contrast. So as you can see, as I pull these around, it creates a different style. Now remember, the sun is a 3D spherical object at the end of the day. So you don't want to create an image that makes it look absolutely flat, because right now it looks very flat, it's very boring, and just doesn't look right. So you have to be able to dial in and create the illusion of creating a curved surface. So by manipulating the light or the histogram, we're able to create that curved look. Now, one thing you probably notice is there are no prominences, and they've all pretty much disappeared because of this particular method. There are 2 ways to do this. You can shoot the prominence in one set, and then you can shoot the chrome sphere on another. However, with imaging, unlike doing visual, the camera can actually pick up data that we just simply can't see. And this is the beautiful thing about using 16-bit and having more dynamic range being available. In reality, there is actually data. This is why I need this thing as big as possible. We can actually see that there is actually a lot of data on the far left-hand side, which is actually where the prominence actually is. So what we're going to do is we're actually going to put our anchor point right there, and we're going to actually pull some of this up until we can actually see some of these prominences. And the higher we lift it, the more apparent it becomes. Now, we've got to be careful because otherwise it will blow out because the curve is just too steep. The idea here is we need to work through and find where it gives us the best results while keeping the background relatively dark, so we have some level of contrast. Now, there is such a thing as overdoing this, So you kind of have to find a happy medium and then just kind of work with it from there. And the more of these points that I'm adding into the histogram, the more accurate we can actually get. So we get a result which essentially gives us both the chromosphere and the prominences at the same time. Now, looking at this as an image goes, that's not bad. I mean, it looks pretty damn good, but logically to me, it doesn't really make sense, which is why when I usually do this, I like to invert the surface of the sun and then keep the background black. Otherwise, you can end up with the complete opposite where the background goes white and the surface goes black. You'll see a lot of people who do this kind of trick. It is actually quite a nice way of doing things, because if I was trying to go for the prominences, for example, this is actually a nice way to present proms in this particular fashion. And the idea here is when we do it in this particular way, the prominences are more prominent. They're way more pronounced. So again, we can tweak this to our heart's content to get it to really get dialed in. And then what tends to happen here is the surface ends up just disappearing. So again, by playing around with all of this, we can actually bring some of that back in. And again, this becomes a positive image. But what I'm going to show you now is how I like to do things when it comes down to this. So I'm just going to stretch this out a little bit so I can actually see what I'm doing. So I put in a point straight away and I pull the far right hand side down, and that creates my inverted image but retains the black background. So first of all, I want to try and dial in those prominences and get them looking as good as I can. And I do that by adding more and more of these points. And I'm just going to rush through this for the sake of time until it's dialed in. Now, you don't have to do it this particular way, but I like to see this heavy, heavy glow on the edge of the sun. I kind of like the idea behind it, although it's not actually accurate. So it's up to you how harsh you want to push that. If you don't want it too harsh, just simply dial it back a notch. And the idea here, or the aim of the game, is to not have any harsh looking edges like that. So we can pull that back until they pretty much go away. So the next thing is let's look at the surface detail. So the surface detail always sits further down the band here. So what we're going to do is, remember, this is a three-dimensional sun. We want to create that three-dimensional look. Now, to help alleviate this harsh edge, we're going to have a couple of more points here. What I want to do is find out where the edge has no detail and bleeds out. Once I find it, what I can do is I can manipulate this to try and match what I'm seeing to give me back that edge detail, and then go for that blend. So the more I define this, the better this is going to look. So you may have to play around with this. And again, let's just get rid of that. Just add a little bit of more of that. And that gives us a pretty good result in terms of making the sun look three-dimensional and not having such a harsh, strong edge. Again, it's a preference thing. I like to have a nice harsh edge. There's something about it that I enjoy. Some people actually reintroduce the black line, which is essentially this, as the separation point. So you can tell where the proms begin and where it ends. I kind of did that earlier on when I was doing the prominences earlier, so we could try and define where it stops and starts. So now that we've got this curve out of the way, and it's not bad, kind of rushed this a little bit. So once we've got that out of the way, we can then look at the deconvolution side of things. So let's just reset all of this back to its default value. And what we're doing here is we're trying to improve the sharpness. We are literally, as it says, we are deconvoluting the image. Now, since our scene conditions were so good to begin with, there is literally no sharpening that's occurred, and we already have a good image, but we know we can tweak more out of this. In fact, we're going to tweak it a bit more to get the prominences to appear even sharper. And we do that by changing some of these sliders. Highly experimental, you just have to play around with it. Again, there is no magical number. The default values is something to work off of. What I first do is I want to check out how much difference it makes when I increase the iterations. The more iterations you have, the more accurate this becomes, but it can cause artifacts. So I'm going to give you an example. So we're going to go to 500 iterations. And I'm just going to bump the sigma up just a small amount. And already we're seeing some serious artifact issues here now. And if I was to reduce that back down to a normal number, you can see the difference here. So the idea here is we kind of need to find the right amount of iterations based upon the sigma value. The sigma value, what I found here is oddly enough, it actually works pretty close to the pixel size of your current camera at its default iteration, which is 50. So 1.586 is what the 174 is. If you find that looks a little bit too blocky, start pulling it back. Now remember, this is a stacked image of whatever the percentage of the frames was, so we had a pretty good result. So I know I can pull this back. Let's pull it back to around about 1.4 and increase the amount of times that it does the processing. So that gives us a nice looking amount of deconvolution. So next we're actually going to do the sharpening. What I do is I really crank this up on purpose because I want to see what it's actually doing. And the sigma value determines how much sharpening occurs. Now, you can overcook this real fast, or you can end up underdoing it where it looks like nothing is happening. Again, it's a preference thing, so it just depends on what you like to do. So what we're going to do is let's focus more on the prominences than we are going to do on the surface details. So we need to find a point where the sigma value gives us the best result before noise becomes a massive factor. As I push, we're going to look into here. You can see that noise is getting worse and worse. And now another artifact starting to appear is this black banding that's happening where the spicules and where the prominences are. So we don't want to get into that territory because we know we're going too high. We need to find that happy medium of where it's going to be. So believe it or not, we're going to go for around about 1.45. I kind of feel that sigma is still a little too high, 1.35. Okay, that's better. And now we can actually choose how much sharpening we want to do. So we're going to work our way from the bottom and come up. You don't go crazy. Again, very subjective. A small amount goes a very, very long way. So we're going to go, like I said, we're going to look more for the prominences than we are on the surface detail. So we can afford to push this one a fair amount. I think round about there is before this image really starts crumbling apart. And if I want to try and limit the amount of horribleness on the surface, remember we're paying attention to the proms here. What I can do is just simply darken it out and have less emphasis on that and more emphasis on the actual proms. I mean, we can just completely shut it off if you want to. So there we have the prominence details being the more predominant part of this image. Now, if I was obviously going for the chromosphere, let me just raise this back up so we can see it. We would actually have to manipulate the settings to be a little bit more respectable in that particular case. So let's turn the iterations back down to 50 and just lessen the amount of sharpening. And then we're going to just bring back those details. I like to try and look for a balance and work in between the two. Again, there is no magical setting. It is just what you want to see and how far you want to push this. So I don't like to go too nuts in some cases. A little bit obviously always goes a long way. There are some situations where you do end up with a negative number or a number lower than the default value. Again, it's totally fine. So this gives us a pretty good result. So Not very many people are probably watching. Any questions, feel free to fire them off now. I'm going to be wrapping this up pretty soon because we did go over time by quite a considerable amount. So yes, get your questions in now. I will try my best to answer them, and we will go from there. So this is just basically a quick look into doing the processing side of things. If you guys want to do some of the colors and stuff like that, I will cover that in a different tutorial at another time. It is actually covered in the free tutorial that is on our telescopes.net YouTube page. Just have a dink around and you'll find it in there somewhere. I think my cat's hungry. That's why she's meowing at me so much. All right, so questions. Feel free to ask. I know you had a bunch of questions earlier, and I'm sorry if I can't get back to them because the chat window only has so much of a history, so I don't see anything any longer, unfortunately. How well does IMPPG do at aligning image sequences when it's not the whole disk? The answer is actually really damn good. I've done it a handful of times, even in the batch processing side of things, which is what this is. There are other tutorials out there that kind of go through all of this. The straight up answer is not only does it do the tracking, it also does the rotation. There is not a lot to it. There's not a lot of science behind all of this. It just does a really, really good job. Again, you can actually do the actual thing through the tools here. It's the line image sequences. When you have a whole batch of stuff together, it'll look at every single shot and it'll do an average and derotate everything. And it works, totally does work. I'm sure your dogs have been interested in the stream with the cat running around. Luckily for me, the cat can't hear nor see the dogs. Otherwise, the cat would freak out. What would your advice be doing on the histogram edits here, but then using something like Photoshop afterwards to align to edit and sharpen the proms versus the discs separately? You know, the funny thing here is I always say this. When you're doing processing, a lot of it is down to your own personal preference, and everybody has their own technique. The best way to answer that particular question is you have to find a workflow that works for you. The workflow that you're seeing that I have demonstrated doing all of this is my actual workflow that I'm used to. And I've tried to simplify it as much as possible so newcomers who get into this are not overwhelmed by all of these buttons and settings, especially when you install Auto Stacker for the first time and you're like going, what the hell am I doing? In all honesty, the default installation is going to be the best settings that you could possibly going to get. It's the average result. Now, when it comes down to the sharpening side of things, again, it's your own preference. What I tend to do is I want to try and keep my data as realistic as possible without going too Photoshop. And try and do as much of it inside of the processing program. So in other words, if I can't push one piece of detail more in one area and less in the other, then what I'm really doing is I'm trying to create a falsified result. Not to say that it's the right way or the wrong way to do something. It's actually, to me, I prefer to do it this particular way. Now, the other method obviously here is I can go into something like Photoshop and then take it out. So let's just say if you guys are into Photoshop, let's just create a mask that only has the prominence data, which is this. So now I've got a good basis to work on in Photoshop that I can then superimpose just the surface details back on through whichever method you want. This is just the easiest one, just do a mask because the mask is black. And then tweak the prominences. Actually, there is a guy, I've forgotten his name off the top of my head. He shows up on Instagram all the time. There is a guy who does this exact method. What he does is he sharpens the living daylights out of the problems. He does a fantastic job. It's almost like unreal what he does in his processing. But he processes the chromosphere, as in the surface, completely differently, and then creates a final image in Photoshop to give you this really nice, fantastic, smooth looking image. And again, it's a preference thing, it's a workflow thing, it's whatever you're comfortable with. I prefer to do it this way just purely because it gives me a more realistic result of what I'm truly getting, and that I am not, over photoshopping something. I will say that having this histogram, the more points that you have on this, the more accurate this becomes, and the smoother you can actually get this thing dialed in. I'm not going to mess around with this too much because we could be here for absolutely hours, because I have been known to sit here and, just adjust the living daylights out of this until, my eyes have glossed over. How do you determine how many frames to use? So I've already covered that. I'll go through it again because yes, it is complicated, and yes, this trips everybody over. The amount of frames that I determine that will be stacked is driven by the quality graph. Again, this line here is the 50% mark. The green line here tells me how many frames am I going to have that are going to be above the 50% mark. The idea here is anything above 50% is worth stacking, essentially. And that's what I'm doing, is I'm looking at this quality graph estimator and trying to ascertain that. This tells me that almost 75% of my frames will give me the best result. So 25%, which is from here to here, because 50% mark is also here, is what I'm going against. That would give me the best results. Now remember that I was telling you, if you have this option checked, you have to remember that any frames below the 25% threshold, which again 25% is the default, is going to be discarded. So let's just assume 100 frames are thrown away. You now only have 1900 frames out of however many percentage that you're going to stack off of. That's basically what that is. Did I miss where you went over the balance of gamma and exposure when taking the image? I didn't cover that. That's something I can't do anymore because seeing the wind, I got a cloud in my way, has kind of like just really murdered me on that. So it's kind of an awful shame because I really wanted to go into that. But I do have a tutorial that is currently up. It's up on my Patreon, or you can just simply download it for free, or not download it for free. You can watch it for free on the telescopes.net YouTube. Just have a look around for the solar tutorial that I threw up there. It's about an hour and a bit long, and it does run through the gamma and the exposure. It's just an awful shame that, weather is not being kind to us as usual. And we're here in California. It's supposed to be nice and sunny, but it's not. So sorry that I can't give you a really good answer. The idea here is, well, yeah, watch the tutorial. It's easier to explain on the tutorial than it is to not have it in front of me and show it to you, because it's quite important that I show you that. What rig did you use for image capture? So I have different setups for all of that. I have a Esprit 100, I have a Esprit 150, cough, cough, I don't use an ERF front filter on the 150. I have a Quark. I did have a Solarmax that I was using for a while, although I kind of upgraded and went for larger aperture. The mount that I'm using is the new Skywatcher EQRH Pro, which is the one that has the Renshaw encoders on there. And for me, that thing works great. I mean, you can pretty much use anything that you got. The great thing here is, if you can deal with the tracking and you have fast enough frame rates, you can even use a regular tripod without any tracking. You just got to make sure that your frame rate is relatively high. And of course, a smaller field of view would definitely help. All right, hopefully I haven't driven any of you guys too insane with this amount of information. Appreciate everybody for watching and sticking out with us it's been one heck of a long day since we started at 8 o'clock. I mean, obviously, I've had to wake up a lot earlier than that to get this thing going. We appreciate you guys watching this. We're going to try and keep on doing these live videos for as long as we can. Obviously, long after the coronavirus ends, I hope, and you guys will still keep watching this. The next video that we're going to be doing, or the next live stream we're going to be doing, is more about film photography. So if you guys are not into film and you're into the astro side of things, I do apologize, but I do recommend you watch this anyway, regardless if you're into photography or not, or film photography. It's like me going back in time, because I studied film for about a year when I was a kid, growing up in school, and it was actually quite fascinating, and it's made such a big comeback when it comes down to it. And we're going to have a couple of giveaways, so hey, who can't say no to free stuff regardless of why it's free? So hopefully you guys enjoyed that. All of these videos will be back up again for you to watch back in time. I know I'm going to be looking for that plane that flew in front of the sun. I want a copy of that. Even though I wasn't recording, it was on the YouTube stream. I want to go see that. If you guys don't know what I'm talking about, earlier on when we had with Steve Ramsden, after he had to disconnect because he was getting clouded out and he was threatening for rain and all that kind of stuff, I carried on with my live view, and this plane just flew in front of the sun, and I probably caught 1 frame's worth. But I want to see it because I've been dying to do that, and I wasn't recording at that exact moment, and I feel really upset because it was a good one. But, is what it is. So again, thank you very much for watching. Hopefully you guys enjoyed all of that. And if you guys have any suggestions for other topics that you want to see, by all means, send them through to us. You can email me directly at simon@telescopes.net. That is telescopes with an S on the end of it, .net. Or you can message us through Instagram, Facebook, whatever method that you want to choose to contact us. And if you have suggestions, feel free to reach out, and we'll see if we can incorporate those. So the next astronomy-based one, I'm doing my best to get Bob Denny, who's going to talk about ASCOM, and I'm trying to get somebody from the guys who wrote PhD2 to help dispel some of these myths and understand and learn more about guiding, because I think that even though this subject has been covered to death, there are still too many people out there who just simply don't understand how guiding works. And we get a lot of conflicting information. The idea here is from the horse's mouth, that is it, that's the final line. That's my hope, at least, anyway. So again, thank you very much. I'm not going to rabbit on any longer because I can talk for hours upon end, and I'm sure you don't want to, and I've got customers to call back who are probably getting really upset with me right now, but that's okay. So thank you very much. I am going to sign off, and I will see you on the next one, hopefully, which will be in about 2 weeks' time, give or take. So stay tuned and subscribe. Click the like button if you haven't done that already, the bell icon, and every other icon out there under the sun or on the sun. Good night.
you